Maybe we should paper over that clock.
It might take a while for that to.
Might take a while. Hello, check, check. I heard my comment about the clock half a minute later. Okay, the YouTube link is working.
I'm gonna mute back up again.
Welcome, everybody. Take a seat. Testing. Everybody can find their seats. We're going to get started. Okay. Hi, everybody. Good morning. Welcome to Quebec. We're so excited to have you here. We're absolutely thrilled that you all made it and really excited to start FRB 2025. So today we're just going to do kind of an abridged version of the introductory slides since not everybody's here yet, but we're going to give you the information you absolutely need. So before we get started, let me introduce myself. So my name is Amanda Cook. I'm one of the two people who've been emailing you consistently for the last months and months. I'm a postdoc here at McGill.
And I'm Alex Curtin. You've also been getting a lot of emails from me. I'm in the very end of my PhD.
And before we jump into the logistics, we just want to acknowledge that we've had a bunch of help, in particular financial help from these four sources. So the Astroflash Group, the Canada Excellence Research Chair Program, Trottier Space Institute, which is our Space Institute, of course, and McGill itself. So thank you so much for the support. Today is all about pedagogy. So it's the opening day. We're going to go through some of the basics, but that are not so basic, and make sure that everybody is starting on the same foot at the same time. So we'll start with Transients at Large and Common Statistic Pitfalls by Ashley Viller and then Daniela Huppenkoven. We'll jump into some radio emission, cosmology, CGM before talking about every major FRB survey and instrument. Okay.
So a few things that we need to know for today, particularly about asking questions. So we have this lovely chat box for those that are in the room. This is going to allow the people on Zoom to be able to hear you. It is very light and you just throw it.
So you throw it from one person who is asking a question to the next. It is quite light, but we don't want to hit anyone in the head. So if we need to go from the very center of the room to the very back, try to do it in some stages. There are only two microphones in this room, the catch box and the computer. So this is important to keep in mind. We want our online participants to be able to hear us at all moments in time. For those who are online, we really want them to also be able to speak up. And so we have a special hand, which is also that for the Canadian hockey team, what people might use, which will represent those who are online, and will be alternating between online and in-person questions.
And so the online people, you should feel free to raise your hand if you have a question or type it in the chat.
Mm-hmm. And those typed in the chat will be read out by, we have an online representative every day. For speaker instructions, I said we only have two mics, so please stay near the computer. You can either talk loudly or you can use this hefty, handy microphone, but the microphone does not connect to the online participants. So you still need to stay near this main computer. It just projects your voice out into the room. We have a handy dandy clicker here up at the front. The laser is not connected, but the clicker part works perfectly. And for any chairs who are in the room, speakers, remember that you need to upload your slides by 8 a.m. the day before and confirm with your chairs that your slides look all good. Lunch will be served roughly between 12 p.m. and 1 p.m. every day. It'll vary a little bit. We're going to be alternating between Mediterranean and Indian. I'm very excited. There'll be vegetarian and vegan options available every single day. But if you have any other special dietary constraint, please let us know ASAP and we will order special food for you. I think the weather should be pretty nice all week, so we'll just kind of maybe spread out outside for lunch. You can also sit inside, but McGill campus is beautiful, and feel free to kind of take a walk around if you want as well.
Yeah, so okay, so I think the code of conduct is like roughly common sense. If you want to see all of the detail of the code of conduct, it's on the website and you can have a look through it. Of course, the major points is let's just behave professionally, right? Be kind to one another. Let's not put down or insult each other. We're all here to learn. And of course, any kind of like harassment or discrimination will not be tolerated by the organizers. And please reach out to us if you have any concerns and we will deal with that ASAP.
And if you need help, you can post in the general channel. LLC members will be monitoring it actively. You can go ahead and email us, or you can go ahead and call McGill Security if anything is very serious, or of course, 911 if anything requires it. I think the only other thing I didn't say is that for those who are in person and those who are online, when you go ahead and ask a question, please make sure to introduce yourself. So those who are online or vice versa will know who's speaking. So just say who you are and where you're coming from. And I think without further ado, we can go ahead and get started.
Yeah, we'll hand over to our session chair.
Cool. Hi, everyone. My name is Lauren Rhodes. I'm a research fellow here at McGill. I am not an FRB astronomer. But I'm introducing the first series of talks today. Our first talk is coming from Ashley Villar, who is at Harvard. She is joining us online. So Ashley, if you would like to share your slides. I was trying to get rid of the people at the top. I know I did the top one, but found it.
Ashley, can we hear you?
Testing.
Oh yeah, we got you. Perfect.
Okay.
Oh no, that was the wrong button.
Okay. We can hear you.
Yes, you can hear me, I think. Can you hear me?
Yeah, we can hear you, but if you are online and you are not the speaker right now, could you please mute yourself?
Huh. I don't hear anyone else speaking.
Yes, we can hear you.
No, but I don't hear anyone else.
Oh, I know what's happening. It's the YouTube. It's the YouTube. This is not open.
We close it?
Okay, sorry. This should work now. Ashley,
Okay.
Try again.
Okay, now you should hear me and no one else.
Yeah.
Okay, great.
Amazing. Okay, let's try that. Thank you for bearing with. Yeah, so Ashley, if you'd like to take it away, yeah, you have 25 minutes.
Okay, amazing. Thank you so much. Thank you for inviting me. I'm so sorry I couldn't join in person this time, but I'll try to pop in throughout the day. So I am excited to give the first talk. I am very much coming from a different world. I don't do FRB science. I don't do radio science. I typically do optical and thermalized transient science. But I think that there's obviously a lot of overlap in the key scientific questions we're trying to answer. And I want to highlight generically some of the things that we've been thinking about in supernova science in particular for a very long time now that I think FRB science is also becoming increasingly interested in. I want to start by highlighting just the incredible complexity and breadth of time domain astrophysics, and that's really the theme of this talk. Here I'm showing this ChatGPT generated image, one, to show my love of ChatGPT, but two, to show that there's so much interesting physics that can be probed from singular objects like the neutron star. That can be observed across multiple wavelengths, that can be observed across multiple timescales. That can really give us deep insight both into how these sorts of exotic objects are formed, how they spend their life both early on and then as they fade away, and then how they kind of populate and change the cosmos around them. And so I think that what's really fun about this is that it's so multifaceted to study this phenomena in our night sky that are really changing on very human timescales. What I want to emphasize again is that the diversity that's being driven by these events fundamentally, at least to me, largely come from two key ingredients. One is understanding the progenitor systems themselves. So are these things coming, are the bumps in the night that we're looking at currently coming from neutron star systems or white dwarf systems? And what's actually powering the transient observation that we see? Is that coming from radioactive decay for me, from my optical world? Is that coming from some sort of magnetic field effect? Answering both of those questions in tandem is fundamental to really mapping out this full picture, which is largely what we're after. So that's going to be the broad roadmap of what we'll talk about here today, is loosely trying to piece those sorts of puzzles pieces together. But I also want to take a human view really quick and just emphasize to what I know everyone in the room already knows, what a cool time it is to be in time domain astrophysics. So much fun. So here I'm showing a version. Oh, did it get cut off? It did. So on the x-axis, that's the years. And then on the y-axis is the cumulative discovery for 3 different, I don't know, kind of characteristic classes of transients, probing the gamma rays, optical, and radio. So I'm showing you supernovae. I've rescaled it so that they all look a little bit closer to the same, which has been experiencing an exponential growth for the last few decades just due to technological advances in CCD detector technology, still CCDs. Gamma ray bursts, which have been experiencing linear growth for quite a while. I hope that they get their own explosion, but it's challenging to find these space-based probes. And then really exciting, of course, in blue is FRB growth, which has just had this absolute explosion of discoveries thanks to dedicated missions like CHIME, DSA 100, that are fundamentally changing the field itself. And I'm out of date. Like this, so this is coming from just an online FRB catalog, but I know that there are thousands at this point FRBs discovered. Looking forward, so just in order 5 years, I think what's really fun is that most of these fields are going to continue with this explosion in exponential or even past exponential growth. For supernova science, we're incredibly excited right now about the Vera Rubin Observatory that just took its first images recently. That will change our discovery rate from order 10,000 events per year to 1 million events per year. FRBs too, my understanding is that with, again, increasingly large online missions here, like DSA 2000 is what I'm most familiar with, we should be expecting also orders 10,000s, if not 10,000 events discovered annually, which is really exciting to think about. If we have those localizations, we can really piece together the progenitors and the launching physics of these sorts of phenomena. A little sad tale is GRBs, again, they won't quite have that explosion. They'll probably continue on their linear growth. I hope they continue at least linearly. We'll see. Okay. So this is all just to say, like, super fun time. We are all, I think, entering this exciting big data era together, although of course that means different, let's see, what do I want to say? Different sorts of data volumes that we're experiencing and different time scales. So back to science, though. What can we do with this influx? I think one of the most exciting things that's also just very simple is that we can map out diversity. We can really start to take these huge populations, capture some easy features from them, and make these sorts of plots where we understand, can I actually classify the underlying physical phenomena and progenitor systems just by sorting them into these simple features? I don't know what Daniela will talk about, but like you can imagine doing this in much more complicated ways to really help us understand the underlying physics. But this is a very common sort of plot where I just measure some form of a duration, how long that event lasts. And here we think about exactly where I'm observing it and how long kind of coherent bursts last, versus how much energy is that thing outputting. So some form of a luminosity. Why these are so rich, you can see right away. You can see that there are often gaps that are not due to observational effects between clear classes. Here, just highlighting things like true FRBs versus more typical pulsar radio, repeating radio behavior. We can use this then to make broader physical statements, even though these are pretty simple to measure. So if I take the same kind of picture and zoom out, this gets much more complicated, I realize, but what I want to highlight is that many phenomena are emitting in radio waves, and their position here is telling us really fundamental statements about their physics. For example, we can make simple statements about whether or not the radio emission we see is coherent or incoherent. We can also understand, so saying in a different way, if we're seeing synchrotron emission, some form of thermal emission, just from understanding these simple features. This is also something that is very much done in the supernova world, where we also plot kind of these characteristic timescales and how much energy is being output as a function of time. And we similarly see these clear kind of separations that are telling us about the underlying engines themselves, tied to whatever progenitor is pushing that engine. In our world, I will say that there is a complication more on the timescale side of things, in that because I look at the optical, that's typically thermalized emission, which just means that my photons have been rattled around in the ejecta material. The localized ejecta, to be clear, this is not a line of sight effect. That kind of fluffs out it blurs out these blobs and makes them actual blobs. So I'm not looking directly at the emission mechanism, I'm looking at it pass through some sort of filter. I'm not an expert in radio. I think there are obviously, though, kind of similar effects that you see too, this blurring function that complicates the picture. One of them is, of course, understanding dispersion effects. So may or may not be localized, but that blurs out this kind of system that we see. The other one that's not really, I don't think this is true for FRBs. We also, of course, this is, oh, I don't have that. I have it here. This is secretly an isotropic equivalent energy. So we're not assuming any jetted physics or anything like that. So there's this blurring function that obviously occurs in these sorts of phase spaces, but even so, there's such a rich amount of physics to explore in mapping out that diversity. A third axis of diversity that really complicates things again is that we can observe across an incredibly wide range of wavelengths to probe different physics of the same phenomenon. And I think we know this, but let's be clear. All the way from the radio, where we can be looking at, again, coherent emission, if I'm thinking about FRBs, thinking about synchrotron emission, particularly for me from supernovae, through the IR/optical UV, where I'm really probing thermalized emission. That's something about the photospheric phase of these events when they're optically thick. Through X-rays and gamma rays, which once again gets to synchrotron, non-thermal emission functions that probes more things like jetted emission or, again, interaction. So that's just to say the phase space that we see observationally is incredibly diverse because of these multifaceted effects. Some are coming from the physics themselves, some are coming from how we're observing the physics. Going back, now, instead of looking observationally, let's turn for a second and think of it more that we're excellent theorists, and what if we really could map out exactly the pathways of these events? This is also a very complicated picture. Here I made, sorry, it's not easy to see, but I've made this kind of flowchart diagram to just really show the complexity of the final transit events that we see. I'm mainly highlighting supernovae, what I do, and their initial progenitors, we think, which can range from, of course, compact objects to massive stars, and the flavors of how they undergo their lives. So whether that be from binary interaction, or undergoing core collapse, and then as their compact object, continuing to undergo some sort of interaction with baryonic material around them, it causally changes the sort of transient that we see that further leads to these complications. So it's not just a observational curiosity that we see so much diversity. It really is being driven by the underlying astrophysics. FRBs are fun because I think that we don't quite know where they live yet on this already complex graph, and I hope and assume that there'll be some discussion of the many theoretical pathways you might see. Okay, let's dive in a little bit more, just some lessons learned, particularly from, I'll mainly focus on core collapse supernovae, of specifically what can we glean from observations of progenitor systems, and then we'll talk a bit about power sources. Taking a step back and just saying a statement first on some supernova science. So I mainly study core collapse supernovae, which I think are probably very relevant for FRBs. You can tell what team I live on for their progenitors. So core collapse supernovae are from massive stars that are spending their life burning away, fusing elements into heavier elements. They do so at the inner cores, the hottest and highest pressure points of their star, and they actually form these onion structures. This is a cartoon, but they really do kind of form these onion structures of unburned material from the lightest elements to the heaviest elements before fusion becomes an endothermic process. And if we assume that supernovae are from single massive stars, they're living their life, I think what's quite beautiful is that we can map out how we think those stars will eventually explode. There's this whole zoo that's taxonomy that's quite complicated and we won't get into, but basically we take spectroscopy in the optical of supernovae and we look to see what elements are present or not present. But more importantly, that's telling us whether or not envelopes of so the relatively low density mass are present within the star at the time of explosion. Sometimes it turns out stars are seemingly missing all of their hydrogen. That's very abnormal because we typically don't burn through all of that hydrogen. Instead, what we think is happening is if I am a large massive star and I lose mass via metal-driven lines, then I can lose sufficient mass throughout my life to be totally stripped of that material. And that typically means I have no hydrogen, and sometimes I even have no helium present. I'm just a kind of core, a carbon-oxygen core. Okay, so that's to say that with our basic theories, we can kind of map out what we think is happening here. Partially why we do this. One, that explains the observations we see, but also then we can map that back into what I call the progeny, or what the compact object that's left over after that explosion. I apologize, this picture is always very hard to read, but it is this is a great review paper and one of my favorite pictures. So what I'm showing you is exactly the same sort of phase space of what is my initial ZAMS mass, what is my metallicity, but now I'm color coding it by the compact object type that I will leave. And again, assuming that I'm kind of a single massive star, I can map out if I will leave behind a neutron star, a black hole, or if actually I might even leave behind no object if it's a direct collapse. Okay, note that this has gotten obviously much more complicated, even the single star picture. But that's just to say that there is a direct link, although challenging to make, between the observations we see from these supernovae all the way to what it's actually leaving behind. So that seems great. Maybe the progenitor question is quite straightforward if we just work on exactly those observations. Of course, that's not true. So one of the biggest complicating factors, in my opinion, of the diversity that we see from transients generically is the fact that massive stars, basically all massive stars, live in binaries. And many of those live in binaries that cannot be even treated as isolated stars. That means they interact with each other. This is a very extreme scenario from NASA where two neutron stars hit each other. But throughout the life, two binary stars might continuously interact. In particular, what we can imagine, if you remember from your stellar physics class, I can fill up my Roche lobe and actually accrete onto my companion star, changing both their chemical history and how they will evolve, but also changing myself and how I will explode. So in this, I forgot to cite, but in this cartoon image, I'm showing here accretion that eventually leads to me stripping my hydrogen envelope without needing to be an incredibly massive star, without needing to have my own metal-driven winds. And that allows me to explode as these kind of complex subtypes of strip stars that otherwise would be clear signals of things like black holes in a wide range of masses. And in fact, we think that common envelope physics can continue to the secondary star. It can also lose its envelope, and eventually it too can explode as a highly stripped event. So these interactions directly change the observations we see and complicate the sort of compact objects we can infer left behind. We'll get to that in 1 second. In supernova science, I'll say this is kind of the holy grail question. It's like, okay, what is that mapping then? There are interesting theories that say maybe binaries like magnetars, can fix everything and explain everything that we see. Maybe we can connect together this complex zoo of observational signatures of having an envelope, not having an envelope, interacting with stuff I've like erupted off, seemingly having maybe engines formed. Maybe I can connect all of that with just different scenarios of a binary system in different configurations that changes the timescale at which I interact before explosion. And then there's a sense in which I've simplified the problem again. I've removed a lot, not entirely, but a lot of effects of like the mass of the progenitor star, and I've replaced it with this complex phase space of the binary system itself. I think that this is not the solution. This is to emphasize that this once again just means that the lives of these stars are incredibly complicated, and understanding where their final endpoints is not a very straightforward mapping necessarily. And as a last point, as we saw in our cute GIF, these stars are also obviously, well, occasionally, they can also hit each other and actually collide and merge. Again, I'm showing you a biased view. Here I'm showing what happens when, imagine a scenario we've already cartoonified. I have two stars, they've interacted throughout their life, they've left behind two neutron stars. If those neutron stars then collide, we see yet another thermalized transient that we can observe called the kilonova that importantly physically highlights where the heaviest elements in our universe are being formed, which require rapid neutron capture. What I want to say though is that the time scales of those sorts of events, so me exploding as a massive star versus me colliding with a companion, are incredibly distinct. As a massive star, I'm only going to live my life for tens of millions of years. Really, like, snapshot, nothing. However, once I've died and left behind some compact companion, ignoring common envelope physics, one of the only ways I can lose energy in my binary is through gravitational waves, and that's very inefficient. And so actually getting to a merger system is an incredibly different pathway of a transient in terms of time scale and, of course, engines than it is from a core collapse supernova. And yet we still observe these things in the same way in the optical and the gamma rays and the radio. Okay, so all that's just to say that the zoo of observational properties of the transients that we observe is only partially driven by progenitor scenarios, which includes kind of complexity of intrinsic to stellar evolution, but also very, maybe more importantly, binary interaction and how that changes stellar outcomes. Switching gears just a little bit, I also want to highlight though how we don't, I think it's clear now, we don't actually observe progenitor systems. That's not what happens. In the transient, we observe some underlying engine or power source that's driving some sort of explosion or eruption, something. This is also incredibly diverse, even just in supernova science, although I'm highlighting slightly broader than that here. In a most traditional supernova, we imagine that what we learn about in class typically is that, okay, I have been fusing heavy elements. I finally have gotten to nickel. That nickel's unstable. I radioactively decay. That powers the explosion I see. Fine. It turns out, though, I think especially important for this audience, there are many other engines that can also feed back into that ejecta and that explosion and completely change the observations that we see. In particular, I want to highlight this idea of a magnetar. If I form a neutron star, that neutron star happens to be rapidly rotating, it happens to have a high magnetic field, we think that that neutron star can very quickly spin down by feeding its angular momentum into the expanding ejecta of the supernova itself. And that acts as an additional engine that drives the explosion and contributes, especially at early times, more energy than, well, and late times, than radioactive decay. Here I'm showing you a theorized light curve that has both nickel 56 contributions, that's radioactive decay, and then a magnetar injection, and just kind of arbitrarily scaled so that they look similar energies. Importantly, you can see that they have clearly different effects, though, at late times, despite having similar peaks and rise times. So even though these can both come from the explosion of a core collapse supernova, they look incredibly different. And we see this. We're pretty sure we see this. When we look at supernovae, there's an exotic class called superluminous supernovae, where we can do tests of looking at the tail, and we can ask, is this following, and here, I've chosen one that's a little ambiguous, but they're not ambiguous. We can ask, is this following the expectation of radioactive decay? Or is actually the decay following exactly what we expect for a magnetar system spinning down? And we have found many lines of evidence that do suggest, yeah, these sorts of exotic supernovae that are stripped of their hydrogen, their helium, do seem to have magnetars. Although we're still totally unsure what the origin of those actually are, meaning the progenitors themselves. I will skip this just for the sake of skipping it, and just say that this is to emphasize the point that engines are causally linked to the progenitors themselves, but independently contribute to the diversity that we see. As a last is my last little theme, which is just to say that the context of these guys helps a lot and matters maybe as much as the explosion itself. Understanding the environments that these sorts of explosions come from is fundamental in connecting the progenitors. Maybe not the engines, but like definitely understanding the question of the progenitors themselves. Here just showing you a picture of two galaxies. One is happily forming stars and one is red and dead. And the transients that we see are a sample, one star, from this massive collection of billions of stars that we call a galaxy. It's not a random sample, but understanding that the stars within a galaxy are young, therefore massive, is very different sort of collection I can pull from than a galaxy in which the stars have had giga years, in which they're no longer forming massive progenitor systems. It can directly tell us that the progenitor of the system that we're seeing is from something young that has recently been birthed, or with some sort of delayed channel that has needed a long amount of time to actually explode. Even just zooming into core collapse supernovae, this picture, host galaxies give us a lot of clues that there is some key difference between their progenitor systems. This is a really confusing plot. I just want to show you two subsets. There's this one and then this one. Superluminous supernovae are the one that I'm highlighting that we think come from magnetars. Really interestingly, they love very low mass, which means very low metallicity and also high specific star formation rate, galaxies. Really weird. There's something about maybe that they love massive progenitor stars, maybe something to do with binarity, but they love to be preferentially in these weird galaxies. I want to contrast that with type 2s. Sorry, the naming scheme is so annoying. They're like the standard, if you hear core collapse, that's what we're talking about. They typically follow what you think, just like massive star-forming galaxies. If I'm forming galaxies, I preferentially blow up there. Very different sort of populations here. These love, the normal type 2s love high metallicity galaxies because those are bigger. Whereas superluminous, the magnetar ones, really have a distinct preference. This is weird when you fold in this idea of FRBs. And I'm not the expert on this. This is a massively, very quickly growing literature. I'm just highlighting a few examples. And again, apologies, it's complicated. I'm showing you here the distribution of galaxy masses, cumulative distribution for FRBs in black, and then comparing it, and I was not on this paper, but comparing it to other populations of transients. And particularly, the takeaway of this paper, the claim of the authors, is that this seems consistent with quark flap supernovae. Seems like they prefer to trace ongoing star formation, massive galaxies, high metallicity, just like the type 2s. Which I will note do not make magnetars. Okay, more recent work, although I don't think this has been reviewed yet, I don't know, has shown, again, through kind of statistical analysis, you can basically just ask, unfortunately, metallicity and star formation are correlated because mass is, I have more stars, I have more star formation. So you can ask a question like, what's actually the causal driving factor? Is it mass or is it star formation? That's what these authors do, and they basically claim that actually it seems like these are more mass weighted than they, FRB progenitors are more mass weighted in preference than they are star forming. More like type 1As, which is a very delayed channel. A little confusing since most of them seem to be coming from star forming galaxies. The incredibly precise localizations are helping unravel this story a bit more, although it's still very complicated. And I just want to highlight this recent result from CHIME, where a very high precision localization allowed it to be associated with a FRB associated with like a clearly dead galaxy. Clearly, this FRB at least seems to be coming from a delayed channel. But to highlight, that's not actually true for most FRBs. Once again, very recently, I'm highlighting a CHIME result. A very high precision localization has allowed it to be associated to a very nearby, although not exactly on, H1 region. That again highlights, in this case, that it might be coming from a younger sort of population. I think that increasingly these localizations are key, and the host galaxies are a very, very helpful diagnostic of the progenitors themselves. Okay, in my 0 minutes, I'm just highlighting here, again, emphasizing what a fun time to be in time domain. I haven't added all the FRB missions because I know that you have a whole session on it. But at least in the optical UV, incredible amount of new mission coming up, well, hopefully, that should be continuously changing the way that we're viewing these events, both in kind of the wavelength space, but also just the rates at which we see them. So I'm going to stop there, and I'm happy if I have time to take any questions.
Thank you, Ashley. That was an excellent start to the conference, I think. Not that I'm biased at all. I also work on other types of transients. So now we have a couple minutes to invite questions. So do we have any questions in person or online? And please don't be shy. Seriously? No one? Oh, Jason. Okay. I don't want to start this. Yeah, no, I have zero hand-eye coordination.
Yeah, thanks for the nice talk. So you distinguished supernovae that make magnetars and don't make magnetars. But to be a bit more specific, I think you mean the ones where there's obviously a role of the magnetar at early times in powering the explosion, right? I guess we're still kind of vague on which supernovae produce magnetars that are maybe less rapidly spinning, but still become magnetically powered, right?
Yeah, you're exactly correct. So the superluminous ones are ones that at early times contribute sufficient energy, presumably from spin down, that they impact the thermal transient. But you are totally right. We don't understand the connection between that much smaller time scale effect and longer time scale. And to emphasize, the type 2, so the typical quark collapse, of course, can lead to neutron stars, as we saw in the pictures I've shown. But there seems to be a preference for incredibly strong magnetars in these dwarf galaxies, so low metallicity environments.
Awesome. Any other? We have a question online. Oh, we need to. You need the thing, the catch box. Oh my god.
Hi, hello. Can you hear me?
I
Oh,
can.
yes.
Beautiful. Thank you. Hey, thank you, Ashley, for the great talk. Forgive me if you had mentioned this earlier, but in terms of potentially identifying in the future FRBs that actually are originating from core collapse supernovae, what do you consider to be like? Would the smoking gun piece of observational evidence be detections of afterglows or afterglows at certain times after the occurrence of the FRB? What do you consider to be things that would be useful for us to actually yield that kind of an association?
Yeah, so I will slightly not punt it, but oh, you're not in the room. Tara Nayeftakari, I think, has very interesting work, and Brian Metzger on the theory side. And I want to make sure I say it properly. I think I will. So one thing that we might expect is that if we have, Tara, you should correct me though if I'm wrong, a pulsar wind nebula at much later, like order decade after the supernova, we might expect then FRB sources to emit from those exact same objects. And so one observational, let's see, what do I want to say? One observational campaign you can imagine is to look at these sorts of known supernova but nearby sources ordered years to decades after their explosion themselves. This has not yielded a notable smoking gun signature yet.
Okay, we don't have time for any more questions right now, but Ashley is available online. That's terrifying. So our next speaker is Daniela Huppenkoten, who's going to be talking about statistics. So Daniela, if you want to share your screen. Awesome. So you have 25 minutes starting now.
Does it look okay? Can you all hear me?
Yeah.
Okay. Hello. I can't see you, unfortunately, but I'm very excited to be part of this meeting. I'm very sorry I can't be there in person, but I'm glad I can participate and join you online. Okay, so I call this Adventures in FRB Statistics. I am much more on the statistics side currently than I'm on the FRB side, although I've sort of dipped my toe into some studies. And I'm going to try to talk a little bit. The brief was to do a little bit of a pedagogical talk. And so I thought I'd talk a little bit about what I've sort of seen in FRB studies where I think sort of how it fits into how at least I think about statistics, and sort of also what you might want to think about when you do analyses, and where some of the pitfalls are. Okay, I'm gonna start with an acknowledgement that all of you are here for FRBs, and at least 50% of you are probably bored by statistics. So I'm gonna try to make this a little bit interesting, but also maybe you're asking, why should we think about statistics at all? And so I like to think about data. I like to think about science in the context of data. And at the moment, I really like to think about the relationship between the complexity of the data that we have and the complexity of the models that we have to work with. And so you can do this in various ways. I like to think about it like this. On this axis, where on one side you have very precise models and very complex data sets. And I think sort of to me, the poster child of this is kind of cosmology, where you have a very good theory and then have very, very complicated data that you're trying to compare to that theory. There's a lot of different things that you can put sort of more in the middle. I work on black hole accretion a lot of the time. And then there's things like maybe exoplanet atmosphere or something where, again, you have like clear astrophysical models, and then you're trying to compare them to fairly complicated data. And I suspect some of the theorists might argue with me about it, but to me, if I look at fast radio bursts, it's sort of fairly far on the other side. We really have a lot of data, and there are a lot of theories that could explain the data. But at the moment, I think a lot of it is not the models aren't really what we would call in statistics generative models. So models that would really produce a fast radio burst from physical models and first principles. If there's now outcries in the room, I can't see them, but you're welcome to talk to me on Slack about it later. But this is sort of broadly how I think about it. And I think this sort of determines a little bit on how we do our science. On the sort of side where we have precise models and complex data sets, you do what I would call high precision inference. This is a lot of things like very complicated Bayesian studies and so on. And then on the fast radio burst side, what I at least currently see is a lot of kind of data-driven modeling where you try to compute some form of summaries of the data and then try to compare that to the physical models that we currently have. And I think that sort of admits different approaches to the science, and that also causes different types of challenges that you might end up facing. And so if I can give you one more high-level thing about science, I want to talk about Box loop. George Box was a statistician. He is famous for saying all models are wrong, but some are useful. But sort of David Bly, who is also a well-known statistician, he sort of encapsulated how Box thinks about science as a whole in this kind of idea of Box's loop, where you start with building a model. And hopefully, usually that is where a lot of your physics goes, where you try to calculate from first principles what kind of emission you might see, and you put it through your telescope and so on. But in data-driven modeling, we often use very empirical models as well. And then you compare that model to data and you try to infer some kind of quantities that you want to know. And that is where statistics come in. This is why we're doing statistics, because statistics is how we compare data to models. And then the sort of next part of what you want to do is you want to criticize your model. You want to ask yourself, is the model actually good? Does it do a good job of explaining the data? Does it make sense? And usually you find out, no, it's because all of our models are simplification in some ways. And so then you go back and you revise your model and you go through all this again. And that is sort of often a mix of statistics. You use statistical methods to criticize your model, but also this is where your physics knowledge comes in of like, do my results, do they make physical sense? And then ideally, if you have a reasonably good model, you want to apply it. For example, you might say, if you, for example, know that your FRB periodically has recurring burst episodes, you can then use that to, for example, plan the next set of observations. And so we're going to use this box loop to sort of go through the details, go through this in a bit of a detail. And I want to pick an example that I know a lot about in terms of the statistical methods, because I've worked on it my entire career. And that is periodicity detection, which I think is also a big field and part of in fast radio bursts, and we're going to talk about some of the examples in fast radio bursts. But I also want to highlight that a lot of the things that I'm going to say are generally true for any type of statistical analysis you might do, not just for fast radio bursts. Okay, so why do you might want to find periodicities in fast radio bursts? One reason is, if fast radio bursts come from magnetars, you would expect to see a rotation period. And so one goal might be, if you look for periodicities in a fast radio burst, maybe it's tied to the rotation period of a magnetar. But even if it's not, there's only a limited number of processes that can make strictly periodic signals. And so if you find one, that immediately constrains what kind of emission process you can have. And then there have been detections of recurrence episodes, periodic recurrence episodes, where repeating FRBs show periodic or quasi-periodic bursting episodes. And then the idea is maybe this is related to some form of binary orbit, that this source is non-binary or something. Okay. The first thing I want to say when it comes to periodicity detection is to not trust your eyes. And I'm going to give you an example here. Here's a transient. It's not a fast radio burst. In fact, it's nothing at all. I simulated this data. And if you just look at it, you're like, oh, these peaks, they kind of look like they, show up in a maybe on some characteristic quasi-periodic timescale. And if you do a periodogram of this, you would actually find something that looks a bit like a periodic signal. But I can tell you, because I simulated this data, that there's no period in the data. And part of this is due to an effect called pareidolia. This is a sort of psychologic cognitive effect because humans are very, very good at seeing patterns in stochastic processes. For example, this is what allows us to do things like see a man on the moon or a face on the moon, or to see often religious figures and slices of toast is something that I've seen. And so when you look at some data, especially when you look at data that has a lot of stochastic processes in it, you want to be a little bit careful when looking at it by eye, because stochastic processes can fool our eyes very much. So if we can't trust our eyes, what do we do? Well, the key is to start building models. And for periodicity detection and for many other statistical methods, astronomers would often like to make no assumptions at all. This would be great. Unfortunately, this is not how statistics works. And so we have to make some assumptions in building our models, even if they might be a bit implicit. And so let's look at some models for periodic signals. The most straightforward model is a sinusoid. And sort of this is just what it looks like. It's a sinusoidal curve. If you Fourier transform it, you get a parallelogram that looks like this. It has sort of one big peak, and it looks that nice and clean because it has no noise in it. And ideally, it should be approximately a delta function and just broadened by the fact that we don't have an infinitely long light curve. You might also have things that are periodic but not sinusoidal, like this one that I simulated actually when I was studying asteroids for a while. And there again, you have, very clean peaks, but now you have multiple, and you might not have the highest peak at the period of the signal. And then this is what I call pulsar-like, where usually you have it's mostly flat, but then on a periodic timescale, you kind of have a peak in the light curve. And again, you can see the kind of patterns that it makes in the parallelogram. If we think about quasi-periodic signals, you might, for example, have a sinusoid. So it's strictly periodic, but the amplitude changes. And then you get a parallelogram like the thing on the right, which we often model with a Lorentzian. And you can see that now power spreads over the entire parallelogram and is no longer concentrated on a single peak. You can also have even more stochastic processes like a stochastically driven damped harmonic oscillator. This then ties it maybe a little bit more to some physics, but it gives you the same kind of shape. But we don't only need models for our periodic signal, we also need models for whatever the FRB does if it's not periodic, so what we call the background process. And the standard assumption a lot of the time is what we call white noise. And this is sort of just randomly uncorrelated random events. For example, here I put in a periodic signal, but you can see the power spectrum of this is flat. And then ideally the periodic signal will stick out as a much higher peak than everything else. Oops, sorry, that was the wrong direction. And so we know statistically how to model parallelograms of white noise, and we do that quite regularly. You use a chi-square distribution with 2 degrees of freedom. And then you're asking whether any peak that you see is an outlier with respect to that noise distribution. And I've seen that quite often in these kind of studies. This model makes a lot of assumptions. So this is a model. The model here is that your process, for example, your FRB arrival times, are constant white noise. It assumes that those signal properties do not change over time in what is called stationarity. It assumes that the power is concentrated in a single frequency bin, which assumes a near periodic signal. And it also assumes statistical independence of power spectrum bins. And in FRB studies, people often use Lomscargill parallelograms, which are useful if your data is not evenly sampled because you have observation gaps and so on. And particularly that assumption is often broken in these kind of studies. And so one big thing I want you to take away from this talk is that for any statistical test, you kind of have to know what the assumptions are, and then you have to ask yourself critically, does my data actually fulfill all of these assumptions? And if not, maybe you need to pick a different kind of model. The other model that we often use is this kind of model for correlated variability. You can see the light curve has lots of bumps and and going up and down. And the power spectrum now has this power law component at low frequencies. But again, you kind of ask the same question. For this kind of process, we know that the parallelogram is still chi-square distributed, but now around this underlying power law process. But you then again ask the same question of whether that peak is an outlier. And again, this makes assumptions. It also assumes stationarity. It also assumes that power is concentrated in single frequency bands, and it also assumes the statistical independence of power spectrum bands. And you can see here in red, I put in the 3 sigma detection threshold for a period if it's just white noise. And you can see that the powers at low frequencies kind of, in this case, highly exceed that. Okay, some examples that I've seen in the FRB literature are for variability models. Before I say this, I think one thing that's also useful to highlight is all hypothesis testing and model comparison methods basically directly compare two models. So usually a model for the variability in your fast radio burst or in your repeater, and then a model with that variability and some kind of period. It does not make any statements about any sort of variability that is not part of these two models. So if you have any variability in these the data that is not modeled in your choices for hypotheses, then that might really mess up your results. So here's an example from this FRB detected with Chime, where they looked for a periodic signal. And so the assumption here is that the FRB is composed of individual pulses that you can model with a generic function, and you expect the pulses to arrive strictly periodically or randomly following a Poisson process. And so you can see there's actually a lot of assumptions in here that you can ask yourself or discuss whether those are meaningful, both from the data point of view and from the view of physics. I cannot say this. This is a question for, FRB physics theorists. But I want to highlight that there are a lot of assumptions in there. Here's an example. This is a parallelogram and then a phase diagram for a repeater. And specifically, they were looking at whether this repeater has periodic episodes of bursting. And so here the idea is that the FRB arrival times are random and strictly uncorrelated, or they might arrive in a fixed periodically recurring activity window where that activity window can take up sort of more than 50% of the phase. And again, there's a bunch of assumptions in here that you make about the data, and then you go ahead and you compare those two models. But the thing that's maybe important to know is that if either of these hypotheses do not reasonably reflect reality in a particular year data, for whatever reason, that could be because of your sampling pattern or because FRBs do a different thing, then the results will be unreliable. I also want to highlight that all of these models are empirical, they're not physical. And I think physical models would make our statistical tests much more robust. However, that's kind of, I understand that FRBs are kind of hard to model. But whenever we can inject more physics into these, I think things would get better. Okay, in terms of inferring quantities, usually that's done with a hypothesis testing and a frequentist model or model comparison of Bayesian version. And so here's an example of your burst arrival times, where you're trying to figure out whether your burst arrival times cluster in a periodic way. And so your null hypothesis is that your burst arrival times are not clustered. They arrive sort of uniformly and randomly distributed in time, or that they cluster periodically. And so when you set up a null hypothesis test, you always start with a conjecture, and that's the quasi-periodic clustering. You set up a null hypothesis that they're not clustering, that they're uniformly and randomly distributed. The test statistic you might set up is maybe the highest power in the parallelogram, because the sort of outliers would give you some kind of measure of a periodicity. As I said earlier, the test distribution is then a chi-square distribution. This is basically the assumptions that you make is that your process is uniform, that the powers are randomly distributed, there is no correlated variability, and also your process is stationary. And so then the decision rule is you can set up a threshold, and if your maximum power in your parallelogram is higher than that threshold, you say, okay, I found a periodicity, or at least I have rejected the null hypothesis. So this is in general how we do hypothesis testing. Okay, so then I looked into FRB arrival statistics, and I found that it's very confusing. Maybe in some works it's a Poisson process, but maybe it's actually a Poisson process with a variable rate, because some of these repeaters seem to do go through these bursting episodes. It may be a Weibull distribution. So this is a distribution for the waiting time distribution plotted here between consecutive bursts. This waiting time distribution can also maybe be log normal in some cases, or possibly a Paula distribution. So there's lots of different models for different repeaters and different sort of bursting episodes. But one thing that I would point out is that none of these are a Poisson process, and that might affect your periodicity detection. So this is data that I generated a few days ago, and I said, well, this is what uniform sampling is. The red 3 lines here are the 1, 2, and 3 sigma detection thresholds. There's no signal in here, so there's nothing that would rise to 3 sigma. Everything's great. And so here's what happens if you put in a Weibull distribution where your FRB episodes actually cluster in time, and then you do a parallelogram. And again, you put in your 3 detection levels, assuming that actually your process is this kind of uniform sampling, and you can see you now have lots of powers that exceed that kind of that limit. And so if this is actually the underlying process for your data, but the Poisson distribution is what you assume for your periodicity detection, you might get spurious detection just from the fact that your null hypothesis isn't right. Here's just for completeness, a Weibull distribution, a different Weibull distribution. If you push one of the parameters of the Weibull distribution very far, it actually becomes a strictly periodic process. But I wanted to highlight that, the null hypothesis you assume really can change whether you make a detection, whether the detection is robust. If you don't know exactly, well, you do have to know what your null hypothesis is, but if you don't know how to estimate the distribution for your test statistics, which for the Poisson case, it's easy, it's chi-squared. For other distribution, it might be harder. What you want to do is basically simulate from your null hypothesis and then get an empirical distribution for your null hypothesis. And this is what this paper did. They did a parallelogram, you can see here, and we're looking at the signal of like 161 days. And then they said, well, we want to know whether this is due to our observation pattern. And so they simulated from the observation pattern from the null hypothesis, and then put in these empirical 1, 2, and 3 sigma limits, which I think is nice. So simulating from your null hypothesis is a really good way to estimate what test statistics you might expect under that hypothesis. Okay, and then I want to briefly talk about how we critique models. And so the first side note I want to make here is that if you make parallelograms of transients, don't plot them on a linear scale, plot them at least the y-axis on a log scale. And this is if you have any sort of correlated stochastic process, you have this, here's the linear parallelogram, and you might like, wait, big peak might be a periodic signal. But if you plot it on a log-log scale, you see that this peak here actually fits in with the general statistical distribution of this kind of Paula-shaped model. So again, this is a way your plotting might mislead your eye. Okay. One thing that's really useful is, again, to critique what's happening, is to, again, simulate from your null hypothesis and then compare that to your actual data. Here's a plot I made. This is parallelograms. In black is the parallelogram of the data. This is actually for a gamma ray burst, not an FRB. And then in orange are parallelograms that I simulated from my null hypothesis. And I was like, this looks great. But then if you actually plot the corresponding light curves, you get something like this. And so in black is the gamma ray burst, in orange is the simulated data, and you can see that they really don't look very similar at all. Here's sort of a different example again that I thought I'd simulate for fast radio bursts, where, here's simulated data again, which I pulled from a Weibull distribution, and here's one from the Poisson null hypothesis. And maybe you look at these and you're like, yeah, maybe my null hypothesis isn't quite right. In the same vein, it's kind of important to know your statistical assumptions. And in particular, the reason why this goes wrong here with the gamma ray bursts is that the process that we assumes stationarity. So it assumes that the properties don't change over time. But for any transient, this is blatantly untrue because transients have a start and an end date, and they do a lot of stuff over the course of the transient. And so this is not really a good model. And this is true for many periodicity detection methods who implicitly assume this. And in a paper in 2022 led by Moritz Hübner, we found out that actually doing that assumption tends to cause an overestimation of periodicity significance. And so this is something to be really careful of. Okay. Then the last thing I want to talk about is one thing you can ask yourself when looking at your plots is whether your distributions make sense. And one way you can sort of look at this here, and again, I've made a parallelogram, I've put in my 3 sigma limits, and sort of if I look at this, a 3 sigma limit means that you should only exceed your detection threshold, 3 sigma threshold by chance, 1 in 1,000 times. And so if I look at this, I'm like, clearly something is wrong here because either I have 15 periodicities in here, or my null hypothesis isn't not right, or I've done something else incorrectly. And what I've done incorrectly here is that I didn't take into account the number of trials, so the number of frequencies in my parallelogram, which is about 500. And so if you take that into account appropriately, all of your detection thresholds move up, and now nothing is above 3 sigma, which it should be because it's simulated data and there's no periodicity. Okay, I'm going to mention one more thing, and then I'm going to finish up. And the point is that a number of trials corrections are actually quite complicated in practice. Here's an XKCD comic where people, test all different colors of jelly beans against the probability of getting acne, and they found that green jelly beans are linked to acne, but they didn't take into account that they did sort of, 30 different tests. This is what, if done maliciously, is called p-hacking, and I think astronomy as a field is quite good at guarding against this. But what Gelman and Loken point out in this great study of this great paper in 2013 is that a lot of the times we make implicit decisions in our data analysis that might actually have a similar effect in practice. And this is because data-driven analyses are often an iterative process where a hypothesis and test may be chosen contingent on the data. So for example, you might take the CHIME FRB catalog and look at all of the FRBs and say, that one looks a bit like it might have a period. And then you run a periodicity test on that burst and present the results on that burst, but you might not talk about the fact that you actually by eye looked through 400 of these bursts and just, pick the one that looked like it might have a signal. And so there's a lot of these implicit kind of decisions made, especially in data-driven analyses, in terms of which FRBs are included, how are they found, what decisions were made during the pre-processing, how did you choose your hypotheses, and so on. And they all seem like they're predetermined, but that's usually because these choices are made implicitly. And so the best thing you can do is predefine your hypothesis and test procedure before you start the analysis. Or what you can also do is ideally separate exploratory data analysis where you go in without a hypothesis and just, see what's in the data. And then if you want to do a hypothesis testing, ideally you do it on a different sample. And I think we're in the lucky position now with FRB that so much more FRB data is coming online that that's actually feasible to do. Okay. I'm gonna finish with my conclusion. I think FRBs are a really exciting area of research, currently really doing a lot of data-driven analysis, which I think is great and really useful. I think it's really important to choose like ideally, very physical hypotheses if you have access to them. If you want to do robust decision making. Knowing the statistical assumptions of your methods is very useful, and if and how your data break them. And your data can break them, but then you have to probably simulate to figure out what effect that has. And then you want to beware of the garden of forking paths and all of the choices that you might make along the way. And I'm going to stop here and ask for questions.
Thank you, Daniela. We have time for two questions, maybe. Yep, up here. Yes, you. Yeah, sorry, I don't know anyone's names. Where's the catch? Oh yeah, Jason can have the honors. Oh my god. Woo! Yeah, if you'd like to start by introducing yourself.
Yes. Hi, Adam Dong from NRAO. I wanted to ask about the timescales that we detect repeaters on can be years, right? And we know with pulsars, you have this period, and then you have period derivative, the spin down, and we think these FRBs are in binary, so you have all the binary, you have all the Keplerian parameters as well. If you have all of those, what are the chances of detecting anything considering look elsewhere effects? And how do we deal?
Great question. I think that's really hard to answer for me without knowing a little bit more, a little bit more of the details of how exactly you would want to do that analysis. I will say, so one thing I didn't really talk about is, a lot of what I was talking about was very frequentist. I actually do a lot more Bayesian inference in practice. And one thing that I will say is that frequentist statistics is very good when you have like large samples and sort of clear hypothesis you want to test. If you think your model is sort of very complex and you want to test that on data, you might be better off moving into some kind of Bayesian model setup. And so maybe that might be a possible answer to then start thinking about Bayesian model comparison questions, especially if you're in a problem where you have, like a Keplerian model with parameters that you can do parameter inference with. So that would be sort of my short answer, but if you want to chat more about it, feel free to reach out over Slack.
Thank you.
Thank you. I see that we have two questions online, but given the time, I was wondering if both of those people could put their questions into the FRB 2025 day one Slack, so that Daniela can reply to those on there. And so with that, I'd like to close the first session of the conference. And if I'd like to invite you all to go and have coffee and Timbits out in the foyer. Oh.
Can you hear me, Daniela? Oh, you can be online. Hey, can you hear?
Hey, Jason. Yes, I can hear you.
Hey, that was a great talk. It was really nice.
Thank
Oh,
you.
you're being called. Great talk.
Thank you. I hope you had good travel.
Yeah. I'm gonna go to coffee, but we'll
Okay.
catch up later.
Yeah, catch up later.
Okay.
Yeah.
not sharing my screen. Can everyone online hear me? Okay, I see a thumbs up. So I'm going to try to talk about some of the bread and butter of radio interferometry, about correlation, calibration, VLBI observations, and how we interpret some of the wavy lines that we see in radio maps of the night sky. So we may not all be here to do radio interferometry, but we are all here to find FRBs. We're here to understand what they are, what the sources of the bursts are, what are the bursts, what are the sources that make them, what are the transient and persistent counterparts at other wavelengths, their host galaxies, afterglows, things like that. We want to use FRBs as probes of the missing baryons, of the matter power spectrum and beyond. And in order to do this, we have realized as a field that we need to detect and pinpoint as many FRBs as possible. And so in this animation, I've shown the night sky. This is our playground, and we really want to mine this night sky for FRBs. So the first reason you should care about VLBI is because it is actually a technique which allows us to mine the sky extremely efficiently. And because I'm a member of CHIME, in this GIF, I've shown a picture of the night sky turning overhead. This is the northern hemisphere sky. You can see right in the middle of that red stripe, which is CHIME's primary beam. The North Pole stays fixed in this projection, and we scan the whole night sky once per day, trying to find FRBs. The reason why VLBI is a really powerful enabling technology is because traditional imaging interferometry makes it really hard to fill a night sky with beams to search for FRBs. So radio interferometry is a technique where you use multiple radio dishes together, not fast, not Arecibo, but something like the DSA 110, like ASCAP, or like CHIME. And you use these small receivers together in order to have a wider field of view to see more sky, to detect more FRBs. CHIME right now is one of the, has probably the largest field of view of any FRB detector. And you can see that it covers only a small part of the sky, something like 200 square degrees, or 1/50th of the night sky that you can see at any given time. However, even a small sliver of sky translates to a very high detection rate, and this is how VLBI enables it. It's a bit indirect. But traditional imaging interferometers make it really hard to fill a night sky with beams. The way you search for FRBs, if you take these two dishes, you take the electric field coming out of these two dishes, and then, hang on. Does this work? Around my neck. Oh, that's much better. Okay. Yeah, it's feeling a little awkward. Yeah, so the way that radio interferometry works is you hook up your dishes, you apply delays to one of your two dishes, and you phase and sum the voltages such that you're sensitive towards one part of the night sky. We call that patch of night sky a beam. I'm going to represent that with a rectangle in this animation. And if I sum the voltages, I can then downsample in time, downsample in frequency, and look for single pulses as a function of time. Since FRBs are occurring all over the night sky, it makes a lot of sense to try to search as much night sky as possible. We don't preferentially detect FRBs in one part of the sky or another, something that Alex just showed. So you want to not make one beam, but make many beams. In this example, I'm going to show just 7. So we're going to tile the sky with beams. Each beam is roughly the size of our point spread function. And in each of these beams, we're going to sum the voltages, square them, and search them for single pulses. Each of these searches involves a trial over dispersion measure. We need to align the time streams at each frequency with different time delays, such that we're sensitive to FRBs coming from different dispersion measures. And if you search over many dispersion measures, many possible FRB widths, and as a function of time, you might eventually, in one of your beams, detect an FRB. When the signal exceeds some certain threshold, you will say this is an FRB candidate. Hopefully it's not radio frequency interference. You'll save it to disk, and then record voltages and move on and keep searching. CHIME does this every day of the year, 24 hours a day, except in the summer when it gets too hot in Montreal or in Penticton. So in this example of a traditional imaging interferometer, these telescopes are designed to have an exquisite PSF, the point spread function, which means that the PSF is really small. This makes it really hard to tile the whole night sky with beams. In contrast, CHIME is not an imaging interferometer. You can take your dishes and put them close together, and what this translates to is that your beams get a lot bigger. And suddenly, with the same amount of compute power, you can cover a lot more night sky at once. And with this strategy, CHIME still leads the field in terms of detection rate with GPUs and computing technology that is now approaching a decade old. Covering more sky means that each beam has much higher chance of seeing an FRB since there's a lot more universe in that direction. However, as we now know, in 2025, detecting an FRB is really just the start of the game. FRB science is quickly becoming a multi-wavelength field. Because once you detect an FRB, the next question is we want to study it and do things like follow it up, obtain redshifts, distance measurements, characterize it at multiple wavelengths. So you've seen some of the benefits of this compact array design, that you can have these big beams to detect lots and lots of FRBs, but now we sort of sacrifice angular resolution and we don't have an easy way to get it back. And what this means is that even within one of your detection beams, it's really hard to associate an FRB with any of the galaxies in this field, even with infinite optical information. So this is where VLBI comes in. It allows you to build these telescopes, these non-imaging interferometers with these funny big PSFs like CHIME. And then you bring in VLBI to get the best of both worlds. No longer is it a question of do I use long baselines or short baselines, but you can have both. And you can sort of decouple this question of how accurate you want your interferometer to be from this question of how sensitive you want it to be. And that's what VLBI allows you to do. This allows us to pinpoint FRBs to host galaxies, obtain distance measurements, study the burst luminosities, study the local environments of these sources. And that's all possible with a combination of sensitivity and angular resolution over a wide field of view. VLBI and astrometry is a rising tide that lifts all boats. VLBI angular resolution allows us to take full advantage of space-based imaging, not limited by seeing from the ground. It allows us to zoom in on scales smaller than the scale of star formation, tens of parsecs in local galaxies. See Mawson's talk later about an exciting new FRB that we pinpointed using CHIME and its VLBI outriggers. It also allows us to get the most out of our surveys. It allows us to make associations between FRBs and faint objects, both the luminous galaxies at high redshift, as well as the nearby low luminosity universe, which has already revealed a massive diversity of FRB formation channels and environments that these sources live in. VLBI has taught us things we would not know in other ways. For instance, as a result of these improved technical capabilities from the astrometric accuracy and precision of VLBI, we now know that not all FRBs have young progenitors. I once clung to a sort of this fairy tale in which all FRBs came from star-forming host galaxies. We now know that some of these are born in globular clusters or offset from star-forming regions, implying delayed formation channels relative to the time of the star formation. We also know from VLBI that a subset of repeating FRB sources are associated with flat spectrum, luminous radio emission, too compact to be star formation, too low luminosity to be AGNs, yet too luminous to be star formation. And that is potentially an important clue in the nature of what these sources are. I think I have more than, I'm a 30-minute talk, right? I'm 30, okay. That scared me for a second, okay. And so sources that are associated with persistent radio emission counterparts include 121102, R1, as well as FRB 2019-0520B, sometimes known as the R1 twin, because it also has a persistent radio source associated with it. We also know that FRBs exist in strange environments, such as in dwarf galaxies as down to 10 to the 8 in stellar mass, as well as massive ellipticals up to 10 to the 11, that's FRB 2024-0209A. And we also know from VLBI and studying and getting the most out of our space-based imaging that for a handful of sources, there are no optical companions down to typical O supergiant and O main sequence star luminosities. These are the two sources I have in mind are FRB 2018-09-16b. This is the periodic repeater, which was studied with the HST after an EVN localization, as well as FRB 2025-03-16a, as Mawson will talk about later. Some of my favorite FRBs are R3, 2018-09-16b. You can remember this is the periodic one because the last two digits of the TNS name are 16b and it's 16-day periodic. I just realized this quite recently. My other favorite VLBI localized FRB is this FRB in M81, which was pinpointed to a globular cluster, also by the EVN team. Just a handful of these sources have already told us a wealth of information about VLBI. I think these are some of the first VLBI discovered single sources that are notable, including some of our favorites here. And in the right here, I've shown the recently localized FRB 2025-03-16a, also pinpointed to an H2 region, but with a slight offset as we saw in the 16-day periodic source. So there are just a few gems for now. Each of these has taught us a lot about the FRB phenomenon, and there's lots more to come. The EVN is not the only game in the room. Chime FRB Outriggers is online, doing well, pumping out FRBs. I think I've plotted for the first time the number of VLBI localizations as a function of time, and finally we're seeing sort of an uptick in this, enabled by the capability of doing VLBI on single pulses, something I worked on as a PhD student. Chime FRB Outriggers is doing really well. I will defer further talk of that array to Matthias and Ziggy later. But this is just the beginning for VLBI and FRBs because a slew of new instruments is coming online, going to use compact arrays and VLBI in order to pinpoint these sources, understand their origins, not in hundreds or thousands, but at the scale of 10,000 or more. And these are chord, burst, and other future efforts, such as charts in the Southern Hemisphere. So now I hope I've motivated why angular resolution is important, why I think VLBI is going to be the future of our field. I think the existence of chord, burst, charts sort of point to the final FRB experiment, which is compact arrays, VLBI for angular resolution, and the field is sort of converging on this design, meaning VLBI is going to be really important. So let's talk about it a little bit more. Now I want to spend the remainder of my talk sort of going into detail about how VLBI works. At its core, VLBI is a question about correlation. How do you line up the crests and troughs of your electric field signal entering your radio dishes? In this schematic, I've depicted radio waves in red going into my dishes. And if I correlate these waves as a function of time, then what I see is that the radio waves are positively correlated. If there's no delay, then the phase should be, these waves are aligned in phase. And what I mean is that if I multiply the top curve by the bottom curve and I sum over time, I get a positive number. However, if I look at a different part of the sky, I get a different number because of the different geometric delay towards my source. In this case, the waves are anti-aligned, and you can see that if I multiply them together and sum them as a function of time, I get a negative number. Sometimes it's a little hard to interpret when your signal can be positive or negative. So something that we like to do in radio interferometry is break up the electric field signal as a function of time. It's really convenient to do this to make our data volumes more manageable. So you don't need to correlate this entire the top wave against the bottom wave for all time. You just do it chunk by chunk, and this allows you to parallelize things nicely. And in this example, each chunk is anti-correlated with the bottom chunk. You get negative correlations for each of these three chunks. Then you can aggregate together these integrations or sub-integrations into a measurement of the visibility or the correlation between the top antenna and the bottom antenna. You get a negative number. That's okay. It's an overall phase offset. So this is what's happening for a source at the North Pole. Let's consider now what happens when we go off axis a bit. Let's say the North Pole is a special place in the sky because it's fixed as a function of time. If I have two antennas in the northern hemisphere, they can always see the North Pole, and the North Pole doesn't change in the Earth's frame. So the delays towards the North Pole are static as a function of time. So if I have two identical antennas, I get positive correlations in all three segments, all three of my sub-integrations. I sum them together, I get a positive correlation. However, The story gets a little more complicated for sources not at the North Pole. You can think of now a source at the horizon. There's going to be a different delay towards each of my antennas. And what's going to happen is that the waves are going to be shifted slightly as a function of time and where your antennas are. In this example, the waves on the left remain correlated, the ones in the middle are not really correlated at all, and the ones on the right are anti-correlated. And the problem is if I stack these measurements, I get something that's 0. It's sort of obvious that I've misaligned these waves as a function of time. I've also colored some of them differently. And what this refers to is the fact that there's actually a net radial velocity for sources off from the phase center here, the North Pole. In other words, since my Earth is rotating, if I see a spectral line at the horizon, I will see it at a slightly different redshift or blue shift in my front antenna versus my back antenna because Earth is rotating. Now, this is a problem because if we just sum the waves, we would get no sensitivity. We would not get a signal, even if the source were extremely bright. To fix this problem is a well-studied thing in radio interferometry. This is the job of a piece of software or a piece of hardware that we call the correlator. It breaks the data into chunks, and it figures out how big the chunks are. And then you tell the correlator what position you want to be sensitive to, and it calculates the delays towards that position using a highly accurate and precise delay model. It aligns the waves not just by changing their position as a function of time, but also applying a Doppler shift, a red shift or a blue shift to each segment individually, such that they are the same color again towards that phase center. That correlator then tells you, okay, I've maximized my sensitivity towards this point in the sky. Now I'm going to repeat the correlation process. I'm going to multiply the two waves together as a function of time, sum, and then I get my signal back, even for sources not at the North Pole, sources that are potentially rotating in the sky that are not static as a function of time. There's a couple of codes used for VLBI correlation. Probably the most well-known is diffx, written by Adam Deller, who I know is on the call. There's also SFXC, written by Ard Kempema at Astron. LOFAR uses something else, and because of the time, we wrote our own piece of code. I wrote this piece of code along with Shio and Andrew. We call this PyFX, and we have now used that piece of code. It's all written in Python to localize hundreds of FRBs using VLBI. So now that we've talked about VLBI correlation, I want to now talk briefly about what happens afterwards. There's also calibration required. Your antennas are not all designed the same. They have different cable lengths, different delays and phases. So at bare minimum, you need to do delay calibration, you need to do phase calibration and ionosphere corrections. How you solve for these parameters? You need a bright network of compact sources in the sky, which have well-defined positions for you to do VLBI. Fortunately for us, the folks at the VLBA are really good at doing this. There is now a radio fundamental catalog of over 20,000 sources over the whole night sky. Maybe 1 every 2 square degrees, with positions at 1.5, 3, 5, and 8 gigahertz. Leonid Petrov is putting out a new catalog every couple of months, and so if you have an old version of the VLBA calibrator catalog, you should reload it every now and then. A subset of these 20,000 sources actually define what it means to have certain RA and DEC coordinates. A different subset of these sources also have optical counterparts, and those let us tie the radio frame, which define the RA and DEC coordinate system, to Gaia. And so what this means is that in the optical wavelengths, with a couple of calibration stars from Gaia, you can use this connection to the ICRF in order to achieve a local frame tie that's on the order of 10 milliarcseconds or better in many cases using that the Gaia astrometry. So this is what happens at 1.5 gigahertz and above. At lower frequencies, the story is a little more complicated because it's just not as well studied in terms of VLBI. There's not a lot of papers on this. Some of the early ones are by Clark, 1975. Also some observations with radio Astron, and also Emil Lenk surveying the sky at low frequencies. This field sort of hit a wall in 2009. Most data from the VLBA at 92 centimeters, I actually learned is completely public, but unpublished because it's just so hard to observe there. And so what we've had to do in order to look at FRBs with VLBI with Chime is to make our own calibrator catalog. There's no low frequency catalog which existed for doing astrometric VLBI at the frequencies that are most interesting for FRBs. And I define this to be roughly a gigahertz, maybe a bit lower, going all the way down to 300, 400 megahertz. Existing surveys from LOFAR were either too low resolution or they did not have an astrometric tie. And so it took Chime outriggers coming online to really fill in the gap in terms of calibrator coverage as I've shown in this plot on the right, where I have angular resolution or longest baseline on the x-axis and frequency on the y-axis. So time outriggers fills an important part of that parameter space. And we're hoping that time outriggers will also pave the way for the next generation of FRB detection experiments by providing a low frequency all-sky survey of calibrators with astrometric availability, so that regardless of where you detect your FRBs, you will be able to find a calibrator and reference that FRB to the ICRF. So I mentioned earlier that once you have a calibrator, you want to perform calibration. There's a couple of steps: delay, phase, ionosphere calibration. The big one is delay calibration. You typically use the brightest sources in the sky for this, bright and compact, and hopefully with well-determined or defining positions in the ICRF. Delays mean that your waves are not aligned as a function of frequency. You can bring those back into alignment. And after delay calibration, you're typically okay for astrometry unless you want to image. If you want to image, you also have to take care of an overall phase between your two antennas. That's sort of a small effect I've shown on the right. I plotted in the top panel an image, a 1D image of the sky with flux on the y-axis and delay or sky angle on the x-axis. And in the bottom, I'm plotted the overall phase. You can see that applying a small phase shift makes a very small difference to the PSF, but it does subtly change the position and the relative intensities of the side lobes, which is really important for imaging. After delay and phase calibration, we sometimes have to do ionospheric calibration. What I've learned in VLBI is we don't really talk about the ionosphere that much, but it actually turns out it's really important at low frequencies. And the reason is that at low frequencies, there's not only a geometric delay, but there's also an ionospheric delay, which due to the presence of electrons gives you a lambda square delay. It's pretty hard to tell what the difference is in the phases as a function of frequency if I have a narrow bandwidth. What's nice about CHIME and about future FRB experiments is that with a wide fractional bandwidth, it's possible to simultaneously fit for your 1 over frequency as well as your proportional to frequency delays here. Oh, right, I'll let this play again because I think it's a cool animation. So here's the thing. There's a source moving around. I want you to see what happens to the phase as a function of frequency. It's sort of linear. You can't really distinguish that quadratic part of the phase. But when I uncover the full bandwidth that we have, we can sort of see by eye exactly how much ionosphere is present. So here again, there's a source changing position in the sky. There's also an ionosphere correction. If you're not working at low frequencies, if you're working at L band or above, typically what you do is you apply a ionospheric model, which is measured with GPS. However, this only takes into account fluctuations of the ionosphere on large scales, not small traveling ionospheric disturbances, which are better to self-calibrate out using observations of nearby calibrators. So now we've talked about correlation, calibration, why we should care. Let's actually do some VLBI. For an example, here is a target on the sky, a phase center, hopefully close to the target. We mentioned earlier that if you are too far away from the phase center, you lose sensitivity. So in practice, you want to be as close as possible to the phase center before you start your VLBI session. This means having a preliminary localization of your FRB or some archival position that you point at. Arc minutes is good. More than that, degrees, that's worse. Radio telescopes are diffraction limited, so I won't show you what the true sky is. I'll show you what the radio telescope sees, which is a blob of size lambda over d. And I mentioned previously that this gives you constructive interference. If you move off axis, it gives you destructive interference when your waves are off by 180 degrees in phase. If you keep going off to the side, then you get positive correlations, constructive interference yet again. This happens on the other side of the sky as well. And this oscillatory pattern, the interferometer response, looks like a sine wave across the sky. And in principle, this sine wave goes off to infinity. However, in practice, this is limited not just by the correlator field of view, but also a contribution from the primary beam if you go way off to the sides. Typically, your correlator field of view is smaller than your dishes for a well-designed telescope, giving you some total sensitivity. So you want to make sure you're pointing approximately correctly, and you also want to make sure that your correlator is pointing close to where you think your target is going to be. And so to close out this talk, I want to now observe a source and sort of lay the foundation for the rest of this conference. We'll talk about FRB observations. Let's talk about observing a point source versus an extended source. For instance, a point source might be an FRB, or it might be one of these compact persistent radio sources. An extended source might be star formation in its host galaxy. And so what I do to see what my interferometer will see is I put on the interferometer response. I overlay it on top of my source function, which is a positive function over the whole sky. And I now integrate over the whole sky, or in practice, over the size of my primary beam. I see positive contributions and negative contribution. These two functions get multiplied together. And since the source is positive, it is in a positive part of my interferometer response, I get a positive contribution to the visibility on short baselines from that source. The same thing happens on long baselines. There's a different Fourier mode, a more oscillatory one that goes across the sky. And because my point source fits in one of these positive lobes, it gives me a positive contribution. For more extended emission, we need to go to shorter baselines. And so at short baselines, you can sort of well match the interferometer response to the size of the object you want to study. You get positive and negative contributions summed across the whole sky. The cloud here will give you a positive contribution. However, one subtlety in radio wavelengths that I want to stress is that if you use long baselines to observe extended emission, you actually don't see it at all, because there are positive and negative contributions from the interferometer response when superimposed on top of the source that you're looking at. Another way of saying this same thing is as follows. Here I plotted the true flux as a function of sky position. What the interferometer sees if you have many long baselines looks a little more like this, where the contribution from the extended emission is suppressed. If you have fewer long baselines, just one or two baselines, then what you see is something a little more oscillatory. Oh, by the way, that's the beam shape, or the PSF. And the beam shape gets a little more oscillatory if you have worse UV coverage, worse frequency coverage, or both. We see this in the literature. Here is an image of, I think, the persistent radio source from 121102. You can see the beam shape specified in the lower right corner. And you can see that, as predicted, the flux goes negative in some places, which is sort of weird in radio. Doesn't happen to other wavelengths. But it's really just a result of the PSF being oscillatory as a function of position on the sky. Right now, the field is also building towards this regime where you have oscillatory fringe patterns. Here are two examples where that's relevant. Tomas and I and Pranav localized this, the very first VLBI localized non-repeating FRB. This paper was finally published in 2024. You see an oscillatory fringe pattern as a function of RE and DEC. There's just two baselines here. Also, we see the same thing happening in Dante's paper, Hewitt in 2025, where the localization ellipses increase in size from something like milliarc seconds to hundreds of milliarc seconds or tens. Turns out this is good enough for most FRB purposes. And so at that point, I'll just say that we sort of made it both to the end of this talk and in terms of realizing the dream of FRB VLBI over the whole sky for FRBs. VLBI, in conclusion, it lifts all boats. It enables us to use design better FRB telescopes optimized for FRB detection, freeing us from the constraints of localization, allows us to do space-based follow-up. It opens up the possibility of diverse environment studies and allows us to characterize multi-wavelength companions to FRBs. And before I go, I just want to say that Chime FRB Outriggers is hopefully the first of many telescopes which will use VLBI to localize these sources. And I just want to give a shout out to some of my colleagues who will be giving more extended talks on Chime and this Outrigger program. I want to end with a picture of my new kitten. Thank you.
Thank you very much for that nice talk, Dr. Calvin. It's, I mean, like a lot of things, gives a good introduction for all newcomers. All right, so question. Yeah.
Oh. I'm kind of constrained here, so I'm not gonna even try to throw it.
Thanks. My question is very, very basic. So you said that you hope that Chime will provide like a catalog of calibrators for low frequencies, which hasn't been done before, but obviously Chime can't see the whole sky. So I was wondering if you knew if there was any plans to, by any facility, maybe someone else knows the answer to this, to have a Southern Hemisphere equivalent.
Yeah, it's a great question. I guess the question is, I feel like the Australians probably have a better answer to this than myself. The VLBA calibrator catalog seems to be working in the Northern Hemisphere. There's no reason why it shouldn't work in the South as well, although the source density is a bit lower there. So I suspect if you build something like charts and observe in the South, you'll just see the calibrator.
Great, thanks.
I should also mention that we actually have published one of these calibrator catalogs already. This is shown paper.
Liam, go ahead.
Hey, Calvin, that was a great talk. I loved all the visualization. Okay, so with long wavelength VLBI and just a few baselines, you don't quite get to the diffraction limit because the ionosphere, lack of UV coverage, calibration, other systematics, seems like you get to about 100 milliarcseconds, which is obviously incredible, but for an array like ASCAP or DSA-110 or the Chime core, you go significantly below the diffraction limit by a factor of about the signal to noise. So DSA-2000, for example, will have a 2 or 3 arcsecond PSF, and it'll get to 100 milliarcseconds localization for a 20 sigma burst. So my question for you is, how do we optimize this trade-off for future arrays? Is there a middle ground we should be considering where you don't actually need the international VLBI networks? Or am I missing something and actually Chord and Chime VLBI really have landed at like a global minimum?
Yeah, it's a great question. The question of how much you super resolve your PSF is sort of thorny, as not always clear how much that happens as a function of signal to noise on different baselines. Right now, what we do in Chime outriggers, which is sort of panned out, is that we're not super resolving the PSF. We are inflating the localization ellipses relative to diffraction by a factor of 2 or 3, although it depends on things like the noise and wavelength coverage. What I will say is that that's actually the correct choice, not because of ionosphere considerations, but because we see RFI substantially increases the scatter in our pulsar localizations and continuum source localizations as a function, RFI scatters the overall positions more than ionosphere does. And so that's why we do what we do. So I think this is sort of the right way to go to completely decouple the design of the core stations from long baseline stations. I hope that answered your question. Okay.
Right. So let's thank the speaker again. Our next speaker is Dr. Robert May from McGill University, and he will be showing us some really interesting slides on propagation effects in FRBs. Yeah.
Yeah, just a second. I'll need to bring up my slides. Where are they? They were on the back. Yeah, well, they're on the Chrome window. This week. Oh. Oh, yeah. That's that. Oh, and then I'm not yet sharing screen. Let me. Okay, should be good. No, is there? There's a problem when it's not mirroring. Yeah, is there no way to see it on here as well? I don't. We need to change the mirror. Give us a second. You change the mirroring. Huh? Is it? There it goes. Probably not. We should be good to go. I think this should be good to go. Yeah, I'm hoping if people can hear me in the back, can I get a thumbs up, thumbs down? I'm hoping I can just project my voice. Great. And fair enough. So I should use the mic. I just wasn't sure about the, okay. Fair enough. I'll use the mic then. Okay, you can all hear me. So yeah, just a second here. Thanks for thanks for coming here and for waiting a second while we figured out the transition between softwares. I get the very fun task today about talking a little bit about the basics of propagation effects and both how they manifest, why they manifest, and what we can learn about FRBs by studying them. So yeah, and my name's Robert Main. I'm a research associate here. And so here's a little, to start, here's a picture of an FRB. You know, the FRB is located in its host galaxy, in its local environment. And what happens to it as it passes between its emission site and our telescope, which is in the Milky Way. On the way, it passes through the intergalactic medium. So all of this space contains plasma, cold plasma, in this case, cold meaning non-relativistic. This will cause dispersion, as I'll show, which is magnetized, and this will affect the polarization, in particular through Faraday rotation. And this cold plasma is inhomogeneous, which will result in scattering and scintillation, as I'll show. So just a bit of a backing, why do we see any such effects on a radio signal? Well, the index of refraction in a cold plasma is slightly less than 1. So this here, index of refraction, I have as mu, and this is the difference from 1. This first term is the plasma frequency over the observing frequency. The plasma frequency depends on the electron density. So this will give you a frequency-dependent group delay as you travel through this plasma, which depends on the electron density over the observing frequency squared. And this value is much, much less than 1 typically. You see it's 8.5 kilohertz if you have plasma densities of about 1 particle per centimeters cubed. And we'll see soon that in any typical astrophysical place, in particular in Milky Way or the IGM, the values are much less than that. So the second term I have with a plus or minus. This is a frequency-dependent group delay between polarization states, or between the left and right circular polarization. This value is, again, much, much less than 1. And this will result in a slight phase delay between polarization states that we will see. And then, of course, I started by introducing the index of refraction. That will immediately tip people off to the idea that, oh, light will be able to bend. So any spatial gradients or any differences in the plasma density will result in the bending of light, and that'll result in scattering and scintillation. So, all right, let's go through these. Let's go through these one at a time. So dispersion is related to that first term, and we can characterize it with the dispersion measure, and it's the total integral of the electrons along our line of sight. So this is the total column density of electrons. It's a catch-all. It's additive for all of the plasma you encounter. And that means that when you measure the time delay, which will have this frequency to the -2 dependence, we measure the total column density between the burst and us. So here's a simulated burst. I put it in. We have it here. It's emitting at the source at the exact same time across frequency. So applying a dispersion measure, we get this characteristic, well-understood sweep. And if you measure exactly what the sweep is, you have measure the dispersion measure. So now I've added some magnetic field lines. I mentioned the plasma is magnetized. This results in the second term I talked about, which is a slight delay between the left and right circular polarizations. This manifests as a phase beta, which I have written as beta. It's measured in radians per meter squared. So already you have an idea. If you measure the wavelength of your light, or you know the wavelength of your light, you have your rotation measure. This will tell you how much it'll rotate between the polarization states as a function of wavelength. So again, this is the same burst, and applying a rotation, looking at the polarization states. So now we have Q and U. So these are the two linear polarization states. You can see the oscillation between positive and negative, and you can see that they're out of phase. So here's an animation for how that can look. So this is right there, you see that's when you have the correct rotation, but you're gonna see if you scroll through different rotation measures, you can see the oscillation becomes faster. And then when you have the exact right rotation measure, everything is derotated, the phase is aligned with 0, and all of the power, which is in the bottom right, is able to sum up, and you'll recover your true peak. So I'll just let that play again. It's going to scroll past the peak, and now it's going to go back. All right, so that's the effects of Faraday rotation. So the one other effect I mentioned, now I've added some squiggly lines to the plasma density because it's inhomogeneous, and that'll cause the bending of light. So this bending, the total bending angle you can get depends on the change in the column density over delta X, so over some spatial scale. So the smaller your spatial scale, the smaller your plasma fluctuations, the larger the bending angle of light. And this results in a path length difference. And this results in a time delay as it takes light a longer time to reach us, just simply due to geometric delays. The bending angle, since it's related to dm, it also has a frequency to the -2 dependence. And then the time delay is related to the angle squared. So you get a much steeper dependence of this scattering time delay with frequency, typically something like frequency to the -4. So now the burst, which was very narrow originally, what you'll often see is something like this, where the different scattered paths of light, if you have many such scattered paths, this will form a characteristic tail. Each of these will arrive at a later time, and it'll broaden your signal. And this is the fun part, or this is, to many, this is one fun part of this, is that FRBs appear to be point sources. And so each of these copies is the same electric field, but slightly delayed. And exactly as Calvin was just explaining with VLBI, you have the same electric field, they're delayed in time, they will interfere. So this is referred to as scintillation, and that gives you this interference pattern that you see as a function of frequency. So I wrote delta F. In this case, I mean the scale of the scintillation pattern is inversely proportional to the time delay. So the larger path, the more delayed paths will give you finer fringing in frequency. Okay, so yes, this is a GIF. Instead of showing the two screens as I have above, just looking at the simple case where you have the observer, and we're looking at these different scattered paths. The top right is a dynamic spectrum of a burst as you get more and more scattered paths, and you can see the fringing get finer and finer. I'll let that play one more time. And the bottom right are the image positions as we would measure them on a telescope if we could resolve the images. All right, so that's in quick strokes how you can understand the scintillation pattern. So to put some rough physical values, so I mentioned these various effects that manifest in effectively any faster radio burst you'll see. We have our dispersion measure related to the total column, the rotation measure, which is the total column density weighted by the magnetic field, and of course the bending angle, which has to do with the change in the column density over space. The IGM is very tenuous and hot. This will add to the dispersion measure because there's such a large space. However, the rotation measure is weighted by the magnetic field, and as well as the bending angle is weighted by your coldest, your densest, clumpiest plasma. And these will be strongly weighted into host galaxies or regions of higher electron density. Okay, so just a quick summary before we get into what we learned from these. So fast radio bursts pass through cold plasma, which is magnetized and inhomogeneous, resulting in, for any typical FRB, usually this array of propagation effects that you see. Okay, so what do we learn from this? So the rest of the talk, I'll give a little bit of a flavor of what these effects learn, what they've taught us about FRBs in the field. It's a non-exhaustive list, but you'll hear plenty about that in the rest of the conference. The hope is that this gives a little a bedrock and a bit of a flavor about what you can learn. So starting with dispersion measure, that's largely why the field kicked off. That's largely why we're here. That let us know that fast radio bursts are extragalactic. So this is the first discovered fast radio burst, the Lorimer burst from 2007. And you see this dispersive sweep. You can measure that very precisely. You can measure a dispersion measure of 375 parsecs per centimeters cubed. And we can say, well, along this line of sight, we know pretty well the plasma density or the plasma column in our own galaxy, and it should be nowhere near this value. So to have encountered this much free plasma, it must be out of our own galaxy. And so that was already remarkable. So how do we know this? And this is one of the main uses of dispersion measure. To start, let's say, what do we already know from pulsars? So we have thousands of known pulsars that are distributed throughout the Milky Way. Again, the dispersion measure is the total column density of plasma, typically measured in parsecs per centimeters cubed. So very roughly, if you know the plasma density in centimeters cubed, you can divide that and you can get the distance. So a dm plus the electron density tells you the distance. Conversely, if you measure the distance to many known calibrators, in this case pulsars, and so you know the distance, you know the dm, each one of them tells you the plasma density along a specific line of sight. And through many known pulsars with measured distances, you create a three-dimensional map of the plasma in our galaxy. And you can see here, that's what's plotted on the bottom. This is from the NE 2001 galactic plasma model. This is an edge-on view, so it's in galactic coordinates. And you see, far away from the plane, there's very little contribution. So these contours are at 50 and 300, I think. So if you're far off of the plane, you expect a very little dispersion measure, a very small contribution to the dispersion measure. So using that idea, you can replace the word pulsar with fast radio bursts. And now instead of being populated throughout our galaxy, they're populated throughout the universe. So using this idea, you can map the universe's baryon content. And there's a whole block on this, and there's another talk today. But using this, you can probe the baryonic content of our universe, and you can use FRBs as a cosmological probe. So then the dispersion measure relation there gets factors of redshift and includes cosmological parameters. This relation here at the bottom is now referred to as the McCart relation. And that's what it's showing. It's showing the dm as a function of the redshift for several localized fast radio bursts. And the black line there was the prediction from the cosmic microwave background measurements. And they generally agreed, which was showing that using FRBs as a probe, you can actually see the majority of the baryonic content of our universe, and it's matching the predictions that we have from cosmology. And as we get many more FRBs with measured redshifts, you could actually create a three-dimensional map of the intergalactic medium, similar to what we've already done with pulsars. So this is again one of the main driving factors, and this is why we want to localize many FRBs to many host galaxies. Okay, so then what do we learn from rotation measure? So one of the main things that it tells us is it's helped reveal that FRBs, or at least some FRBs, are in very special environments. So again, the rotation measure integral looks very similar to the dispersion measure, except it's weighted by this magnetic field. So if you know the dm and the rm occur in the same region, you can simply relate them. And in the typical units that we measure them, rm in radians per meter squared, dm in parsecs per centimeters cubed, you can take the ratio of the two, and it basically tells you the magnetic field in microgauss. So in the slide above, the Milky Way, a typical value is about a microgauss in the ISM. In the intergalactic medium, it's much less than that. So in this bottom case, this is the first repeating FRB. And when the rotation measure was measured, it was tremendously high. It was about 10 to the 5 radians per meter squared. The DM budget, the amount of material or the amount of plasma that could be in the host is something like 100 units, perhaps a bit more or less, but not orders of magnitude. And this suggested that the source had to be already in a fairly special environment. The magnetic field had to be at least about 1 milligauss, far more than you expect in typical ISM. And this already suggested, along with the persistent radio source next to it, that perhaps it's in a young, dense supernova remnant or a highly magnetized magnetar wind nebula, or in our own galaxy, we've seen high rotation measures like this near our central black hole. So, right, so what do we learn from scattering and scintillation? In broad strokes, I would say that it gives us a window into the smallest scales. So again, the bending angle that we see, it's weighted by the spatial scale. So the more tightly you can pack your plasma, the wider your bending angles are. And in the case of pulsars, we've been able to map we're able to see the actual substructures that, or infer the substructures that bend light to cause the scintillation that we observe. And these are sub-AU scales, so almost planetary scales of plasma. And similarly, that's just from scattering, but for a source to scintillate, it must be point-like. So for the exact same reason that Calvin explained, an extended source becomes washed out with VLBI. If you have an extended source, it'll wash out this interference pattern because each of them will have effectively a different diffraction pattern that'll superimpose and destructively interfere or average out. And what do I mean when a source must be point-like? Again, it's perfectly analogous. We have the exact same electric field from multiple deflected paths, and the interference between them is just like a 2-slit or n-slit experiment or an endpoint interferometer. The spatial scale will be lambda over L, and in this case, L can be AUs or tens of AU. And the analogous statement is always stars twinkle and planets don't. Or you could say FRBs scintillate and radio galaxies don't. And again, I'll briefly touch on this if I have time. You can use scintillation and scattering to localize our plasma structures, either through the interplay between multiple screens or directly through VLBI or by using the time axis. So here's a little animation showing how scintillation constrains source size. So I've put in an image on the right and I've made it gradually get bigger. And I'm passing it through the exact same scattering screen. And so on the left is its spectrum, and you see these bright peaks and troughs. That's due to interference. That's the scintillation pattern. And as it gets larger than the resolution of the screen, lambda over D, that's what I have denoted as this orange circle. You see that the scintillations are dampened. So by measuring the degree to which a source is modulated, you can either constrain the source size, or potentially, if you're ambitious and brave enough to interpret your data, you might be able to even measure it. And using this exact same idea, many of you have encountered this, this idea where you can use the presence of multiple scattering screens and using the 2-screen constraint to constrain or localize where the scattering occurs or where the plasma fluctuations are. This uses the exact same idea that a source must be point-like to scintillate. But now, because you have 2 screens, you have a scattering tail. That means that's an extended source. And then that scattering tail is fully scintillated by a second screen. Both screens must be point-like to each other. So that broadened scattered image must still be point-like to the second screen. And what that means is that you have to put the 2 screens sufficiently far away from each other that they still follow this point-like constraint. And that gives you a constraint on typically a constraint on the product of the 2 distances. This is just a characteristic value. And then knowing the plasma distribution in our own galaxy, say we know that the scattering is probably somewhere within about a kiloparsec in our own galaxy, we constrain that the scattering has to be within the host. And in some cases, we can get much tighter constraints. And we'll hear about that later this week in some of the science talks. So how am I doing for time? I think 5 minutes or so. Anyways,
Yeah, you have to.
okay. So, right, so I was talking about all of these effects in isolation, but of course it's all the same plasma. These effects are intertwined. And sometimes through the combination of them results in other measurables. So one of these is the fact that the same plasma that's scattering light, the different paths that the light has to take don't have to encounter the exact same plasma. They don't need to have the same dispersion, and they don't have to have the same rotation measure. And necessarily they must be slightly different. If they're sufficiently different, then your main burst that you're measuring is sampling many different paths, each encountering different magnetic fields and different plasma densities. Each of those will have a different rotation measure, and then the phase oscillations won't be aligned. And similarly, you'll effectively average over many different oscillations, and your polarization signal will disappear. So that's what I've shown here. This is in the bottom left. These are many images sort of isotropically distributed on the sky. I've put a rotation measure gradient across it. And on the right, I've plotted the polarized spectrum. And you can see at high frequencies, where scattering is not so prevalent, you have a fully polarized signal. And it very steeply depolarizes as a function of frequency. And the different lines are just different models that you can use to try and predict how that depolarization should occur. All right, in the remaining few minutes I have, so all of this could apply to a single fast radio burst that you observe. But this, we know that some fast radio bursts repeat. And of course, that's part of the drive of this conference. It's the 10-year anniversary of the first known repeating FRB. What happens if you use the time axis? What happens if you set the FRB in motion? So for one, scattering and rotation measure, these can change with time, and these can change quite drastically with time. One great example where you see all of these effects is FRB2019-0520B. So in the bottom left, you see a very clear scattering tail of about 8 milliseconds. A few minutes later, the scattering tail is gone. So for it to change that rapidly, the source must be seeing a very different environment over a very small time scale. So that suggests that the inhomogeneous plasma causing this must be extremely close to the source. And I think physically it must be less than a parsec, perhaps much, much less than a parsec away from the source. And similarly, the rotation measure was both very large, implying a high magnetic field, but changed sign, which again is difficult in your standard interstellar medium. And one of the possibilities is that this is the magnetized wind from a binary companion. Oh, and similarly in the bottom right, you see the polarization fraction as a function of frequency. It's depolarizing due to the interplay between variable rotation measure as a function of the viewing angle as seen through scattering. And the last effect I wanted to show is, let's put scintillation in motion. And it's fun to give this after Calvin's talk because this is again exactly analogous to VLBI. So I showed how time delays manifest in this interference pattern or fringing as a function of frequency. But each of these scattered paths samples a different velocity vector, either of the FRB or of the Earth. And that gives you a relative Doppler shift that actually causes your light to go in and out of phase as a function of time. And so I'll show the exact same animation, but now instead of the burst spectrum, this is how the spectrum of the burst would change as a function of time. And the bottom right shows the Doppler shift and the geometric time delay of each of these images that I'm setting. And you see that it's going to play again. You see that this pattern in time becomes finer as the longer paths are introduced. So this spatial scale, or this time scale of the interference, it's related to these Doppler shifts, and that directly measures the velocity weighted by the distance of your scattering material. So if you can measure this, you actually have a way to probe the dynamics of your source. And this isn't just in simulations. I wanted to point out that you can actually do this for an FRB. So this is well studied for pulsars. It's the whole field called scintillometry, which is the idea to make precision measurements of the ISM and of your source dynamics by using scintillation. But we've actually measured scintillation arcs in highly active repeating FRBs. And this is one such study using the FAST telescope by Ziwei Wu and others. And this is a scintillation arc for 2022-09-12A. The scattering is very likely in the Milky Way. So we're probing the Earth's velocity. I guess this is another proof that the Earth goes around the sun. But if you're able to do the same using a scintillation pattern from the host galaxy, you directly probe the FRB's motion. And you might even be able to show, for instance, a binary motion, or at the very least constrain its transverse velocity. So yeah, that's a quick overview, hopefully a good bedrock for what we're going to hear in the coming week, of the different ways that radio light is affected between the source and us. And on that, I'll leave it on my final slide, and thank you.
Like 5 minutes earlier.
Well, gives time for questions.
Yeah, it does. Yeah.
All right, so questions. Oh, awesome.
Yeah, so you had this slide, or sorry, I'm Mawson, for the people that are online. So you had this slide that basically showed the differential rotation measure as a function of the, so you had this, right, well,
I'll repeat it.
Doing about that. Yeah, right, so you had this, I think it was on slide 19 or 20, the differential rotation measure as a function of viewing angle. Is part of this effect due to the Doppler delay that you have for a source that's in motion?
Yeah, so Mawson asked, so I have this plot and it shows that the rotation measure changes as a function of the scattering angle. And he asked if this is related to the Doppler shift that I showed later, which gives you the time scale of scintillation. Short answer, the depolarization, no. The depolarization comes from the fact that you're averaging over all of these angles at a given time in your scattering tail. That said, if you could plot this in a delay Doppler map, you would see that the ones that are positively Doppler shifted would have an RM in one direction and vice versa. And I think there's actually a talk later this week that tries to put all of these constraints together.
Yeah.
But so short answer, the depolarization doesn't come from the Doppler shift, but you could see this effect. You could see the same gradient as a function of the Doppler delay, if you could decompose it that way.
And so the reason that I ask that is that we often, I suppose, have this degeneracy of that some of our constraints are, it's difficult to know whether they apply if a screen is one-dimensional. But it seems that if a screen is one-dimensional and the source motion is orthogonal to the dimension of that screen, that then some of these effects like RM would disappear. And so in the circumstance where you have those observables, you might be afforded the capability to distinguish between things that we thought were degenerate.
Yeah, that's right. It definitely breaks the degeneracy. There is still an angle there between your RM gradient and your velocity axis.
Yep.
But a 1D screen does look different than a 2D screen and how it depolarizes. So, oh, I guess I didn't repeat the question. Mawson was asking if you could break the degeneracy between, I guess, the axis of motion and the RM gradient, and if that could tell you about the geometry of our scattering screen.
This is an online question from Aniket Prasad. How would the scintillation pattern be different from the Milky Way and the host galaxy?
That's a great question. So yeah, so how would the scintillation be different between the Milky Way and the host galaxy? So in some ways they're symmetric. So for the same time delay will create the same interference as a function of frequency. If you can measure how the scintillation changes in time, they're sensitive to different velocities. So the scintillation in our Milky Way is sensitive to the velocity between the Earth and the plasma. The scintillation in the host galaxy would be dominated by the velocity between the source, the FRB, and its plasma. So they're probing different physical velocities. Similarly, which source has to be point source-like is different. So if the scintillation happens in our host galaxy, it has very little resolution, so to speak, at the FRB. Whereas if the scintillation is occurring in the host galaxy, then the FRB must be point-like, and that's where the constraints on the source size come from. So in some ways they're symmetric, but not others. Also, if the scintillation occurs in our Milky Way, it might just be, in some cases, the scattering can be milliarc seconds or tens of milliarc seconds. So you could actually resolve it with VLBI. So you could break this degeneracy using, for instance, chime outriggers or even other existing VLBI networks.
I guess we'll continue discussions over Slack because we are, all right, so let's thank Rob again. Our next speaker is Navin Sridhar. He will be talking about the emission physics in compact optics and FRB. So yeah. Navin is a postdoc at Stanford right now, and previously was with Brian Metzger at Columbia. Yeah.
Great. Thank you for inviting me to have this and have me talk about the emission mechanisms. All right, I'll quickly jump into the challenges that we face as the community. So FRBs are some of the largest amplitude electromagnetic waves that we know of, and that can be defined by this strength parameter A, and it's just the ratio of here you have the amplitude of the electric field of the wave, and ME is the mass of the electrons, omega is the frequency of the FRB, and it's extremely large, 10 to the 5 at a radius of about 10 to the 8 centimeters for 10 to the 42 Earth per second FRB. And some of the most powerful lasers on Earth can get to the strength parameter value A of about few or even 10 max. This means that the electrons' oscillations are so relativistic that the Lorentz factor that they experience is comparable to the electric force. And the second challenge is the brightness temperatures, which can be obtained from the Rayleigh-Jeans law. Over here, and for FRBs, this happens to be about 10 to the 36 Kelvin. If an ensemble of incoherently emitting particles has some temperature T, then the brightness temperature cannot exceed that. So this puts a strong constraint on the emission mechanism that it has to be a coherent emission mechanism involving large number of particles emitting radio wavelengths in a phase. And how many particles do we need? And yeah, so that's the number of particles that you need. It's about 10 to the 26, assuming that these are electrons that are emitting. And the immediate question is, how are you going to get all these particles work in cohesion to produce FRBs? There are a few ways. And there are multiple flavors of models based on these ways to produce coherent radio emission. I will go through each one of them in this talk. Before I get into it, quick primer on different types of MHD waves. I'll be talking about this a lot. You have alpha waves where the oscillation is moving along the field lines. So this is an alpha wave, whereas there's another kind of MHD wave called the magnetosonic waves, where the compression moves even perpendicular to the magnetic field lines, across the field lines. And then I'll be using these three icons to denote whether this emission mechanism can operate in neutron stars, in jetted black holes, and whether this is also numerically simulated, whether this emission mechanism also occurs inside computers. And I will not be using this icon anywhere. All right, so charged bunches. So that's one way. You can just bunch up these charges somehow and then let them radiate in cohesion. So this is a snippet from Alex's paper, and you can see similar lines in many papers. You just consider that these bunches automatically form, and the origin of the electric field that lets these bunches travel at the speeds that's required. You just assume that it exists. So it's not really clear how these exist. And one way for them to exist is through something called two-stream instability. So this is where you have a beam of plasma going through a background different plasma with differential speeds. So here I'm sending this green beam of electrons into a background beam denoted by the gray dots. And this is what you see happening. So this can be imagined as something that's happening along the field lines of a neutron star, for example. What you see is that as a beam starts accumulating certain fluctuations due to these two-stream instabilities, and you form really nice bunches. And these are phase-space bunches that you form. This is y-axis space, and this is Vy. That's the forward velocity perpendicular to the motion. But these bunches do not seem to last for a reason that they last. And let's assume that they exist in the neutron spheres. And then we can construct some models for a radiation mechanism. One of such models is the curvature radiation. So this is where you have a neutron star and these in the background field of some particles, and you form these bunches denoted by these stars. You need 10 to the 14 Gauss magnetar-like fields, and this has to happen at extremely close distances, 10 to the 7 or 10 to the 8 centimeters, for the particles to not have velocity dispersion perpendicular to the field lines and to maintain coherence. So the particles clump, and they form these clumps of the size of about FRB wavelength, about 30 centimeters. And you need these large parallel electric fields along the field lines to sustain these bunches, and they have to follow some accelerating path. This can happen along closed field lines or open field lines. There are other sub-flavors of this model. And there are a few predictions. For example, broadband emission, you can expect some flavors of these models, millisecond duration fast optical bursts, and a time-dependent polarization angle swings, the rotating vector model, and so on. And the burst rate is also expected to decrease with this frequency near to the -2/3. Another flavor is of this that invokes bunches is called free electron laser. So you have you send a beam of electrons through oscillating magnetic fields, something like this, and a laser-like emission, laser-like coherent light. This is a very well-studied phenomenon in laboratory plasmas. And Max invoked that in the magnetospheres of neutron stars, where the neutron star's crust oscillates, it launches these alpha waves that I talked about earlier, causes these wiggles along the field lines. And he also invokes a coherent, a relativistic beam of particles that are launched from processes, say, like magnetic reconnection. And when these beam of particles pass through these alpha waves, they bunch up due to what's called ponderum motive force. So this is where when you have an inhomogeneous oscillating electromagnetic field, and you put a particle in that field, the particle not just oscillates, but it also experiences a force that pushes this particle away from the high intensity of the radiation. That's the ponderum motive force. So this bunches the particles, and these bunches travel along curved field lines, and power that is emitted is comparable to the Larmor power that you can compute for coherent, for the curvature radiation that I talked about earlier. But these bunches also Compton and Raman scatter these Wiggler alpha waves to produce FRB-like emission. There are a few other predictions from this model. The emission duration is about 1% of the spin period. Other interesting prediction is that if a narrowband emission comes through this mechanism, it has to have a strong linear polarization and only linear polarization. You could also expect some giant gamma ray flares with millisecond duration rise times. Another flavor that invokes bunches is through inverse Compton scattering. Again, crustal oscillations happen in magnetars, and this not only launches alpha waves, but it can also launch fast magnetosonic waves. And these fast magnetosonic waves can travel across the field lines. And again, these FMS waves can create bunches by themselves with appropriate sizes comparable to FRB wavelengths at about 10 to the 8 centimeters. And then Compton scattering happens where these bunches, which are traveling at extremely large Lorentz factors, 10 to the 3 or 10 to the 4, it Compton up scatters the low frequency, kilohertz frequency, fast magnetosonic waves to gigahertz band. That's another model. And the predictions include a very narrow band spectra, something like what we see for repeaters. You could expect some weaker and narrower, higher harmonic components in the spectrum. And you can expect 100% linear polarization and circular polarization, depending on the angle of the observer with respect to the emission cone. Okay, so the next class of models invoke population inversion, something like what you see in lasers. And I've placed this between charged bunches and oscillating currents because you will find certain conceptual features in these population inversion models that are similar to these charged bunches and oscillating currents. Okay. Okay, there are many ways to cause a population inversion. I'll focus on one way in this slide based on shocks, and then I will discuss other ways in the upcoming slides. Let's say you have a magnetized transverse shock. That is, a shock is propagating along this x hat direction, and the magnetic field lines is perpendicular to it. That's the requirement. Say if it's along x direction, z direction could be the magnetic field lines. Particles from the upstream, they enter the shock. They gyrate coherently, and they form an unstable ring-like structure in their momentum space. X-axis shows the x momentum, y-axis shows the y momentum, and it forms a ring-like distribution, a soliton-like distribution. So this is a simulation, a particle cell simulation of such transverse magnetized shocks. You can find these soliton-like structures with a density cavity formed in these simulations, which are very interesting. And that's the reason why this mechanism operates. And how it works is that the X mode electromagnetic waves, that is the electric field of the electromagnetic wave oscillating perpendicular to the ambient magnetic field, are generated by oscillating currents along the y direction in this trailing soliton. And then the X mode FRB-like waves are emitted, which propagate through this density cavity, a soliton, and then it goes upstream. It goes upstream, and then it causes various instabilities, these filamentation and modulation instabilities. And these instabilities have another effect in that it induces an XBX, a magnetic field along X direction, and that gives rise to these O-mode electromagnetic waves, where the electric field is oscillating parallel to the ambient field due to the oscillating current along Z direction. The X mode and O mode oscillations are extremely important to explain the polarization position angles that you see from the different FRBs. This is the so-called synchrotron measured instability. By synchrotron, I typically mean that the emission is happening at very high harmonics of the particle gyro frequency, and you expect continuum spectrum. And the Maser efficiency is goes as 0.10⁻³ over magnetization. Okay, so the place where this mechanism works could be, for example, flaring black hole jet or a magnetar a flaring magnetar or even merging neutron stars, the transverse magnetic shock it can propagate into either baryons or into electron-positron plasma, and that can determine the high energy counterparts that you expect from FRBs. And the emission radius is large, AU scales, to avoid the induced Compton scattering and other optical lithic regions close to the neutron star. Predictions involve a synchrotron afterglow at X-ray GeV ranges for a baryon optical band. And you expect very high, close to 100% degree of linear polarization. Both constant and swinging polarization angle is possible, because like I said before, if you only emit X mode waves, it's going to be a constant polarization angle because the ambient field is not changing much. But if you also emit O mode waves with a perpendicular electric field oscillation, the superimposition can give rise to changes in the polarization angle within a burst. And this can also happen at 10 to the 13 centimeters at far away distances. Yeah, and the prediction is a narrow spectral energy distribution brought on by differential Doppler shift. Another way to bring about the population inversion is by steepening of an alpha wave. So you have a magnetar that quakes, launches kilohertz alpha waves, and the wave steepens. That is, the oscillating magnetic field of the wave is now larger than the ambient background magnetic field at about 10 to the 8 centimeters. It generates closed magnetic islands called plasmoids that you see here. And these plasmoids are ejected from the magnetospheres. These are seen from force-free numerical simulations. Are ejected from the magnetospheres, and these plasmoids then accelerate and drive ultra-relativistic shock ahead, and which can harbor synchrotron measure instabilities and produces FRB at 10 to the 13 centimeters. One of the interesting predictions is that these merging chain of plasmoids that you see here could produce higher frequency, shorter duration, and fainter bursts. And if you have a pair of bursts, something like what you see in SGR1935 from our galaxy, the prediction is that the latter one would be a bit more energetic than the former one. And the third sub-flavor invoking such population inversions invoke something called monster shocks. This is a very interesting new idea where, again, you have quaking magnetar or a neutron star collapsing into a black hole where it works. The dipole background magnetic field of a magnetar goes as 1 over r cubed, whereas the wave amplitude goes as 1 over r, the fluctuating amplitude. So the ratio goes as r squared. So the fluctuating amplitude as a normalized to the background field, it increases as you go to large radius. So it can be understood from this schematic. In a particular phase of oscillation, the wave B field and the background field are aligned, and in another phase, they are anti-aligned. So in this case, the electric field is smaller than the total magnetic field, whereas in this case, the electric field is larger than the total magnetic field. So this is a dangerous condition. So when electric field gets larger, when E squared is larger than B squared, the assumptions of ideal magnetohydrodynamics, they break down. And that's what's seen in this particle cell simulation by Arno and Amir. Black curves show BZ, red curves show oscillating EY. At some radius, EY gets larger than BZ, or E squared gets larger than B squared. That's where particles start accelerating, and it produces a very strong shock. And this is one of the strongest shocks in the universe. And you can see it forming over here. This also forms these soliton-like structures which can harbor synchrotron maser instabilities. The very interesting thing is the synchrotron maser instability in this scenario happens at 10 to the 8 centimeters, extremely close distances from the neutron star surface. And most of the energy goes into X-rays, about 1,000 goes into gigahertz band. Another way is through non-resonant interactions with alpha waves. Magnetar quakes, produces alpha waves, and these alpha waves can interact with the magnetized and relativistic plasma in the magnetosphere that are a higher temperature. And the reason why they have to be a non-resonant interaction is because the gyro frequency of the particles in the magnetosphere is much larger than the frequency of the alpha waves. That's the non-resonant condition. This is the omega c, the cyclotron frequency of the particles, and this is the alpha frequency, and this is the wave vector, and this is the speed of the particles along the field lines. What I show here are the particle distributions. You have a Maxwellian distribution of particles, and then as this interaction happens over some time, you form these crescent-like shape in the momentum phase space. This is lifting the particles to some sort of a metastable state. This is a population inversion, and this can give rise to synchrotron maser-like emission. Some of the predictions is that this mechanism of synchrotron maser instability has a much larger efficiency than the shock marks, depending on the plasma temperature. It could potentially expect a much higher frequency and even fainter emission from even smaller radii, smaller than 10 to the 11 centimeters. 10 to the 11 centimeters is where you expect gigahertz emission. And this has a strict limit and it cannot produce extremely low frequency FRBs below 0.few gigahertz. We haven't seen FRB2025 below some frequency. So if maybe this could be a candidate for that. The other third mechanism is through oscillating currents. Okay, yeah. So a flavor of emission mechanism that invokes oscillating currents is called through magnetic reconnection. This is where you bring magnetic field lines of opposite polarity next to each other, and then they snap into each other, thereby changing the topology of the field lines and giving away energy from the magnetic fields to the plasma. So this can happen in the striped jets of black hole accreting black holes, or you can also have neutron stars, of course. Magnetar crust quakes, it launches a low frequency, again, kilohertz pulse away from it. And what happens is that these propagating pulse, it reaches a light cylinder and it propagates beyond the light cylinder, which is where you have these current sheets. Current sheets are the locations where you have these oppositely oriented field lines, and the region between them are regions of current. That's seen as these tails in these particles, in these global peak simulations of neutron stars. So the green ones are the magnetic field lines. As you can see here, these are going out, these are going in. The current sheet is where a flip happens. And that's where magnetic reconnection also happens. And this is a triggered event where the low frequency pulse hits the current sheet and then causes the formation of what are called plasmoids, which are basically variable linear currents. And here's a movie that shows what happens during a reconnection event. So reconnection is triggered in the center, and you form these plasmoids. And these plasmoids merge into each other because currents of same direction, they attract and they merge. And these merging events perturb the magnetic field immediately surrounding these plasmoids. And these perturbations give rise to higher frequency fast magnetosonic waves propagating radially away from the merging site. I'll play this movie again because it looks good. The waves, the quasi-spherical waves that you see emanating from this region are the outgoing Poynting flux from these mechanisms. And there are a few other predictions, conversion efficiency of about 10 to the minus 3, and the emission frequency scales as luminosity of the flare to the 5/8, set by the size of the plasmoids. And the smallest plasmoid mergers could give rise to extremely narrow features of the order of tens of even hundreds of nanoseconds. And this happens at about 10 to the 11, 10 to the 12, 10 to the 10, 10 to the 11 centimeters and beyond. And you expect 100% linear polarization and the constant polarization angle from all the bursts. Another flavor of oscillating currents is something called force-free FRB. So what is force-freeness? So force-free is basically a set of closed set of equations that describe the electromagnetic field of a magnetically dominated plasma. So you just have enough charged particles to screen the electric field such that E dot B is 0 and B square is larger than E squared. But the plasma is very diffuse and barely exchanges stress energy with the fields. So you can just ignore the inertia of the particles. As Roger says, a tsunami doesn't care about the vibrations of water molecules. That's the approach of this force-free FRB model. So magnetar quakes launches a pulse of toroidal oscillating magnetic fields and current propagating along the open toroidal flux tube. These turbulent fluctuations steepen at about 10 to the 7 centimeters, reach FRB scales, centimeter scales about 10 to the 9 centimeters. It mode converts to electromagnetic waves and propagate. Here's another movie. This is a turbulent system, and the bottom right panel shows the current density. This shows the gamma beta momentum, and the top right shows the Poynting flux. All the turbulence is initiated at the center of the box. You see the Poynting flux eventually going, emanating away from the box and spreading the entire domain. So that's sort of the idea. You can expect broadband polarized emission up to 10 gigahertz. Curvature GeV can be produced. Final couple of slides on that could sort of disappoint a lot of you. I'll quickly touch upon the nonlinear propagation effects that Robert did not talk about, which is that remember that the FRBs are high amplitude waves, where the A parameter is extremely larger than 1. So the electrons in the upstream medium, they gain an effective mass given by this. So if this strength parameter is 10 to the 4 or even 10 to the 5, 10 to the 6, you can have somewhat like a negatively charged protons. This actually changes the rate of induced Compton and Raman scattering, and the dispersion measure experienced with the FRBs locally changes everything. This can also change the refractive index of the medium surrounding the FRB, because the refractive index, as Robert pointed out, has a component that is plasma frequency squared, and plasma frequency is dependent on the mass of the charged particles. And if the mass of the charged particles changes by this, plasma frequency changes and the refractive index changes. So if you have a rising pulse of an FRB, the earlier parts of an FRB could be experiencing different refractive index than the higher peak of an FRB. So it completely changes the propagation curves. And this can give rise to lots of plasma instabilities, filamentation, modulation instabilities that can imprint different temporal and spectral structures onto the FRBs that are separate from the emission mechanism. Quick movie, I'm sending an FRB like pulse through a medium, and then it completely changes the properties of the FRB as it passes through it. I'll quickly run through my conclusions here. It is possible that multiple emission mechanisms can operate within a single engine. Different flavors of population inversion or oscillating current models could operate in multiple engines, neutron star or black. And measuring the emission radius does not inform what the emission mechanism is. Recall the monster shock. It invokes synchrotron maser happening at 10 to the 8 centimeters. And the short width timescales that you observe from new FRBs does not again translate to corresponding emission radius immediately, because we call plasmoid mergers happening at 10 to the 12 centimeters. Extremely small plasmoids can merge and produce very short features and non-linear propagation effects that can impart these extremely short duration timescales onto FRBs. It's very challenging to pinpoint one emission mechanism without understanding these non-linear wave-particle interactions. And we need more theoretical developments supported by computational simulations to increase the predictive power of models. I'll stop here.
Thank you, Naveen. That was a very informative talk. A lot of things are something that we don't think day to day. So I'm sure there are a lot of questions.
Yeah.
One second. Yes, the catch box. Yes, so this is Robert May speaking. I just gave the last very nice talk. I wanted to wrap my head around a little bit about the current sheets, which happen just outside of the magnetosphere. So in that case, you've got reconnection just outside of the magnetosphere, and I'm trying to figure out the geometry from here. Oh, sorry, outside of the light cylinder. Yes, thank you. I'm trying to figure out from the geometry, would it only interact, or would it only reach our line of sight at specific viewing angles? So would you still see the periodicity of the source? And could it occur anywhere in the current sheet? So subsequent bursts could be separated by about a light cylinder on the sky?
Good question. It is definitely viewing angle dependent, and I'm not sure about the periodicity here because these current sheets, although it looks like two-dimensional structures, they have some inclination angle dependence to them, and these are like tori, something like what Jans has drawn here. So they happen in all azimuthal angles pretty much. So I'm not sure if that would have an imprint of periodicity there. And along the current sheet, yes, plasmoid mergers could happen anywhere, but the sizes of these plasmoids will be different, so they may not fall in the gigahertz band.
Thank
you. Young Han, please.
Hey, Navin, very nice talk. I just have a follow-up question about this model. Yes, the C1. So because you need a fast magnetosonic wave to do this, compression of the current sheet, but you also mentioned the Alex Chen's paper, the fast mode may experience the E square larger than B square. So maybe this fast modes cannot escape all the way to the light cylinder. Is that right?
Sorry, you're asking if the fast modes could escape beyond the
Yeah,
light
because
cylinder?
it may. So yeah, this is my question. So can this mode really propagate freely all the way to the light cylinder to do this compression?
Yeah. So I think the authors are careful in not claiming that these are the fast modes that are hitting the current sheet. They just call it a low frequency pulse, maybe because of that reason. But it could be any compressive perturbation that reaches the Y point that could launch this, that could trigger the reconnection. But yeah, that's a good question.
Okay. Let me ask a more general questions. You mentioned various models. I see some models mainly produce very high linear polarization, and maybe they also show you very different spectrum bandwidths. So observationally, do you think all the circular and the non-zero circular polarization FRBs have to use propagation effects, the additional propagation effects to do this?
Okay, good question on the circular polarization. So how can a circular polarization be produced? So you can have X mode wave and you can have an O mode wave and just put them 90 degrees out of phase, superimpose them, you get circular polarization, right? So if the linear polarization models that I've talked about here, if they can produce both X mode and O mode waves of comparable luminosities, then they can produce circular polarization. If they are unable to produce O mode waves along with the X mode waves, then probably propagation is the way to produce circular polarization, or they just don't work for that particular source.
Okay, thanks.
More questions? I think so let's go. Let's try.
Hi, my name is Om Gupta, and I wanted to ask a question on your last slide, which is when we have a very powerful electromagnetic wave propagating through the plasma, my understanding is that the head of the wave would interact with the plasma and with the ponderomotive force, move the plasma ahead, so that the rest of the wave is not impacted so much by the plasma through which it is propagated. Is this also seen in numerical simulations?
Yes.
Okay. Thank you.
I mean, the work is still undergoing. This is for a specific value of A naught and certain other nonlinearity parameters for which you see the plasma completely pushed ahead by the FRB wave. But there are other parameter combinations for which you don't see such full flowing happening, but some plasma goes in, and you see, for example, in this video that I just played, some plasma there is some accumulation happening in front of the wave, but some plasma manages to get past the head of the wave. So it's very much under exploration.
All right, let's continue the discussion. We're well into our lunch time now.
Thank you.
Thank you.
Let's thank the speaker again. Thank you, Naveen. Lunch would be served
I'm just losing control of the mouse, which is annoying.
Okay, that's what I was gonna ask, if I could use the mouse to point.
Yeah, I think it's a keynote thing because PowerPoint was fine.
Oh.
I literally cannot recover the mouse.
Okay.
I can't even like I can't even use the 3 fingers to like swap.
Yeah, there might
screens
be
either.
like a keynote option to make them announce it between through when you're.
You know, sorry, I don't use Keynote. Sorry.
Yeah, let me see if I can find I'm not very adept though, unfortunately. If not, let's see.
So you might be manually. There. Might just have to describe, I guess.
Yeah, I can just describe if I have to. Let me ask, is it go time or that also has ChatGPT?
You're unmuted, by the way. He couldn't get that error on that like the error doesn't come out. You know, like the perfect.
Look at this.
Oh, that's
wonderful.
It's like almost a laser
I
pointer.
couldn't get it to look early on.
So that's just the top one and then the button advance and then the top.
Oh, that's really nice. Okay.
Sorry, let me.
Yeah, no, like.
Okay.
You can even try. I just want to circle. Oh, that's so weird. Yeah.
Oh, so this doesn't. Oh, so this is what it says then. If we go to the top of the screen after you press play, we have to skip over it. Start your slideshow. Move your cursor to the top of the screen.
Yeah,
I guess.
pop up there.
Okay, I'm just gonna. I can just talk.
Yeah, we'll just.
Oh, so you can put this on for a second. But then the Zoom, this microphone's in the speaker. Yeah.
Okay. Let's get started. Thank you all for coming. So my name is Luis Marribas. I'm a project scientist at University of California in Santa Cruz. I will be speaking later in the week, but I'm chairing this session. So we will have 2 talks now, cosmology and circumgalactic medium. And our first speaker is Matt McQueen. Matt is a professor at the University of Washington in Seattle. And he will be talking about cosmology, but he has been working on many other different things. And I encourage you to talk to him this week. He knows a lot about a lot of things, in particular CGM, intergalactic medium, large scale structure, and all things related to cosmology. So take the opportunity. And yes, I'll leave you with Matt. Thank you, Matt. I will be giving you.
Awesome. Oh, thanks for the really kind introduction, and it's a pleasure to be here. I should definitely have this on, right? Okay, I'm a bit of a pointer, and the mouse is not displaying, so I'm gonna try to point by describing. But yeah, I'm talking about FRB cosmology, which is a topic where we're trying to figure things out, and I think that's going to be apparent from this talk. But we have 2 things that we think are potentially interesting about using FRBs as cosmological probes that make them unique, and one which is much better developed, and you're going to hear a lot about this week, is that they're sensitive to very diffuse baryons via this effect of plasma dispersion that was talked about earlier today.
and in fact, like we just don't have ways of probing low density ionized gas in the universe other than FRBs, and there's also some CMB anisotropies that are interesting here. And so potentially FRBs can tell us about where most of the gas is in the cosmos, which will also be the subject of the talk after this. And that's potentially interesting for cosmology. The second aspect is that they can be exquisitely timed. They're about as good a point source as you'll ever get. This is even the case if there's millisecond scattering in the host galaxy. And so if we're unambitious, we can time them to a millisecond, but some have started to even use coherent approaches where we're timing their arrivals to nanosecond. But at the same time, precision cosmology is hard, especially for constraining the standard set of cosmological parameters, and so the FRB cosmology is going to be pushing up against this. That we have really good methods for constraining many cosmological parameters. Most or all cosmological parameters are constrained at least to like several percent. Some a lot better. Okay, so first idea you might come up with for constraining cosmology with FRBs is to do essentially what's a Hubble diagram. We call this in our field the Makar relation, after this paper that initially did it with 8 FRBs by the ASCAP-Craft collaboration. And so essentially on the x-axis, you use velocity or redshift, they're the same. And the y-axis is dispersion measure, which you can essentially think of as distance in a Hubble diagram. And so this was done, this diagram was made with 8 bursts in 2020, and it's improved steadily by various groups. And so for extracting cosmology from this diagram, there's an equation at the bottom of this slide that shows the expectation for a homogeneous universe for how much the contribution to the dispersion measure you have out to a given source redshift for the FRB. And so most of this term just depends on cosmology. There's the small fraction, this omega stars plus H1, that's not probed by plasma dispersion, the neutral gas and gas that's in stars. But I can believe that we can model that to a percent or so level. The part that's worrisome about doing cosmology with this type of diagram is the second term in the equation. This is the contribution from the host galaxy. So FRBs come from biased regions in the universe. They're dense regions in the universe. And in order to be able to do competitive cosmology with this relationship, we really, at the percent level, need to model the second term, like to make statements about, for example, the Hubble tension, probably that are helpful. We really want this to have an error of about, or to know that term to about few percent. And I think it's kind of, it's hard for me to believe that we'll ever be able to do that. So I'm not super optimistic that we're going to make a lot of progress with this type of approach to FRB cosmology. Of course, at the end of the talk, if you object to my statements, and I'm going to make some opinionated statements such as this one, I'm happy to discuss. Okay, so if we're not going to be able to do cosmology from the mean dispersion measure to a given redshift, the next idea you might think of is, let's say I map many dispersion measures to many FRBs where I kind of know their redshift, or I know their redshift, maybe just with photoseize. Then I just correlate the dispersion measure between the different FRBs. Well, this is going to be sensitive to large scale structure, because if I have a big structure, my dispersion measure for a couple of FRBs may go through the same structure. And so when I correlate the dispersion measures, essentially, this is a large scale structure survey. It actually is a large scale structure survey that's very similar to weak lensing. Where with weak lensing, rather than dispersion measure, you measure the shear of your background galaxies. And dispersion is giving you the total column of electrons. Shear gives you the total amount of matter, essentially, along that sight line. So we can compare the two because we're actually in this era of weak lensing surveys. And so with modern weak lensing surveys, such as Rubin LSST, we're talking about 1 billion or probably 10 billion galaxies where we're doing this type of mapping of measuring the shear. The error on the shear for each galaxy turns out to be a bit larger. There's a lot of text here, and I'm not going to go through it like carefully. The error is a little bit bigger than I would estimate for FRBs, but nevertheless, we're using at least 1 billion galaxies. And so if you just kind of do the back of the envelope, I think you need 100 million FRBs for this to start to be competitive. And at the same time, the FRBs are mapping the baryons. And the baryons turn out to be kind of the messiest, we think, part of large-scale structure, messiest part. And so maybe this isn't 10 to the 8 FRBs is a lot. It's the baryons. We're already doing this with weak lensing, so maybe this isn't the way we want the path forward to cosmology with FRBs. Okay, but. And as you're going to see during this talk, we're often going to take ideas and keep trying to improve them. Maybe we don't have to map large-scale structure at the precision that you need for precision cosmology. Maybe we can still facilitate cosmology constraints. And so in particular, it turns out that with weak lensing surveys, and essentially like somehow the field of cosmology has invested humongously in these surveys, such that most upcoming cosmology surveys are of this sort, and like a bunch are listed here, including LSST and Roman. It's Euclid, and so the cosmologists have put a lot of energy into weak lensing. And when we were making forecasts for weak lensing, we actually didn't realize that the baryons are as terrible as they are. And so this movie from the Lustra simulation is just showing you like how messy the physics of the baryons are. The galaxies are forming in certain parts of the universe. The explosions are the supernova and the AGN that are going off in those galaxies, and they're moving the baryons around. And so it turned out that when people made forecasts for all these surveys, the forecasts are wildly or way better than we have been able to achieve with these surveys. And it's because of this limiting factor of knowing where the baryons are. And so potentially FRBs could be used to help here. They could be used to map the baryons. You don't have to do this at high precision as you do for constraining precision cosmology, and it will help these surveys. And people have started to do this. I think the most promising way to do this is to correlate foreground galaxies with FRB dispersion. We did this, or my student and I did this a few years ago on CHIME DR1. There's a really interesting paper that's going to be presented later in the week by the CHIME collaboration, Wang et al. That did this on CHIME DR2. And I would say that the constraints are already getting interesting for help facilitating these weak lensing surveys. There's also been a lot of interesting work that you're also going to hear about this week on using the scatter in the dispersion measure redshift relationship to constrain baryons. And this is looking to me, I was originally kind of pessimistic about that type of approach, but I'm gaining some optimism based from some of this work that you're going to hear about. Okay, and here's just a cutout of all of the talks you're going to hear during this conference on this topic. If you're constraining the gas in the CGM, this is the gas that also we want to know where it is for constraining cosmological parameters. Okay. So now I'm going to talk about constraining cosmology from FRB timing, which is potentially the more exciting route, but where our ideas are less developed. Most of the ideas I'm going to talk about are going to involve strongly gravitational lensed FRBs. There's this really nice paper by Connor and Ravi that motivates that in the future, when we have tens of thousands, hundreds of thousands of FRBs, we should expect a lot of strongly lensed FRBs. Okay, with strongly lensed FRBs, the first idea you might have for constraining cosmology is that if you're able to measure so it's strongly lensed, so it has a bunch of it's going past a galaxy or a galaxy cluster, and this is creating some number of images. And so if you measure the positions of those images and you measure the delay, the arrival time delay between the different images, you can show that this can break the degeneracy between the mass of the lens and the Hubble constant. And so you can measure the Hubble constant if you assume that you know the mass profile of the lens, which is a big if. So you can do this with FRBs. You can measure the Hubble constant. Currently this is done a lot with AGN. The potential advantage of FRBs is that we can time them much better than AGN. So maybe this is the path forward. We'll do this arrival time lensing cosmology, but we'll just do it better because we can time FRBs better. Unfortunately, I think the consensus of people who've thought about a cosmology from this type of probe is that what's dominating the uncertainty is not how well we can measure the arrival times of AGN, or FRBs. It's actually the potentially more complicated mass profile of clusters and galaxies, that galaxy lenses, than people have assumed in the past. And so, unfortunately, because it's timing is not doesn't appear to be the limiting factor. FRBs don't appear to me to be a huge advance over doing this with AGN. There's an interesting paper that acknowledges this and says, okay, maybe we don't use a galaxy or galaxy cluster lenses, and instead we use stars. So stars are we're going to start to see strongly lensed FRBs by cosmological stars in for example, the halos of galaxies. And then then it's a point mass. And so I don't have to model the mass profile of my lens. And you could do this as long as you can also identify the positions of the images. So the angle from the point mass of the images. And so this paper by Tsai proposes that you can use scattering, where you get, as we saw, an AU scale telescope in effect to potentially measure the positions of the images. You need to do this at the percent level because we're doing cosmology, or maybe fewer, 10%. But if you can do that, then that would be a way forward. Okay, so we're iterating on this. So maybe galaxy and galaxy cluster lenses for just time delay cosmology is not the way to go. But what if we measure the delay between two images, and then we wait some time? The universe has expanded by some amount over that time, and then we compare the difference in time in the delays between the two images. The formula is wrong. H naught should be to the -1. This formula is just the estimate for how much if I wait a time delta t, and my images are separated by some number of days in the right, it's evaluated at 10 days. Delta t times H naught is just how much the universe has expanded over a time delta t. And so if I wait a year, you just do back of the envelope, you expect that the time delay between the images to change by 10 to the -4 seconds. 10 to the -4 seconds, that's of order the duration of an FRB. We could potentially measure that. If we measure that, and this is the only effect, we would be able to constrain the cosmology, because this depends on the expansion of the universe. Unfortunately, I think this doesn't quite work. It would be super cool to measure this, first of all. And in order to measure this, you need a lens repeating FRB. For a lens repeating FRB, the fraction of FRBs that are repeating is a small fraction of the total number of FRBs. And so we're starting to get into territory where it's not totally obvious that this source exists. But if it exists and we measure this, it's part of the signal in the change of arrival time of the images is telling us about the expansion of the universe. That's amazing. But it also turns out that if you just back up the envelope for how much you think the mass of the lens grows, you'd write down the exact same estimate. Like the mass of your lens should also be growing on a Hubble time of order. And so to me, it doesn't seem like this is a precision cosmology probe, although super cool. Okay, so we're going to keep iterating on this idea. So rather than the change in arrival time of images, we're now going to talk about the change of the change, or the change of the change of the change, or just some power spectrum of I measure the arrival time difference and I take some power spectrum of it. And so what could this be sensitive to? Well, this could be sensitive to small things that are changing on the time scale that you're measuring the change of the change over. And so for example, in this image, it seems like the dominant effect could be that dark matter we expect to be very clumpy in the universe, to clump down to very small scales, Earth mass scales for WIMP dark matter. And so if this could potentially be sensitive to dark matter halos drifting across the line of sight, and in particular, how far a dark matter halo drifts over year time scales is about 100 or 1,000 AU. And so dark matter halos that have scales of 100 or 1,000 AU. And so we did some back of the envelope estimates to see if this could be interesting. And so our conclusion was that if you could do coherent timing, so if you could time these changes and the delay, the delays between the images, on the nanosecond time scale, then this is potentially sensitive to the amount of clumpiness that we expect for just vanilla cold dark matter. And there are a lot of dark matter models where dark matter is clumpier, like some of the axion models where the axion is formed after inflation, the condensate. So maybe that's the thing to do if we are able to discover a lens repeating FRB, and if we're able to coherently time it, which probably means that we have to be able to measure it at relatively high frequencies, like several gigahertz, then the time delays of the images will change in a stochastic manner that depends on the structures that are drifting between us and the FRB. And I'm probably going too fast. How much time do I have? 7 minutes. Okay. All right. This is my last. Oh, no. Oh, I actually have more slides than I realized. Okay. 7 minutes is perfect. Okay. Another direction to go. Maybe we don't want to constrain the standard cosmology. Maybe we want to constrain more exotic things. And so the early universe can produce things like primordial black holes and cosmic strings. And so we can use the lensing of FRBs to place constraints on the formation of these objects. And so there was really interesting work led by Calvin Leung here that used the CHIME data set to do just this, and actually did coherent timing. And the constraints are shown here. So they were looking for small offsets in the arrival time from different images of a lens FRB, where it would be lensed by one of these primordial black holes. And they were sensitive to mass scales of 10 to the minus 4 to 10 to the minus 2 solar mass. And you can see their constraints on the left. It depends slightly on what they assume about scattering in the host galaxy. The constraints aren't quite competitive with macho surveys, which are most of the contours that are in the plot on the right. But there are going to be a lot of FRBs in the future. So this is something that definitely FRBs are going to contribute our understanding to. So constraining the mass in primordial black holes in this mass range. One in these plots is if all the dark matter is in primordial black holes of that mass. Okay, cosmic strings is another thing that could be produced in the early universe. And actually, there was a flurry of activity several years ago when PTAs announced a discovery of a stochastic gravitational background, a punitive discovery. That background could potentially be generated by cosmic strings. Currently, the cosmic microwave background rules out cosmic strings that have a tension. So tension is the string tension is the one parameter that characterizes these defects that can be produced in the early universe. So tension is greater than 10 to the minus 7 in these Planck mass units. So you can calculate what is if a FRB is lensed by a cosmic string, what is the delay between the two images, a typical delay. And so for G mu 10 to the minus 8, an order of magnitude less than what has been probed, the delay is 500 seconds. So that's a very reasonable number. And so with my collaborator, we did forecasts and laying die. And what we find is that around 100,000 FRBs, we're starting to probe string tensions that are close to the tensions that are the CMB is ruling out. And as we go into the millions and tens of millions, it could get really interesting, and we could probe this parameter space to tensions that are much smaller than we have currently been able to. Okay, and then this is my final slide before the conclusions, and also maybe the most out there. So all of the timing applications that I mentioned involve lensing systems that we're looking at the different images and when they arrive. But you could imagine putting your telescopes far enough apart and timing the arrival of your FRB at the different telescopes. And so you can ask, like, what the heck would this give you? Well, the wavefront that arrives at your telescope when your telescopes are far enough apart starts to become sensitive to the curvature of its curvature. The curvature, if I measure the curvature of the wavefront, it's telling me about the distance to the FRB. In order to do this, you need 4 telescopes for the same reason you need 4 GPS satellites to measure the location of your phone. But if you have 4 telescopes that are separated by 40 AU, so I'm looking at the equation at the bottom of this slide, and you're looking at an FRB at 200 megaparsecs, and you're observing at 4 gigahertz. There's a reason you need to observe at slightly higher frequencies that I'm going to get to than is typical. And if you're able to time to about the inverse of the frequency, then you can constrain the distance to the FRB by measuring this curvature of the wavefront with these 4 telescopes to about 2%. 2% is how well we've been able to constrain distances of supernova. And the reason I chose 200 megaparsecs is 200 megaparsecs is the mean distance of supernova in the SHU survey, which is one of these surveys that is in this Hubble tension fight. Okay, so you can ask, okay, how crazy is this? I would say that a lot of things about this actually work. You would do this to repeating FRBs. And because then you would know where to point the telescopes. The most repeating FRBs, or a lot of repeating FRBs, are at distances that are really good for this, 100 to 1,000 megaparsecs. The short duration of FRBs is actually really good also for this because you can actually send the data back to Earth, which is a problem if you were sending like a huge voltage time series. You can use large telescopes on Earth to try to pull out the signal noise on your to pull out the waveform from your distant telescope at the outskirts of the solar system. I think the biggest issue with this is that you need to go to relatively high frequencies because here I'm assuming that I can time to the inverse of the frequency. And so if you just take the scattering times from, for example, Cordes and Lazio, for frequencies below 4 gigahertz, the scattering times are longer than this delta t. At about 4 gigahertz, things become refractive, and the refractive time delays become short enough that this error, I think, is realistic. But then there's the question, how many FRBs can we find at these higher frequencies? And so with the remaining minute, I'm just going to conclude. So that safe bet, FRBs are going to contribute to constraining cosmology via figuring out where the baryons are and facilitating weak lensing surveys. And I think we're already at the cusp with some of the work that I presented from CHIME collaboration of this being interesting. The timing is potentially more exciting and more ambitious. The detecting lens repeating lensed FRBs would be wonderful. Lens repeating FRBs would be really wonderful. It's not totally clear if this will contribute to standard cosmology for the reasons that I mentioned. FRBs will contribute to constraining these exotic relics, cosmic strings, and primordial black holes. And maybe at some point we can do something even more ambitious. Thank you.
Thanks a lot, Matt. We have about 4 or 5 minutes for questions. And please encourage the ones in the background because I really want to throw this. Raise your hands. It's floppy and soft and light, so don't be afraid. Okay. Sorry, Matthias is farther away, so you're gonna go for that.
Oh, that's wonderful.
Excellent talk. This is Matthias. I'm a grad student at U of T. I was just wondering, what would you say is kind of your estimate for a timeline with which we could have a space-based kind of solar system-wide VLBI array? Your best guess.
Especially with current funding and what I will say is that the technology that's involved is not that much different than a GPS satellite. And so you need an atomic clock that's like on the atomic clock on our GPS satellites. You do need a big antenna. This radio Astron that Calvin even mentioned in his talk is a 10-meter antenna that was put into space. What I find is with 8 meters in space and 80 meters on the ground, you can get to 1 Jansky millisecond fluences for a millisecond FRB. So it's in the ballpark. We've discovered 5 gigahertz-ish FRBs that have those fluences. I would really like to know how many repeating FRBs one could expect. You need at least tens, I would say, for this to be worth it. I think we're at the point where it would be interesting to do some research, like the research into this, like where a high frequency survey targeting maybe the CHIME FRBs, it would be really interesting if there were repeating FRBs that were specific to higher frequencies that CHIME wasn't getting. But 10 years.
Okay, we're going for Robert. Matthias, it's your turn.
Am I going back to you or throwing over there?
We are going back.
Oh, back to Robert.
All right. Hi, it's Robert Main again. So I was wondering about the when you're measuring the time delays, which you said is not the limiting factor, either from lensing or when you're doing this like solar system wide VLBI. Are you counting on being able to actually coherently correlate the bursts? And then for the case of the solar system, I was wondering, like, are the different sight lines through the heliosphere, is that going to mess you up the same way the ionosphere does, or?
Yeah, these are really good questions. So it depends. I guess 10 to the minus 4 seconds doesn't necessarily require a coherent. And that's just for a year. If I waited 10 years, then it's a millisecond. I think the biggest problem for this, the change of the change, is that you need this to be coherent. And actually, so it turns out that for a lensing system, where you're really kiloparsec or tens of kiloparsec size telescope, in effect, you really worry about also scattering in the host galaxy. And so I think that could put any scattering in the host, essentially for this idea, no, you can't have any scattering. Our galaxy becomes refractive, 3-4 gigahertz if you take -4 scaling. But yeah, so I think scattering is huge here. For this case, yeah, this is also coherent. That's why we're going to high frequencies. In this case, you don't resolve, but unless the scattering screen is greater than hundreds of parsecs from the FRB, you don't resolve the scattering screen in the host. And so here you more worry about scattering in our galaxy.
We have maybe Zoom question.
Kriti Sharma, do you want to unmute?
Yeah, hi. Thanks, Matt, for the amazing talk. I haven't thought a lot about timing yet. I just wanted to ask for like measuring change of change or just the change in the time delays. What's the observable that we are looking for, like in terms of modeling? And for example, in case of feedback, we have several models, right? And we are sort of limited by that as well. So what kind of limitations can we expect from the modeling front?
Yeah, okay, that's a good question. And so like you could partly think of this as like a Taylor expansion, that like the first is just linear and the time delay for us to wait. And then you'd have a quadratic term that the quadratic gets rid of anything that's on a really long time scale. So that's what we're doing. Like because the linear term was dominated by things like the Hubble expansion and the growth of the lens, which occur on cosmological timescales. And so the quadratic is actually dominated by really small things that are moving across your images. You can also think of it as a power spectrum. Because it turns out that not only is it interesting to do the quadratic and the cubic, like everything is kind of interesting there because it's probing different size structures crossing your lenses. And so the paper considers both of those. So that whether there's a different way of thinking about it, and like those are the ways we thought about it in that paper. And so yeah, so then you'd measure this term, and then you'd ask, how much clumping do I need along the line of sight in order to explain it? And I guess one thing I didn't mention is that there is a little bit of modeling uncertainty here, like even for like WIMP clumping dark matter, what we're talking about is like the gravitational time delay between us and the FRB, and so there's some modeling there, that nonlinear modeling that you have to do to make statements like WIMP dark matter will produce this amount of gravitational time delay. Axion dark matter, which has more clumping, will have this time delay. So there's a modeling aspect, kind of like the feedback at the end.
Gotcha. Thank you very much. So for axions, can we also like put computative constraints on the axion mass? Like the particle mass?
Yeah, that's right. That's a good question. We were thinking of the QCD axion actually, and so there's some range of mass that's motivated. And the range of mass actually affects the size of these fluctuations, because whether these axions are generated by the misalignment mechanism or cosmic axion strings, I'm not going to get into. So it does constrain the mass, for the axion.
Gotcha. Thank you.
This is not the fuzzy like pseudo axion type of stuff people have been doing. It was the QCD axion.
Gotcha. Thank you.
You're welcome.
Time for one quick question. Maybe we can change speakers in the meanwhile.
Barak Zakai asking. So it seems that the property of the FRB that you are using in this particular idea is only the fact that it's compact. Aren't there compact radio sources that that are constant that you could use with this, so that maybe even one satellite that is just moving through the solar system will just map the distance?
Yeah, this is really interesting. So we started That's right. Not only is it compact, but you really don't, you want it to be point source for tens of AU baseline. So so it has to be really compact. And so the paper kind of goes through different radio sources. Even black hole shadows are kind of marginal. Like the FRBs are really compact. Like we even saw that with millisecond scattering, with the scattering screen hundreds of parsecs from the FRB, they were still like AU type of like the angular extents. And so at least our contention was that they were the most compact thing that you could really do that, or the only thing that was point source like that, where you even, so the black hole shadows we would even resolve with these baselines. So I think FRBs are actually special. They're more point source like than anything else that we can imagine that we can see at extragalactic distances.
Okay. It's really sensitive.
No, where did it go?
Okay, while we are getting set, I'll introduce our next speaker, Sanskriti Das. She's a Hubble Fellow, postdoc in Stanford, expert on circumgalactic medium. And I think she will talk about that, from X-rays to Zodiac, Zeldovic, and I think going to cold gas also 21. 21 centimeters in front. So yes, all of you will be okay.
Am I audible? Oh. Yeah, I'll try to speak loudly so that you can't see it. It's post lunch, so I understand. You have to click on it. Yes. Oh.
It's not like a highlight like this one. Oh, it doesn't. Okay, let's do this one.
Hello, everyone. As mentioned, I'll be talking about circumgalactic medium and its different tracers. So thanks to the previous talk, I don't need to convince why FRBs are great at probing very low density diffuse plasma. And that saves me some time to talk about things that are not FRBs. And one of the main purpose of this talk is to give an overview of the CGM with different tracers and create more conversation across different communities, instead of just claiming this is my favorite tracer and this is the best. I don't think really we have a best tracer. So the purpose of this talk is to show how we can try to move from this artistic illustration to eventually having an actual empirical data to know how CGM looks like. And unlike the more, sorry, go ahead. And yes, unlike more massive halos where we say intra-cluster and intra-group medium, ideally we should say it is intra-galactic medium, but as traditionally CGM and galaxies has been studied from the optical point of view, the stellar disk has been called the galaxy for a long time, although it is just a subset of the galaxy. So CGM is anything that's outside the stellar disk and is extended out to the virial radius. And again, you can choose R500 or 200, whatever you like, because the hot gas doesn't abruptly stop existing at any radius. So the CGM is a very happening place because of the infalls, the outflows, and the fresh accretion all happening in the same time. And CGM is an incredibly multi-phase medium. Its density and temperature is expected to span more than 2 orders of magnitude range, which is why we need so many different tracers to correctly probe it and constrained in different physical and chemical properties. Now, broadly speaking, there are 4 problems that we can try to solve with CGM. One is the missing galactic variance problem. Now, baryons are quite interesting depending on your perspective. If you're a cosmologist, you are more supposed to think of baryons as a disturbance because your interest is more probably in the dark sector. And if you're interested in the galactic and extragalactic properties, we often think in terms of metals. And their baryons become a good bridge to connect these two fields. Now, missing galactic baryons are actually separate from missing baryons because on a broader scale, cosmic waves will obviously have more baryons than the CGM. But the question is, if the ISM and stars have only 20% of the required baryons, do all galaxies retain all of their 80% missing galactic baryons, or do some of the galaxies lose them? How does the baryon sufficiency depend on the galactic properties, and how does that change with time, for example? Another problem is the missing metals problem, and this is also very distinct from missing galactic baryons. Because if you find a lot of baryons, that doesn't necessarily mean it has come from the feedback. It could be a lot of unprocessed baryons that is just ionized by the cosmic background. So if you trace the metals, you know for sure that it has come from some galaxies because the metals has to be processed inside the galaxies. Now, again, the ISM and the stars retain only 20-ish% of the metals that are ever produced inside stars. So again, the question is, do all galaxies retain all of their 80% missing metals, or do some of them lose that? And how does that relate to different galactic properties? Now, when the galactic winds throw a lot of metals, they also carry a lot of thermal and kinetic energy. And depending on the initial conditions and the conditions of the pre-existing halo gas, some of the galaxies might retain some of their missing feedback, and some of them might not. So the question of these three are very much connected to each other, and we need to understand how all of these are related to individual galactic properties. The other problem is the missing accretion problem, which is connected to the neutral baryons. Now, to become a galaxy, you need to form stars. For this, you need molecular hydrogen. And for molecular hydrogen, you need atomic hydrogen in the first place. So if in an ideal world, if you assume 100% star formation efficiency, the accretion rate of H1 will be exactly the same as the star formation rate. But in the local galaxies, it is often the reverse. The star formation rate is actually larger than the H1 accretion rate. So it might seem like stars are forming out of nowhere, which is obviously unphysical. Now, the catch is that the accretion rate is often calculated inside the stellar disk, which means there might be more gas outside in the CGM, which is being actively accreted onto the disk. So we need to find the missing accretion as well with the neutral CGM. Now, CGM can be, as I said, it's a very rich multi-phase and multi-scale ecosystem. So we need to use different probes as shown here. Now, some of them probe the ionized baryons, some of them probe the neutral baryons, some probe only the baryons, some probe only the metals, or maybe both. So we need to combine as many methods as possible to get a very holistic understanding of the CGM. So I'll be starting with the neutral baryons. This is the shortest section and also the smallest contribution to the total baryons. But this is the one that actually contributes to the star formation and makes a galaxy a galaxy. So the setup of any absorption and Lyman alpha absorption is follows. You need a bright background like a quasar, and its light will pass through the galactic halo, and the hydrogen and other metals will absorb light at specific transition wavelength. And that's pretty much of it. And because of the sensitivity of Lyman alpha absorption to very low column densities, it has been traditionally used to probe the outermost CGM very efficiently. But when you are closer to the galaxy in the inner CGM, the lines are often saturated, and that gives you only the lower limits and not the actual column density. Also, the other limitation of any absorption measurements is that you need to combine many galaxy and quasar pairs to get this radial profile. So if you need a radial profile around individual galaxies, and also need not just lower limit, but actual measurements, 21 centimeter emission might be the key. So this is, recently there has been a lot of great interferometric surveys mentioned here that has given a huge spatial coverage mapping the whole CGM, and also giving great angular resolution to resolve small clumps as well as clouds. And here they find that the H1 disk is often significantly more extended than the stellar disk, both across the major and minor axis, indicating inflows and accretion happening just outside the stellar disk. But another limitation of interferometers is that because of this non-zero gap between the antennas, They are limited to a maximum angular scale, but as we know that CGM can be quite diffuse, so they cannot probe the very diffuse CGM. And also the surface brightness sensitivity is often really low. And that's where the single dish comes in, because they can do exactly what the interferometers cannot. And in the nearby galaxies where you can separate the inner and outer CGM, very deep 21 centimeter emission surveys with single dish can constrain the radial profiles as well as the velocities, again showing accretion and inflows both along major and minor axis out to almost 100 kiloparsec. So as you can see, in the innermost region, interferometers are the best. In the outermost region, it's Lyman alpha absorption. In between, single dish can bridge the gap. And this is what exactly FRBs do not probe. So in the future, when we know all of these components quite well, we can combine the dispersion measure of individual galaxies with the column densities from these neutral probes to get the total baryon budget. And why is it important? Because the relative fraction of neutral fraction actually changes with galactic mass. And for smaller galaxies, actually the neutral fraction can be quite significant. So as the contribution from FRBs start changing with mass, we might find that the neutral fraction is increasing. And in rest of the talk, I'm going to talk about, ionized baryons, and we'll start with the Milky Way. And there are multiple reasons for that. Even if you don't care about the Milky Way, as an observer, we need to separate the galactic and extragalactic contribution across many different probes, both FRBs as well as X-rays and millimeters. And secondly, because of our position in the Milky Way, it is the only galaxy where we can see the galaxy inside out. So because of this unique observing geometry, we can see a lot of things inside the CGM of Milky Way that we cannot see in other galaxies. But other galaxies will also have similar contribution unless Milky Way is very special. So we can project a lot of things from our understanding of the Milky Way for external galaxies. I'll start with X-ray emission because it has been the most traditional method to probe the ionized hot gas. And one of the main advantage of any emission is that it's a direct measurement. If you want to map a galaxy, you target that galaxy and get the map. And also it gives you a very large spatial coverage and not just a pencil beam. But also it has its own limitation. Emissions are always biased to temperature and density ranges where the emissivity is very high and also the density is very high. So out of the whole density temperature parameter space, we always probe a subset of the density and temperature. And that's why we need multiple probes. Now, very brief and quick history of the hot galactic halo. It was first predicted in one of the visionary papers in 1956. And it took almost 4 decades to detect this hot gas and separate from the interstellar medium, which is much brighter and denser. But Rosette gave a very crude estimate of density and temperatures because of its broadband photon counters. And in the next 2-3 decades, the CCDs have enabled the detailed spectroscopy and measured the temperature and emission measure or the density square of the hot galactic halo. Now, the main challenge in detecting the hot galactic halo is not the signal itself, it's the background, which contributes to more than 90% of the photons. And talking about the background itself is going to be a separate talk, so I'm not going to that details, but it is composed of many different components. Some varies across the sky, some varies with time, some both, some varies across the detector plane, and some of the spectral shapes are not well understood because we don't know the physics well, and so on. So it is a very complicated way to do spectroscopic modeling of all these components together. But if you just focus on the emission from the CGM itself, it looks something like this green line. And there are 2 components. One is these 2 bumps coming from oxygen 7 and 8, oxygen left with only 2 and 1 electrons. And that emission measure, the intensity ratios give you the temperature, and the underlying continuum gives us the emission measure. So the summary roughly until 2020-ish was that 1, the temperature is roughly constant across the sky, consistent with virial temperature, exactly what we expect. And the emission measure, unlike what we expect, it varies by an order of magnitude across the sky, and it does not have any correlation with the galactic coordinates. So on a 0th level, since it is intuitively comforting, you can think of the hot galactic halo like an ellipsoid or something, but in reality, it's more like a cosmic amoeba. It's very anisotropic. And this was just the detection phase, assuming that oxygen 7 and 8 comes from the same temperature, because at a 0th level, you have to assume something. Now that we have deeper data and have a better understanding of the soft foreground, we now know that oxygen 7 and 8 do not come from the same phase. There is actually a supervirial phase that's 10 times hotter than the virial phase. And it was first detected with XMM and then follow up with Suzaku and Helosat and Rosetta. Multiple galaxies have followed up across the sky. And now the consensus has changed. So the virial gas is there as it was, but there is also a hotter phase, which is consistently an order of magnitude fainter than the virial phase. And that's why it was so harder to detect previously. So if you want to visualize, it will look something like that. And further chemical tagging shows that this gas is dominated by the iron. Now, virial phase is dominated by oxygen, and the supervirial phase is dominated by iron. And as we all know, oxygen and iron comes from different sources of feedback. So what it gives us is a cosmic clock to probe the feedback history of Milky Way located at different locations in the CGM. And this is just in the emission. What if we try to probe the same gas in absorption? Now, X-ray absorption is a very powerful but somewhat underrated probe. Its principles are pretty much like optical and UV, except that now you need the quasars to be extra bright. And unlike X-ray emission, it does not have density or emissivity bias. So it allows you to probe the whole density, temperature, space, unlike emission. But again, just like FRBs, you have pencil beams, so you have limited spatial coverage. Now, again, in the first 2 decades of gratings with Chandra and XMM, people could probe the oxygen 7 and 8, the same things you saw in emission, but now in absorption. And here we could get the column densities, and from column density ratios, we could also get the absorption temperature. So the summary was pretty simple. You get the temperature from emission and absorption. They are also same. Great. And also the column density varies by an order of magnitude, same as emission measure, but a direction with high emission measure doesn't correlate with a direction with high column density. So you can think of a spherical halo for, at a 0th level, but again, it's like a cosmic amoeba again in absorption. And if you want to combine emission and absorption, it looks something like this. The advantage of combining emission and absorption is that you don't need to assume a density profile. Emission is density square, absorption is density. So if you combine them, you can empirically break the degeneracy between density and path length. And that shows that the path length is actually larger than 200 kiloparsec. So the hot halo is truly extended. And also for a reasonable assumption of the metallicity, it gives a pretty large mass sufficient to account for the missing galactic baryons. But this was again assuming all oxygen 7 and 8 comes from the same phase. Now again, if we have deeper data, and if we try to probe other metals in addition to oxygen, what do we see? Again, initially people probed only the smaller wavelength range shown here with the green window. And if you just expand your wavelength range, you start seeing a lot of metals at an unexpected strength, and that gives rise to additional temperature. So there are many extreme ionization lines like neon 10, magnesium 12, silicon 14, sulfur 16, that are not expected in a galaxy like the Milky Way. And unlike the emission phase, which was fainter, here the column density of the supervirial phase is actually larger, which is quite interesting. And just to make things worse, here people didn't really detect any iron lines. So the gas is truly alpha enhanced. And if you remember from just 2 slides back, the gas, supervirial gas in emission is enriched by iron. The gas in supervirial in absorption lacks iron. Now, iron cannot be present and absent in the same time, in the same phase, which means despite being the same temperature, the supervirial gas in emission and absorption are actually probing 2 different phases. And just for the sake of completeness, I should also mention the lower temperature phases. At a 0th level, you can ignore this because it contributes less than 15% to the total baryons and the dispersion measure. But again, depending on the precision you want to reach, you should include this. But just remember that the column densities are again very anisotropic. There is no correlation with galactic coordinates. So if we try to combine all of these phases together, what we should kind of visualize as Milky Way CGM is like this. There is no smooth distribution as a spherical halo or an ellipse. So how do we connect these to the FRBs? Well, first of all, you need to separate the contribution of Milky Way both in ISM and the CGM. And if we try to combine these measurements from X-ray and UVs, we see something that is roughly consistent with the direct estimates from local FRBs, where the contribution from IGM can be ignored, at least at a 0th level. So roughly speaking, everything is consistent at the median level, but this is log scale. So all the discrepancies look much smaller than they actually are. But if you look really carefully, once you correct for all the saturation and ionization correction, the distribution is quite skewed. So the mean is a factor of 3 larger than the median. And also the scatter is, more than 2 orders of magnitude. So if you assume a spherical halo, you might actually over or underestimate the contribution from Milky Way, and that might create an additional scatter in the extragalactic dispersion measure. So this is something we should be more careful about. And also just to clarify, in the left plot, there is no inclusion of the dispersion measure of the supervirial emitting and absorbing phases. So the sheer existence of these phases naturally increases the total dispersion measure, which we should talk about that in the future. Now, quickly moving on to the external galaxies. Here, most of the things are what we can do in the future because we don't have much observational evidence. So again, in X-ray emission, since detecting the X-ray emission even from Milky Way CGM was challenging, it is even more challenging for external galaxies. There is literally one external galaxy where the CGM, hot extended CGM has been detected from 30 to 200 kiloparsec. And just to clarify how difficult it is, if you can follow the cursor, these gray circles are the total data. This dashed curve is the total background, and this tiny excess in the data compared to the total extra background is the evidence of the detection from an external galaxy. So this is just one galaxy. One is small, but still much better than 0. And this is qualitatively consistent with the stacking measurement of, I think, 50,000-ish galaxies from eROSITA, which is shown here in 3 different mass bins. And for a reasonable assumption of a metallicity, in both cases, the mass of the hot CGM is large enough to account for the missing galactic variance. And just to clarify, all of these galaxies do not host an active nucleus. So if the galaxy has an AGN, it is naturally going to be much biased toward stronger galactic feedback. And same as emission, we also have X-ray absorption. And here, so far, there are just 2 evidence of the detection of hot CGM toward 2 X-ray bright quasars. And the redshift is confirmed by both oxygen 7 and oxygen 6, which is oxygen with 3 electrons in UV. And in both cases, these are at exactly the same redshift. And in both cases, there are basically 2 takeaways. One is that the column density is really large. So the implied mass is also quite large, which can account for the missing galactic variance, at least for these 2 galaxies. And also in both cases, the impact parameter is large. It's more than 100 kiloparsec, which means oxygen 7, which is a highly ionized oxygen, which has most likely come from the galaxy. It has managed to reach a distance of 100 kiloparsec, unambiguously telling us that the galactic wind can be strong enough to throw the metals at a distance of 100 kiloparsec or more. And here, as I have been talking about X-rays, you can already see that everything is connected to metals and metallicity weighted. So if we want to combine FRBs and X-ray measurements, we can actually constrain the absolute metallicities, both with X-ray emission and X-ray absorption, although the bias in metallicities are slightly different. Now, lastly, about the SZ effect, which can be a true competitor to the FRBs because both trace the total ionized variance. I'm going to talk primarily about thermal SZ effect because currently we cannot constrain the kinetic SZ at the CGM level. It's mostly the massive groups and cluster levels, but in future we'll be able to constrain that. So a very brief and quick introduction. The emission from CMB, that's like this dashed line, a pure black body. As the photons from the CMB pass through any ionized plasma, it is inverse Compton squared. So the observed spectrum is like this dashed curve. It is distorted. And this difference between intensities, if you plot that as a function of frequency, you get this blue curve, which is the measure of thermal pressure or thermal energy of the intervening plasma. And the secondary effect is kinetic SZ, but as I said, it's an order of magnitude weaker. And it might be very hard to see here. That just emphasizes why it's so weak. And one of the main advantages of SZ is that it's redshift independent. None of the limitations of X-ray emission or absorption are present in SZ, but one main limitation is that individual galaxies are not detectable now or even in the next 2 decades. So we have to combine a lot of galaxy catalogs with, Compton Y map from millimeter to get the average estimate. Now, if you have a bunch of galaxy catalog and Compton Y map, you can just randomly stack a lot of things and get some signal. But the interpretation of stacking is very challenging and non-trivial if the galaxy properties are very inhomogeneous. So we have to be very careful about target selections. And all of the papers mentioned here are, producing very different results because of different galaxy selection. So once you have your proper galaxy selection and cleaned Y map, you get a thermal pressure profile shown here. And the fact that these black points are in excess with this green patch showing the TSZ background shows an unambiguous detection of the TSZ effect in the CGM, independent of how you model the one halo term or the signal. And once you repeat it for many mass bins, you get the thermal energy as a function of mass. And as you can see, the best fit, the red line, is very different from what you expect from groups or clusters. So the non-gravitational aspects like the feedback and cooling or feeding, and the non-thermal properties are very different in galaxies, unlike their massive counterparts. So galaxies are not just a miniature of groups and clusters. They have their own identities. And even if you are more careful, you can see the trend is more like a broken power law and not just a power law. This is something never found in more massive halos, and it is probably because mass is no more the best and only descriptor of galactic halos. At a given mass, there might be more galactic properties giving different thermal energies. And one of the reasons could be star-forming and quiescent galaxies, which have very different dominant feedback mechanism, one being dominated by Aegean feedback, one dominated by stellar feedback. So seems like the star-forming and quiescent galaxies actually have very different, thermal energy versus mass relations. And there are primarily 2 ways we can connect these with FRBs. One is the temperature, because in everything, in thermal SZ, it is dominated by the hotter gas. So by combining that with FRBs, we can constrain the volume average temperature of the CGM. And in future, when we can constrain the kinetic SZ, although mathematically kinetic SZ and FRBs probe exactly the same thing, they're actually not the same. Because one, KSZ is direct, because you can pre-select which galaxies you are going to stack on. But in case of FRBs, you don't have any control of what is intervening the FRB sightline. And secondly, KSZ gives you a map. So it's a volume average estimate, always dominated by the hotter gas that has larger volume filling factor. The power of FRB is that it's a pencil beam. So it is not biased by just the hotter gas, it's all the ionized gas together. And depending on your science perspective, it could be a pro or con, because it is also very susceptible to density fluctuations. So if we can combine KSZ and FRBs, although they probe identically the same thing, we can get a much better understanding of the ionized gas. Now, this is the last slide on how the simulations are doing. Short answer, not very well. Left, you can see, it is very comforting to see that the stacking and individual measurements are consistent with each other, but there is 2 orders of magnitude scatter in the prediction of X-ray luminosity among these 3 simulations. If you start adding more simulations and idealized simulations, it will just look worse, so I didn't include them. And similarly, in millimeter, all the simulations are predicting larger thermal energy than the data. What is more interesting is the case of SIMBA. It underpredicts the X-ray emission, but overpredicts the thermal energy. And that tells us that we should compare simulations with multiple tracers to see where they're going wrong. And that also means if you're trying to calibrate your observations with a particular simulation, that can be quite dangerous. And overall, the talk has been based on with an optimistic expectation that FRBs can actually probe the CGM. And the short answer is yes, the FRB sightlines intersecting the CGM are systematically showing larger dispersion measure than the sightlines not intersecting. But obviously, we need a lot more FRBs, 3D localized, especially nearby FRBs in the future. So I'll leave you with this slide just saying that FRBs are very sensitive to diffuse plasma, but since they do not have any spectroscopic handle, we need to combine as many probes as possible to get a better constraint on different, different constraint on the different components, and also get a holistic understanding of the multi-phase CGM across phases and across spatial scales. So I will leave you with this and take questions. Thank you for listening.
Let's talk questions.
Yeah, hi, it's Paulson Salmons here. So I had a question regarding your the cosmic amoeba structure that you showed for the Milky Way. And I just wondered if basically any of those like asymmetric or like inhomogeneous structures that you see can be traced back to certain events in the Milky Way's history. Do you see them correlated with like positions of compact objects that went supernova, or is there kind of implicit information that we can get from that?
We are currently working on that. First, we try to rule things out, what it is not correlated with, because we are trying to probe a much larger scales. And the galactic feedback, a lot of galactic feedbacks are much local. And how it propagates through the CGM depends both on the initial condition of the galactic feedback as well as the pre-existing halo gas. So first, we are trying to see all the possible correlations that are not possible. For example, it's not correlated with the position of M31, which means we are not seeing systematically higher dispersion measure closer to M31, which is quite interesting. The second thing is that we are trying to constrain things with the stellar halo. For most of the time, we talk about galaxies thinking of the stellar disk, but there is also a stellar halo, which is almost extended out to 50 kiloparsec, which is quite large, especially along the minor axis. If it is 50 kiloparsec, it's quite large. And we are trying to see if the runaway stars in the stellar halo can contribute to this. The problem is that it can contribute toward a few cyclines, but since we are seeing this anisotropy across the sky, the population of runaway stars has to be much larger, or the metal loading factor has to be unphysically high. So right now we don't have an answer, but yeah, those are the directions we are probing.
Cool, thanks.
This is an online question from Sunil. Do you want to unmute?
Yeah. Hi. Hi, Sanskriti. Nice to hear from you again. I hope you're doing well. And I had a question, and I guess like two related questions. So you mentioned that the emission measure changes by an order of magnitude in the Milky Way, depending on the sightline that you're looking at. But you also mentioned that there is significant error coming from the modeling of the foreground or like other components that could be contributing. I was just wondering whether that order of magnitude change is significant, and if so, how much? And the related question was that do you see evidence for this order of magnitude change when you're looking at stacks of the X-ray emission? So do you see, for instance, like a large scatter in the X-ray emission from the CGM of different galaxies?
Okay, yeah, thank you, Sunil. So there are two questions. First is related to the Milky Way. Yeah, that's a great question. So the thing is, we tried, I think, 6 different foreground models, and that naturally changes the temperature and emission measure of the CGM of the Milky Way. But those changes are within a factor of a few. It's like maximum difference is a factor of 3, I think. So if you use different foreground models, the emission measure of the Milky Way will obviously change across all directions. But qualitatively, the order of magnitude scatter will still remain, but the exact values will change. Does that answer the first question?
Yes, yes, it is. Thank you.
Yeah, okay. Yeah, and for the second question, yes, for the SZ, yeah, that's also a great question. The problem is that we do not have any way to know the azimuthal distribution right now for the galaxies we are probing. So in case of external galaxies, in SZ, we are stacking over, say, 1 million galaxies. And many of them are at a larger redshift where we don't know the position angle. So what we are just getting...
sorry to interrupt, but I was wondering about the eRosita X-ray stacks.
Oh, in eRosita, I think, so there I do not know of any azimuthal analysis. They are just, again, getting the, azimuthal average of radial profile. So if you take the scatter across galaxies, that's just a factor of a few. But the, order of magnitude scatter in emission measure that we see in the Milky Way, that's an azimuthal scatter. So if you have the azimuthal profile for external galaxies, then only we can see. But right now we are just getting the azimuthal average. So across galaxies, it doesn't show the scatter. And we do not know yet if that azimuthal scatter is, there in those individual galaxies. We need to know their position angle correctly to rotate all the maps to correct position angle. Because if you don't know the position angle, you are just stacking across many different azimuthal angles. So right now, we cannot do that either in X-ray or millimeter. In future, when the X-ray and millimeter surveys are more sensitive and stacking over a smaller number of galaxies are possible, we can do that for more nearby galaxies, say less than 0.1 or something, where we know the position angle. So we can rotate the map at correct angles and then get the azimuthal profiles. Yeah.
Thank you.
So does that answer your question?
Yes, thank you.
Okay, I think it's time for coffee. So if there are more questions, please head to the speakers outside and let's thank you.
Okay, I'll mute it now.
Thank you.
What? Is Yagmin coming?
Oh no. Mason, is she definitely in person? Is the speaker in person? Oh, you've seen that? Okay. I was just like, I can't. Can you point her out? You know, is she in the room right now? Yeah. Oh, yeah. Awesome. This is great. Oh, you recognize her as well?
Yeah, she picked up the next one.
No, that's just no, this is fun. Where's that? Maybe she's in the bathroom.
We give 20 seconds and then we do first.
Yeah.
Oh man, they're gonna do an ABCD joke.
No. Yeah, not in. No, okay.
I'll be prepared to change. But I'll wait. Yeah, let's just let him make some others. Yeah.
But if it's kind of up on the screen, you can not be sat down.
Right.
Yeah. Okay.
Just in case.
Yeah, no, 11 minutes, I'll be like, yeah, I'll give you 2 minutes. Yeah, good? Yeah, cool, okay. Fine. I mean, you get 15 minutes in total. I just, yeah. Yeah. Yeah, that's absolutely fine. Yeah, I like to use them notes, let's catch up.
Oh, she's here.
Oh, oh no, but we didn't know you were sat down. Oh, okay. Okay, you go first. Okay. No. Yeah.
Sorry, there's too many people in the room.
Yeah, we just didn't too much.
Where did it go?
Oh, it was down. Yeah.
Thank you.
Okay.
No,
that's still.
Should be good. What the? Oh. Say it again.
Oh, magic. Genius. Go back to the server. Thanks. That's good. That was great. Thank you. Okay, welcome everyone to the last session of today. So we're going to have overview talks from 8 different telescope / collaborations. I just want to mention there were 2 things, but I can't remember the second one. But okay, so it's a catch box, not a drop box. So we're going to implement some new rules. That wasn't me who came up with that. Someone else acted and I thought that was funny. So please don't throw the catch box the whole length of the theater. We're going to do halfway at a time. I think that is far more reasonable. As fun as it may be, we would like it not to break. And that also, please don't shy away from it. So if you're only throwing it halfway, the throw isn't going to be as hard. it is not going to hurt you. So please catch it. I know none of us are like pro baseball players. That's why we're here. And so there was also another thing. Oh, yes, it doesn't connect to the speakers. So when you're asking your question, can you make sure you really project your voice, or ask the speaker, like the presenter, to repeat your question so everyone else can hear? Does that sound good by everyone? Cool. Yes. Awesome. Like the thumbs up. Thank you. So yeah, we'll now start with our first speaker of this session. Wang-Ming Wang will be talking about the ASCAP craft/Krakow system, and I'll give you a 2-minute warning. Is that all right?
Yeah, thank you. Okay, thanks everyone. So I'm Yuanming Wang, and I'm a postdoc working at the Sweden University. So today I'm going to introduce the ASCAP Craft-Krakow survey on behalf of the Craft-Krakow collaboration. The telescope we are using is ASCAP, which is a wide field survey telescope located in Western Australia. Specifically, it's in MRO Observatory. And ASCAP have 36 antennas, which arranged in a way to provide good imaging capability and also can do precise localization. So ASCAP also confirm 36 simultaneously overlapping beams at the same time. To combine all these 36 beams, we're able to get a larger field of view, which is about 30 square degree. So combine all these advantages with good localization precision, large field of view, and the relatively high sensitivity. ASCAP is very good for to conduct untargeted transient search. We started the craft incoherent sum ICS survey from 2018. And the survey is to find millisecond bursts in real time with precise localization. So here is a workflow. From each digital beamformer, we get the total power summed over polarization and average them into 1 megahertz and 1 millisecond resolution. Because we have 36 beams, so we are getting 36 intensity time series data streams from the beamformer, from each digital beamformer, and conduct the FRB search. We will get the search pipeline will provide a list of candidates, and we will use this list of candidates to triggering the raw data voltage downloads. The voltage have 1 nanosecond time resolution and full polarization. Because ASCAP can save about 3-second buffers, that means all the search needs to be finished within 3 seconds. After we have the voltages, we have the CDB pipeline to do the calibration and imaging and then localize the FRB. Once we have the FRB localization, we will conduct the optical and infrared follow-up using VLT, Gemini, and CAC observation to identify the host galaxy and study the host galaxy properties. So Craft and Krakow survey is fully commensurate with ASCAP other large surveys, which means we generally do not have a lot of control of where we are pointing. Here is the exposure map of the Craft ICS survey. You can see some field has been longer monitoring than the other field. For example, the ASCAP bandpass calibrator field, 1934, we observed it more than 1,000 hours and found 1 FRB in that field. And until the end of 2023, we have total about 15,000 hours observation. And the FRB detection rate is about 0.05 FRB per day. So ASCAP have 3 different frequencies. And in low frequency, mid, and high, we are a bit more efficient in a low frequency, which is about 900 megahertz compared to the other frequency. So we'll also highlight some craft science. Since we're able to localize the FRB, the first time ASCAP, so ASCAP localized the first one of FRBs, and which is at a massive galaxy, which is quite different from the first repeating FRB 121102, which is in a dwarf galaxy. And after that, we started accumulate more and more localized FRB, and we provide the first large sample of localized FRB. So we can use them to study their host galaxy properties, and we found the majority of FRBs are from star-forming galaxies and trace the star-forming maze sequence. We can also use these localized FRBs to study the intergalactic medium or solving the missing barons problem as mentioned in previous talk. So to enable to do more useful science on the host galaxy side and also the extragalactic matter side, we want to find more FRBs. That's why we start the Krakow survey, which is the ASCAP Craft coherent upgrade. So Krakow started commissioning from 2023, which is an image plan transient search. So we are doing coherent image. That means we will improve the sensitivity by 5 times, which is quite good. So again, for Krakow survey, from the digital beamformer, instead of getting simple intensity time domain time series data, we are getting the correlated visibilities and average them into 1 megahertz and design time resolution. So we are using the 30 inner antennas of ASCAP, and also we have 288 frequency channels. That will give us about 130,000 measurement data points per time step. And we'll send all this data for pre-processing and then send them into the search pipeline. The data size will be further increased during the search pipeline because we are using a range of de-dispersion trials and boxcar weights trials. And also we grid the data into a fixed spatial size, and then we perform the fast Fourier transform, convert them into image. So for the search pipeline, all of this process, the data volume is about 20 terabytes per second. That is the data we need to deal with. And from that data volume, we roughly get 10 to the 7 raw candidates per day, which is a huge number, and we can't inspect them thoroughly. That's why we developed a candidate pipeline. So the candidate pipeline will do the clustering to group similar candidates and do the basic classification and filtering all the known objects. After the candidates pipeline, we will get less than 10 final candidates per day, which is pretty good. So for that final candidates, again, we will use them to triggering the raw data voltage, which is a similar, which is the same system we're using the Craft ICS survey. And the voltage data, again, it is 1 nanosecond and full polarization. So we save the 1-bit voltage data. That means ASCAP can save about 12 seconds in the data in buffers. That means all the pre-processing, search pipeline, and candidate pipeline needs to be finished within 12 seconds to enable the real-time triggering, which is a lot of data. And after we have the voltages, again, we will use the CDB pipeline in, as what we used before in the Craft ICS system to do the calibration, imaging, and localization, and perform the optical infrared follow-up to identify the host galaxy and study their properties. So until last month, the Krakow commissioning, totally we have more than 6,000 hours. And the FRB detection rate is about 0.14 FRB per day. And again, similar to Craft survey, Krakow is also fully commensurate with other ASCAP large surveys. So we have some fields which we have the longer integration time. And also we have our own failure time. So that is time, that is the field defined by the Krakow Craft team and can be observed during the between of the large observations. So we have different phases in the commissioning. So before 2024 May, we are in the offline mode, running in 110 millisecond and 14 millisecond mode. After 2024 May, we are running in real-time mode, which will enable us to do to trigger the downloading of the voltage data. And in the real-time mode, we are running in 14 millisecond mode and 3 millisecond mode. The discovery rate of FRB compared to the Craft ICS survey is improved by a factor of 3, which is good, but this is still lower than what we expected. So we are still working on technical improvements. With Krakow FRBs, so here is the plot showing the DM of excluding the galactic component, and also the redshift of all the ICS and Krakow FRBs found to date. So we found quite a lot of FRB in this redshift, about less than 1. And this will provide us quite good cosmological constraints. And we also found the repeating FRBs. We found 6 pulses over 1 minute. And here is the super scattered FRB. We found the weight is about 1 second, so very wide. And our modeling showing this is scattered by its host galaxy. Krakow can also do some galactic science. We found about 30 rotating radio transients. So here is the comparison between Krakow RS and the non-RS population. So we can see the Krakow RS in general have the lower DM compared to the RS population, which is not unexpected as image plane search will not limited by the lower DM cut. We also found a pulsar, which is about 40 seconds rotation period, so very long compared to the normal pulsar, which is less than 10 seconds. We also found other long period transients. We have found the 44 minutes long period transients with X-ray emission has been first detected. We also found the 6.5 hour long period transients with interpulse has been detected. Except all these astronomical objects, we also detect a nanosecond pulse from the dead satellite. And the DM of that signal is very near to 0. So that means in the normal time domain search, this is RFI for sure. All this work because of the team collaboration across of the world. So we have a different people working on different parts, working on operation, commissioning, post-processing analysis, and also multi-wavelength observation. So you will be hearing the talks from some of the people in this week and hope you can enjoy it. So this is a summary of the ASCAP craft Krakow. We localize the first one-off FRB, and we provide a large sample of localized FRB to use them to study the host galaxy properties and intergalactic medium. We are currently upgrading to Krakow system with improved sensitivity. That means we will find more FRBs. And Krakow can also discover the galactic objects like RS, long period transients, and we're using them to study the galactic science. I'll stop here and thank you.
Any questions? Definitely silence. Who has the catch? Oh, ball.
Yeah. Hi, it's Matt Tubbs. I'm wondering if you can speculate on the lower than expected improvement through Krakow. What's causing that? And certainly you must be sensitive to a different underlying population of FRBs. And so I wonder to what extent that can play a role.
Yeah, that's a very good question. So from the image, so Krakow is doing the image plan search. And the image plan search, the first, as what I mentioned before, we are not limited by the DM card. That's why we can find the galactic object and even the satellite. And the second is from the imaging plan detection. So if we are using the time resolution, like for example, 40 milliseconds or even longer, so we're able to detect the wider object, no matter it is FRB or the other object. So that is another advantage compared to the other survey, but it also depends on what time resolution we are using in the current survey.
We have an online question, so pass it over if I'm fasting.
I have this question for you. In one of your plots, you showed the pulse width is 1 second. Then for 1 second, because normally is millisecond, is not the large pulse width.
Sorry, are you talking about the super scattered FRB?
Yeah, the one of the last plot you showed.
Oh yes. So
what is the?
I don't know how to go back.
Yeah.
Here.
I think this one.
This plot, right?
Yeah. What is energy? And then here we have 1 second. Yeah. What is? Do you have any value for energy or luminosity? For example?
Sorry, I cannot think about the number. So if you just send a message in the Slack, I think I and my other colleague Yosha, who is leading this work, will have the further discussion.
Yeah, because mostly that's the pulse width is millisecond. 1 second is very interesting. Thank you very much. Anyways, thank you.
Thanks.
Cool. I think we will move on to our next talk. So let's thank the speaker again. So our next speaker is Sujin Yi, talking on behalf of the FIRST collaboration. And I'll give you a 2-minute warning.
Can you hear me? Okay. Hi everyone, I'm Sujin Yi, a postdoc from in Asia in Taiwan, and it's a great pleasure to introduce our first instrument alongside the great instruments for FRBs. And first is focused on the detecting nearby FRBs, which we believe hold a great potential for unlocking the physics of FRBs. So let me start from highlighting the 3 key challenges from the previous FRB surveys: the low detection probability and the limited localization capability, which the CHIME and the DSA or FS is now already giving a dramatic increase of the FRB detection rate and also increased rate of the localization sources. But because of the limited field of view, we still have kind of missing a lot of repeaters or detectable FRBs, and also missing the host galaxies for the single events. And also the known FRBs are quite far, I think very far, to perform the multi-messenger observation, especially in optical and X-ray telescope. So it also hinders the redshift measurement for all of that. So this burst is launched to solve, to answer these challenges. So it is a dedicated FRB instruments initiated in Taiwan and also expanding to East Asia right now. So we aim to detect the FRBs and repeaters with a very wide field of view, and also the localized it promptly right after the detection, and also focus on the nearby sources to make it possible to perform the multi-messenger follow-ups. So before explaining the specs of the burst, I'd like to highlight the importance of the nearby FRBs. So first, so far the host galaxies and the source environment is not, the contribution of the source and the host environment is highly poorly constrained. So how can I say? So if the FRB is closer to us, it's much easier to separate out the DM contribution of the IGM. So we assume that we believe that the more nearby FRBs can help to constrain and also refine the models for the high redshift FRBs. So I have a jet lag, so I've just started slightly sleepy and try to make it awake for myself. And also, as you know, that for the thinking of the SGR 1935, where we found the X-ray counterparts because it is nearby. And if we have more nearby sources, it is more possible to detect the multi-messenger signals. And also nearby FRBs have better possibility to detect the follow-up burst and the follow-up pulses probably, so we can increase the rate of the repeaters. So let me move on to the burst specs. So the burst wide field of view can be provided by our LPDA array that covers from 300 to 800 megahertz. So the antennas on the bottom is the 3 types that we are using now. And the third one, I can use my mouse cursor here. But the third one with the black one is the one that we are using right now for the main station. So this is sensitive above 400 megahertz. So now we are switching our antennas from black commercial antennas to the custom built antennas, which is on the first one, to reach down to the 300 megahertz. And the middle one is also our own design, which has a better durability and weather resistance, and also being used in one of our outrigger stations. So on the right side, we are comparing our field of view with CHIME. So at least we have at least 20 times larger than field of view than CHIME, and it could be kind of trade-off. So we're giving up some sensitivity with exchange for the wide field of view, so we can cover the 1/4 of the sky at once. So, and our beamform architecture allows us to effectively scan our wide field of view. So this figure shows our current beamform distributions. So now we are using 256 antennas at the main station by forming the 16 by 16 beams. And the direct east-west beams are formed on FPGA, and the data will be transferred to our CPU servers to form the north-south beams. And both of them are conducted in real time. So the current beam size of our at the main station is 2.5 times 5 square degree, and we are planning to shrink this to have to better with higher beam density by increasing the number of the antennas. And for each beam, we perform the real-time pulse search at the main station where we have the high sensitivity. And we use the bonsai for pulse search, which is developed by the Chime team with a 1 millisecond time resolution and 16K frequency channels across 400 frequency band. Our DM search range extends to 1900 parsec per cubic centimeter, which is exceeding our original goal of 1000. So on the right, we are showing the real-time detection of the crack giant pulse in the DM time plot, and the bottom one is the zoom-in plot. So because the data rate is high, which is about 200 gigabytes per second from 256 antennas, we are not saving out the old data, but each station have a 40-second ring buffer. So once the main station got a detection of the burst or FRB targets, we sent out the triggers immediately to all the outrigger stations, and each station will gonna dump both baseband and the intensity data for that, depending on the DM, which will be used for the VLBI localizations. So the main station is located in the Fusan Botanical Garden in northern Taiwan, and we are now operating 256 antennas and a continuous real-time pulse search at the station. So we are also planning to double up the antenna array to 512 in a few months. So we can have a better sensitivity and also cover wider field in the sky. And for the outrigger station in Taiwan, we are planning to, and we already have and also planning to have more outrigger stations. So 2 of them in the central Taiwan and also on the Green Island, they are already operational. And also we have completed site surveys in some of the places in Taiwan for future expansion sites, which is marked with a blue color. So currently the longest operational baseline of the burst is 230 kilometer, which gives us a 0.7 arc-second precision at 400 megahertz. And to increase our localization precision, we also established outrigger station on the wall in Hawaii and Japan and India. So they already have some of the burst antennas. And also, so from burst Taiwan and Hawaii, we can achieve the precision of 0.02 arc-second precision in east-west baseline. And you may notice that they are basically located in the east-west baseline. So to have the security north-south baseline, we are now settling up a site in South Korea. And also we visited Mongolia just a few days ago to have for the RFI survey and got a very promising results and found a good place to put our antennas. And also together with NARID, we also exploring some candidate sites around the TNRT. And the burst antennas are simple and cost effective and really easy to deploy. So we are welcoming any partners who would like to host our stations for VLBI. So from now, for the remaining time, I'd like to show our performance. And this is the 16 by 16 pixel sky view from the burst. So on the left side, we are showing the sun is moving in the third row from the bottom. And it is moving from east to west. And we can also see some clear visible side lobe. And on the right side, it is Cygnus A plus galactic plane. So if you see in the middle, is moving from left to right, is Cygnus A. And also we can see that the galactic plane moving diagonally in the frame. So using the radio calibrators, including the Cygnus A and the Tau A, we measure our SEFD is around 12 kilojansky, which is twice higher than our original expectation. And we suspect that this might be related to the antenna degradation because we put that antenna for years. So, and also possibly some combination of factors that we are now investigating. So on the right side, it is showing the detection rate of the many facilities. And the burst 256 was calculated from our initial design. So the actual burst at this moment is actually located in the right side on the lower sensitivity part. But we are now, that is for now, but we are now replacing our antennas with a higher gain models. So gradually improving the SCFD, and also plan to expand the array size to twice, and also optimizing the beamforming. So we expect that we can reduce, make the burst location to come back to the original or have better places. So, and the real-time search status is ongoing well. So we started the full beam search from mid-May, and to increase the detection rate, we are now shrinking our field of view to 3,000 square degree. So, and detecting the, every day we are detecting the single pulses from 0329 and also some of the clutch ion pulses. So on the bottom, we are showing the plot, which shows the beam map and the DM time plot and the dispersed waterfall, which is generated right after the trigger is sent. So we can monitor our triggers right after we detect some, the first main station detects some pulse or FRB signals. And the localization test is also ongoing. So this is showing the cross correlations of the many single pulses from 0329. And I'm sorry that I didn't show the clutch ion pulse cross correlation results here. But what we found so far is that a residual delay from the single pulses from 0329, the residual delay is consistent with our ionospheric expectation within 2 nanoseconds. And we are trying to improve this more with GNSS data. And also we recently found that working on the improvement of the cross correlation SNR by re-beamforming the clutch ions data. So there will be a lot of updates from in the perspective of VLBI, so please stay tuned for this. So I think I'm almost done. So burst is unique and quite interesting design. So we believe that burst can answer some of the key questions for FRBs, such as whether all FRBs are repeaters, and also where there will be more multi-messenger counterparts of FRB, and the third, the contribution of the source and the host environment, host galaxies for their DM. So this is not only from the burst, but it requires a close collaborations with high sensitivity follow-up instruments that many of you are involved in. So we are really welcoming, we are happy to discuss and collaborate all together. So please reach out, feel free to reach out us if you think that you have something interesting to work with first. So we have many things ongoing, and I think I covered some of them. But there are more on the way, including the 2 polarization recordings and also machine learning classifications for fast FRB determinations. So please allow me to skip the details, but I wanted to mention that everything for burst is working pretty well. So, but we haven't got the FRB detection yet, but we have a giant pulse and a single pulse detection. So the FRB detection might be very soon. So hopefully during this conference. So if I get a detection, I'm gonna dance and then sing here. Yeah. So okay, so this is all for burst, and thanks for your attention, and please stay tuned for our project. Thanks a lot.
Okay, thank you so much. Do we have any, Jason? Oh, Jason.
Okay. We'll go somewhere on this
Oh. Sorry. That was a terrible throw. That was. It's got to keep going back.
Okay, sorry for asking a question. Very nice talk. Very exciting. I hope you do find an FRB sometime this week. I was wondering, so in terms of using commercial hardware, what is the difference in sensitivity compared to your custom designed hardware, and kind of like what are the lessons that you've learned from that? Like what were the main limitations?
Oh, right. The reason that we started from the commercial antennas is that we took much more time for designing our own antennas, and the price is way cheaper to use the commercial antenna. And first we thought that it is, the technical, the sensitivity SCFD of the commercial antennas is higher than the usual, but after we deployed the commercial antennas, we found that the performance is not very good compared to our expectation, and our designs, our antennas, we can reduce the cost for our antenna own designs. So
okay, yeah, maybe we can talk at the coffee break. I'm curious in more detail what specifically is the
sure.
issue.
I think
Yeah.
the chime in Canada, I suddenly forgot the name, but we are also using the similar LPD antenna around
In Algonquin, yeah.
It's Algonquin.
Yeah.
Is there any questions online? If not, Kelly has a question. There you go. Doesn't have to go far at all. Thank God.
This is Kelly Gorgie from CSIRO. Yeah, great talk. It's really exciting to see how things are progressing. I was wondering if you could comment on the potential prospects of long period transient discovery. Long period transients.
Oh, right. That's an important question. And we are also planning to see more whether we can also work on the long period transients. But as you know that our sensitivity might not be very enough to detect the single pulses from them if they are not bright enough. And also our ring buffer has a 40-second duration. So if we keep the current ring buffer size, it might be slightly tricky at this moment, but probably by saving the long-term intensity data for the candidates of the long period transient, maybe we can save out and do the offline search separately. That is one of our plans.
Great, thanks.
Cool. Any other questions can be asked on Slack. Sorry, Vicky, we're running behind. But yeah, you'll be available on Slack for any other questions. So let's thank our speaker again.
Thanks.
So our next speaker is Ziggy Finis from who's going to be talking about Chime FRB. And thank you, Mason, for big tech wisdom. You have to wear the Brittany microphone. And I'll give you a 2-minute warning. Yep. All right. It goes around you know. Yes.
Okay. Nope. This doesn't go any further, right? Oh. Okay. Well, hello everyone. Thanks to the organizers for inviting me to give this talk. It's an instrument overview on Chime FRB that you can see here in the background. And this is a talk on behalf of this wonderful team. Many of us are here at the meeting, so please come talk to us and ask all your questions about how to interpret or use the data. So Chime is located in British Columbia in the west of Canada. It's in this natural valley, and so the hills around it naturally protected from the RFI environment of the neighboring towns, which is great. You can see Chime here on the telescope. It's at the Dominion Radio Astrophysical Observatory that also hosts a range of other telescopes, so there's lots of expertise on site. We zoom in a different season. You can see one of the 4 cylinders that make up Chime. It's a unique design. It focuses light in the east-west direction, but it can basically see horizon to horizon in the north-south direction. And on this focal line here, you can see there's 256 dual polarization antennas. And so Chime is an interferometer, just sits there and looks at the sky as the Earth rotates. And because of the interferometric aspect, we can beamform in different directions by applying different delays. And Chime operates from 400 to 800 megahertz, which was originally set by the cosmology experiment that runs on the telescope as well. But it turns out to be a very unique range to look at FRB. So we probe a different population probably than the L-band surveys, where we are very sensitive to propagation effects, but not yet killed by things like scattering. And Chime recently got an upgrade. So we built these 3 extra mini chimes across North America to do VLBI. I'll talk more about that at the end of the talk. And the way that Chime does its detection is, so the instantaneous field of view that you can see here on the top right is about 200 square degrees. We make 16 channels over 16,000 channels over 400 megahertz. We search the data in about 1 millisecond time resolution, and we use 3D dispersion up to DMs of about 13,000. And so within this primary field of view of the CHIME beam, we make about 1,024 digital beams. And so it's essentially as if you're using the GBT, the Green Bank telescope, 1,024 times. So that gives you great mapping speed for detecting lots of fast radio bursts. And the other strength is that we try to be on sky 24/7 and year round. It doesn't always work because sometimes snow accumulates on the dish, for example, in winter. And in the summer, it gets really hot because it's essentially in a desert. And the other strength is because we revisit the same sky every day, that we're very good at picking up repeating sources. And so the way FRB detection works, so the voltage data coming from 1,024 antennas and 2 polarization is about 6.5 terabits per second. And this is beamformed in the correlator, and the search backend then finds the triggers. And the whole, we can of course not store all the 6.5 terabits per second 24/7 year round. And so the whole game is to recognize in real time automatically if one particular few milliseconds of data is worth saving. And we do that by sending a trigger to the 40-second ring buffer that's there to save the data. But most of the data, so we really save less than 1% of data every day, and the rest is all just immediately thrown away. And how this works with the outrigger stations, they're basically just passive receivers. They don't do any FRB searching. That's all done by the main chime station. But the outriggers all have their own buffer. They're longer than 40 seconds because they have less antennas. But they just wait there until they get a trigger from chime, and then they save the data to disk. So in terms of FRB characterization, first I want to talk a little bit about repeater identification. So the detection rate is quite high. It's about 1.5 sources per day, or it is actually measured it to be 1.5 sources per day. And at that rate, the chances of finding 2 FRBs that are closely related in sky position and DM is non-negligible. And you can see here from Amanda's paper, we developed a statistical framework to say how likely it is that 2 things are aligned by chance. And you sort of see in the heat map here that towards higher declination and at lower or sort of moderate DMs, the chances are highest of finding 2 FRBs that seem related but are not. So we worked out this framework, and we do manage to detect a lot of repeating sources. About 3% of our FRBs turns out to be repeating. And you can do nice things like monitor them. This is a figure from a recent repeater discovery catalog. And you can see the different lines here are different repeaters, and all the colored dots are detection. So we can track things like their activity over time. In terms of characterizing the intensity data, so this is the beamform data that we do the FRB search on. This is a less intensive data product to store in terms of its volume. So we have about 1 millisecond time resolution and 16,000 channels over 400 megahertz. We developed this framework to do burst fitting, which we call FitBurst. This is telescope receiver agnostic. So if you have some data from your telescope or your receiver that you'd like to fit, it should be able to work. But please reach out if you encounter any difficulties. On the left, you see an example of one FRB from chime on the left, the model that FitBurst comes up with in the middle, and then the residuals on the right. We also do flux calibration, but as you've maybe seen, if you try to use the flux influence measurements from the intensity data from chime, these flux limits should be treated as a lower limit, and that's because there's a little bit of a degeneracy because of how the beams are formed. And so this figure shows some slices through the beam model, and you can see on the left for different beams the sensitivity in the east-west direction. So you see there's some degeneracy between a brighter FRB being detected in the side lobe or a less bright FRB detected in the main lobe. And that we cannot solve with this data. And on the right in this image, you also see that this is a chromatic effect. So you see these side lobes here with the different colors, they appear at slightly different angles. So we do apply flux calibration to our intensity data, but these are the caveats. We can do a much better job if we have the voltages. And so now we managed to save the voltages also for a very significant fraction of all of our FRBs. In this case, we have 800 megasamples per second for the data. We can't do PFB inversion. Those are some technical details that I'll be happy to chat more about if you're interested. And we can do with the data is we go from about a 10 arc minute localization accuracy to about an arc minute on the sky. And you can see this in this figure, where the blue contours show the best we can do with the just with the header data, the real-time detection. And then this red cross here shows the accuracy we can get with the voltages. So it's much better, and it also solves the degeneracy between the different lobes of the sensitivity. Then we can also get to microsecond time resolution, and here's the most dramatic example that I know of, where you see the difference between the 1 millisecond time resolution on the right and the microsecond time resolution on the left. So you see much more burst structure that you can use to learn about the emission physics. We can also get the polarization information. We can get Faraday rotation as well. And now if we measure the fluxes with the voltages, then we are able to resolve the degeneracy in the position. So we know where in the sky the FRB is coming from to enough accuracy that we can actually measure the flux instead of providing a lower limit. And here you see the comparison between those fluxes from the baseband data or the voltage data on the vertical axis versus the intensity fluxes. Then another feature of CHIME is it's doing a deep main lobe survey, but it's also doing a shallow side lobe survey. And this you can see best in the figure on the right. This is showing the sensitivity of the CHIME beam as calibrated by some bright radio sources. And you see out to many tens of degrees, we're still sensitive to the sky at about a % level. And so, for example, this FRB-like burst from SDR 1935 on the left was detected 22 degrees away from the meridian because of the sensitivity still at those hour angles. And then we also found, at least we published so far, 10 of these very far side lobe FRBs. So as a population, we know these must be 500 times brighter. And so that implies they're 20 times closer on average. And so that's also setting interesting limits on the repetition rate of these FRBs because we're very often on the sky in the side lobes. Then we try to characterize our selection effects. So one way of doing this is we do injections in our detection pipeline. And so this characterizes our sensitivity. Here you see one example from Marcus Merrifield paper showing the fluence versus the width of the injected burst. And so the color here indicates the fraction of injected burst that we recover. And so you see we lose a lot of sensitivity towards lower fluences and higher widths. We also know there's some chromatic beam effects, especially in our intensity data. And so this figure shows if you detect different bursts from the same repeater, in this case, FRB2025 we know that if we detect them outside of the main lobes, we are biased towards detecting narrower frequencies. So this is something to take into account if you want to interpret those intensity data. To be more sensitive to the broader burst and maybe to long period transients as well, we're developing now CHIME Slow. And so you'll see more talks about this later on the conference. And the next revolution we're trying to make happen is using outriggers to really zoom in on a lot of FRBs and also find host galaxies and the position within host galaxies. And so for the main CHIME station, the best we can do is probably about an arc minute, which I overlaid here roughly on the Hubble Deep Field. But now with the outriggers, we can get down to about 50 milliarc second localization. So then we can tell which of the galaxies the FRB is coming from and where in the galaxy it's coming from. So all of these telescopes are now built and operational. And just some details, because this is pedagogical day today. We're doing very sparse sampling of the UV planes because we only have 3 baselines, 3 telescopes with CHIME. And so we don't do traditional imaging as you are maybe used to from VLBI. But what we do is direct fitting of the delays to the visibility. So what we're interested in is fitting this function from the visibilities between all the baselines. And what we're after is this geometric delay tau, which gives us the position of the source on the sky. But we need to correct for the effects of the ionosphere, as Calvin already explained this morning. And so how this works in practice is, here's a nice diagram from Xion, is at each station, we first need to align the wavefronts. Then we need to do de-dispersion because FRBs are de-dispersed. And then finally, we need to identify or gate on the transient so we don't correlate the noise, but only the FRBs. And then eventually we form the visibilities on all the baselines. And then those visibilities is what we actually fit to get out this geometric delay and this delta dm term on the different baselines. And so here's an example of how this then looks like. This is for the one-off FRB that was localized with the pathfinders for the Outrigger project. So 10-meter dish in Algonquin and a dish at Greenbank. And so you can see here also the multimodal aspect of these localization that Kelvin already discussed. And so you see here what we're fitting is this, the RA, the deck, and this delta dm term for the two baselines in this case. And so that's how the localizations are produced. It's not through direct imaging. And the way we validate this is from the commissioning paper on the first Outrigger telescopes, the KKO one. We can look at many pulsars, many pulsar pulses, and we localize them. And for those pulsars, we know the localizations, and we compare our CHIME Outrigger localization with the known position, and we see that this matches in most cases, and we can characterize our uncertainty. Yeah. We've also started doing this for science, and so with one baseline, we already published or are in the process of publishing a host catalog. We can also do it for repeaters. This is for one baseline, multiple bursts, and you can see from the different positions of the day, the times of the day you detect it, you actually constrain the position a bit better. This is from using two baselines, and Maassen will talk about the first result where we use the full array. And so in terms of catalogs, what we've been doing is presenting an intensity catalog, then identifying the repeaters, then updating it with voltage data, and we'll have to think about how we do this with including the Outrigger data as well. But the second catalog of intensity data will be published very soon, hopefully. And I'll just leave you here with some thoughts about the strengths of CHIME and the outlook, and I'm happy to take any questions.
Do we have any questions? Yes, I don't know where the catch box ended up. Okay, can we bring it down like 4 rows? Sorry, I don't know. Nice. Can you please introduce yourself as well?
Hey, thanks for the really interesting talk. I'm Pawan. I'm Pawan from Swinburne Uni. I was just curious about the statistical inference about the number of repeaters that you're finding. Does that change the percentage of repeaters that you already have, especially using these clustering methods that you just mentioned about?
Yeah, so far we haven't seen any evidence for a turnover, so it seems to still remain around 2%.
Thanks.
We actually don't know. Okay, Laura, if you have us a really quick one. Okay. Oh, sorry. Everyone starts off very confidently and then realizes they can't actually.
It's Laura Spiller. I have a very quick question. So now that you have the CHIME Outriggers, do you have a policy for updating the positions of repeaters as you get better positions from the Outriggers, so that we can, for those of us who are interested in following up with, say,
yeah, we haven't really answered all those questions, but it comes back to sort of like our way of doing the data releases. I think we have to rethink a little bit how we do this going forward, and what's the best way to help the community and science forward. But if you have any ideas, please feel free to talk to us. What's useful for you?
Cool. Yeah, let's thank Ziggy again. So our next speaker is Casey Law, sorry, and he's going to be talking on behalf of DSA 110. Sorry, I had DZA in my head.
Does this sound okay? Yeah, good. Thank you. Okay, I'm Casey Law. I'm a staff scientist at Caltech. Also have an affiliation with the Owens Valley Radio Observatory, which is operated by Caltech. And I'll be presenting a summary, a technical summary of how DSA 110 works and how you can benefit from what it's done. I also helped build the real fast instrument, the VLA. It's a separate topic, and if you have questions, I can answer those separately and over coffee, perhaps. So this is meant to be really a technical summary, so I don't dive into the science so much. But I wanted to quickly give acknowledgement to everyone that worked in the project. It's a large team. It's largely based at Caltech and Overo, but it is nonetheless a large team that worked hard over several years. Two people from the science and commissioning team are Jacob Faber and Miles Sherman, both of which will be here this week, but both of which had travel delays. So I hope you will connect with them tomorrow or soon after when they arrive. Very high level summary, just to give you a sense of the punchlines of what this instrument can do and what it's all about. It's really the first purpose-built FRB localization machine. So it's an interferometer that was built for this reason. And up until recently, that was the only instrument that was purpose-built for that reason. It's located at the Owens Valley Radio Observatory, so it's about 4 hours north of Los Angeles. If you find yourself visiting Caltech or Southern California and you have a free day, it's really worth the drive. It's a beautiful part of the state and a part of the West. And what distinguishes it is really this combination of wide field of view and good localization precision. So the wide field of view is really is designed to maximize the survey discovery rate. And the localization precision of about an arc second or so is defined by the longest baseline, but it's really targeting the fact that that's the scale of a galaxy, right? We're trying to associate the FRBs to their host galaxies. And that's what this instrument was designed to do. We're centered at the L-band, so relatively small bandwidth, for modern instruments, I would say, but it is in this really productive and marginally protected band. Actually, I'll come back to that a bit later. And the search time scales range from 260 microseconds. And with the recent expansion that I'll describe, it goes up to longer time scales, up to 20 seconds. And that's the subject of this not so fast radio burst project, which Miles is developing. Much as Chime and others have been practicing, it's a real-time search triggered recording for offline analysis. So it's this sort of two-stage. You break up the problem into search and then analysis. And you can bridge that gap by having large buffers of data that hold the data while you are prospectively doing and looking for the FRB. If you find no FRB, then you just throw the data away and you move on. The timeline, this might seem like a nuance, and a little, but it actually is important to understanding where the instrument is today and where we're going. So it really started back in 2018 and was constructed in stages. So there's 2 big stages here, and you might know a lot of the science that's come out really from only the half of the array. So that's the 63 antenna array, which was built during COVID, actually, which was an ordeal in itself. The team is shown here that was doing the construction. I want to acknowledge them because they actually worked in full PPE during construction in the desert of Eastern California. They actually received a commendation from Caltech for their extraordinary service to the Institute, which is remarkable. Early science operations have been conducted over the following 2 years. So that includes basically all the publications you've seen thus far. That's the sample of 60 odd FRBs. If you go to the DSA 110 public archive, which is basically a light little webpage with a table and links to some DOIs to download data, that shows 48 of those which have been published. And there are a handful more which have not been published yet, but are undergoing some analysis. Over the last year, so 2024 essentially, we brought the array down and we were installing another set of antennas, which was essentially adding collecting area, but it also modified some aspects of the digital system. So I'll talk a bit about that. And since 2025, we've conducted science operations again with sort of the completed array. So that's something I'll dive into at the end as well. So this soon aspect here, right? DSA 2000 is a much bigger project. It's actually in many ways totally different from DSA 110. And that's something that's really going to come to dominate what we're doing at Caltech. We expect soon, or we hope soon. So I'll talk about that more over coffee as well if you're interested to learn more about that project. So thinking about how you might be interested in learning about the DSA 110, how you can use it, benefit from it. The novelties are really the fact that it was one of the first to really reduce the cost of the individual elements of the array. So maintaining this high survey capability through wide field, high sensitivity surveys. requires you to have a combination of relatively small apertures, but also very, very cheap low noise amplifiers. So that's what this little inset shows. So Sandy Weinreb is a early innovator of the field, and he developed this low amplifier as a system temperature or a temperature, receiver temperature of 7 Kelvin. It's extremely low because it's uncooled. It's really remarkable. Another distinguishing feature is that it's only steers in the elevation axis. So again, it's very cheap, but relatively simple. And it has this core plus outrigger layout, which again is quite common nowadays. But the core is what conducts the search, and the outriggers have this data recording capability and a buffer. I'll highlight here the yellow lines show the core. So there's a sort of a T, we call it. So there's a concrete pad there that existed for prior arrays and work. So the millimeter array, for example, you may know, which is a part of Karma. You know that? It's before ALMA. Anyway. So the east-west array was what was populated during the 48 antenna era. The north-south part of that array was what we built out over the 2024 year to make this 97 antenna array version of the array. And the outriggers were there the entire time. So that was part of the first phase. So all those outriggers were part of the analysis system from the first construction phase. So the real-time search system, don't need to go into a lot of detail here, but it's an FX correlator design, which is produces both beamform products for the search system. So there's 256 beams along this east-west axis, 256 beams along the north-south axis that's formed from the east-west and north-south antennas that are in that T shape. So those 512 beams go into a search system, and we have an algorithm which tries the coincidence and threshold on that stream in order to decide when we should trigger the recording of voltages that are in that buffer for all antennas. And then in parallel to that, you notice this middle arrow here that goes, there's one that goes to the NSFRB search system. So that's this roughly second scale transient search, which is an image plane search with moderate dispersion. It actually does search over dispersion space, but it's a relatively low computational intensity in that case. And then on the bottom channel there is an imaging and calibration pipeline. And that includes actually something that Jacob Faber is working on, which is an ESE scattering, stream scattering event search algorithm. So when we find things, we have a triggering process, which is that box sort of on the top right roughly. And then that's where we make the decision about sending alerts to the community and also sending data to our public archive. So the rough process here, just to go through it in detail, is the search system. That whole everything I described to you is in that top left box there in item 1. So discovery, confirmation, and analysis in that entire graph I showed before. The offline analysis relies on applying the calibration from the image plane and doing astrometry. And we use that fundamental radio catalog VLBI reference field for calculating offsets and correcting for calibration, residual calibration errors. And then we'll have an image plane that looks something like this with that T plus the outriggers. We have a kind of a weird looking PSF. And so that has these really strong low PSF low side lobe patterns. But you can clean it up pretty well. So that bottom left panel shows how it cleans. And then on the bottom right, you see the offset distribution when you apply the same imaging algorithm to the VLBI sources. And you get generally a distribution of offsets, which gives us some confidence in how well the localization works there. This is, I would say, a pretty good scenario. Doesn't always look this good, but that's kind of how they tend to look. And so my last slide is just to highlight the things that we're producing in the completion stage. So once we get things really rolling with a completed array, we have now we have a minute latency ArcMinute precision alert stream. So that's something we've already used to send alerts to the Swift Guano system for rapid follow-up. And that's something that we intend to make more open. We also have an analysis system that Miles Sherman built, which does sort of in-depth interactive analysis of the burst data. So scattering, polarimetry, all the good stuff. Those results can be packaged into alerts and messages we send out to the community. Filter bank files, the classic, data product that will be served on the public archive. It's actually not there presently, but I will get to that this week. And localization regions. So this is, of course, how we do a lot of the science. So we have this arc-second scale localization, in this case, shown against a massive, massive galaxy to make it look really, really precise. But generally, we have galaxy scale localization regions, which are really helpful for helping us think about, well, do the association to measure distances, but also think about the source origin problem. I'll make one final comment, which is that we have been observing in 2025 with this completed array, our rates is not where we expect it to be also, which maybe is a theme for many of us. And we're digging into it. It seems like we might have a problem with a new source of RFI, which is really kind of peculiar. And we're digging into it. It might be like out of band RFI. So it's something that we're not fully understanding yet. And that's limiting the rate at which we're identifying new FRBs. If that gets resolved and we can filter it out, that means we'll be actually doubling the rate of discovery from the initial stage of the array, roughly doubling. So that's where we hope to be in the next few months. So keep your eyes open for those alerts. Thank you.
Thank you, Casey. We have some time for questions. Mawson, where's the, Laura has the catch box. Can it come this way, please? Someone take one for the team. I like that. Yeah. That's even worse. That's got to be a lot, right?
Hi, Casey. It's Mawson Salmons from here at McGill. And it was a great talk, so thank you for that. The kind of question that I had was that given that there is some through theme about not meeting like the desired specifications for like FRB rate and that RFI might be having an impact on some of this, in like trying to tackle this problem, do you think it's worthwhile to like have a few different instruments out there publish like wide scale studies of the RFI that they actually observe and put that out in the community as like a data catalog for people to help train on or help mitigate with new techniques?
Right. So the question is, would it help for instruments to publish RFI surveys essentially from their own, from what they see? Yeah, I could imagine there's a lot of value there. RFI does, there's certainly many classes of RFI, and many in cases they tend to be local. We actually, for DSC 2000 purposes, built a portable RFI monitor, which is out in Eastern Nevada right now, surveying the site. We didn't want to take for granted that we could, Starlink would tell us, exactly how it behaves, or the mobile phone companies would actually know what they're radiating. But in terms of ML-based, techniques or filters, I think there's a lot that can be done from real data that we measure. If we can make it, there are open source classifiers of various flavors, right? And convolutional neural networks that will look for sort of real bogus-like classifications. But they would certainly be improved with more diverse RFI categories.
Great, thanks.
Any other questions? Okay. Oh, Kelly? Give it a wall.
Who's in the middle?
Nice throw. Kelly Gorgie from CSIRO. So you'd mentioned extreme scattering events. That was really interesting. I was wondering if you could say more about what specifically, what sort of observables you're looking for in your data stream to flag that, and what you plan on doing with it. Because I think
that was a teaser. See
yeah.
It worked. Jacob will be here this week, and he should really be the one to tell you all about it. But it is essentially doing deep imaging with the DSA 110. So full cross correlation of all antennas. Hours long integration to make very long, deep, wide maps, and then repeating. So it's a transit instrument, and we'll just continue to monitor daily. And then there's follow-up also. There's a follow-up aspect to it, but. Yeah.
Thanks.
Let's thank Casey again. So our the second half of this session is going to be entirely online. Unfortunately, due to some last minute travel issues, our next speaker was unable to join us in person. So our next speaker is Chen Hui Niu, who is talking on behalf of the FAST collaboration. That is not.
Okay, it's my screen.
Yeah, we can see your screen.
Thanks, Lauren.
Yeah.
No.
Oh, you got the background.
Is this fine? Okay.
Yeah. Okay. Take it away. You have 11 minutes.
Thank you. Hello, everyone. This is Chen Hui Niu from Central China Normal University in Wuhan. Sorry for not being able to be in person this time due to my visa problem. It's my pleasure to introduce FAST here. Just to notice, my talk is on behalf of the FAST FRB Key Science Project collaborations. This is our logo. My talk will include 3 parts. For the FAST overview, the introduction for the FAST proposal call, the FAST program on FRBs. As most of my slides use a full screen layout, I will try to turn off my camera a little bit. Right, anyway. So in 1993, the International Union of Radio Science held in Tokyo. During the conference, astronomers proposed to build a next generation large telescope, which later known as the SK project, aiming to construct a very big telescope with a total collecting area of 1 square kilometers. Upon hearing this news, Narendong, who is the father of the FAST, was very inspired. He began planning to build the large radio telescope in China. He began the road to build China was full of challenges. Beginning in 1994, it took 12 years to take the site selection. FAST was officially proposed in 2005, and after overcoming lots of technical difficulties, the telescope construction was completed in 2016. So image here shows the original FAST site natural cast landscape with 12 local residents. So animation here shows the construction process of FAST. As Narendong once said, the best astronomical facilities are in fact built for the next generation of astronomers, for the young people who are studying now and those who will enter the field in the future. So we are the lucky generation. Okay. So first take a lot of experience from Arispo. So the photo on the left bottom shows Narendong and Chu Yihai, who was 2 FAST founders. That's a trip to the Arispo observatory in the early days. So image in the upper left shows the FAST alongside with the world famous Arispo telescope. Unfortunately, the Arispo collapsed in 2020 due to an accident. FAST continue the science from Arispo. The image on the right shows the scale compared with the world's largest telescope, offering a sense of a FAST impressive size. So FAST achieved a lot of innovations. It has a 500 diameters, that feature an active reflector surface composed of 4 sound panels that dynamically adjust to form a parabolic shape for each target direction, greatly improving the pointing flexibility. Its feed cabin is suspended by 6 cables and controlled by the computer. So the FAST feed cabin weighs up to 30 tons. So its positional control achieves accuracy of within 4 millimeters. It's very impressive. So 30 tons within 4 millimeters error. So FAST not only get a scientific achievement, but also makes the local economic development. The area within 5 kilometer radius of FAST is dedicated to the radio quiet zone. And the residents there near in the 5 kilometers will move to the Kedu town, about 5 kilometers away from the FAST center. So government built a lot better housing for them, and with fast tourism is bloomed. And astronomy town also was built in the Kedu town. It has restaurants, the hotels, and the science museum. We hope the FRB conference can be held in China next year, and so that everyone could visit this place. So based on its past bandpass, FAST has its scientific goals when it has been established. So including the H1 detection, the discovery pulsar, like the PDA, during the International WLBI network, perform high-resolution spectrum survey, detect the weak space signals, participate in the SITE. As it is proposed in the early years, FRB is not one of its basic scientific goals that time, but it added later. So this scientific goals has been realized by the observation programs. FAST has been supporting the regular science programs, the medium science programs, and large programs. Over the past 5 years, the large programs used to call the Key Science Project, covered 6 main projects. Each project have hundreds of hours to do its main science per year. So there are 3 science projects that are related to FRB. It is the Commensal Radio Astronomy FAST Survey, the Galactic Plane Pulsar Snapshots GPPS survey, and the FAST Radio Burst Search and Multi-Wave Observations. The last one is the most concentrated on the FRB science. So except the large program or the key science project, most researchers are likely to take the general proposal call to perform your own target. The general proposal call start from the March to May each year, and the result will be public in August that year. So you can find the link there is the official website for the FAST. It should have both Chinese and English, so it doesn't have any difficulty for the understanding the website. All the for the regular science proposals, it will have up to 50 hours per proposal, and for medium science is observation times span from 50 to 150 hours. So each proposal will be peer-reviewed and judged from the tech. CRAFTS as one of the FAST key science project or the large program, it was proposed by Dili using the high time frequency calibration injection technology. It could perform a pulsar search, the spectrum record simultaneously. So during a scan, CRAFTS also discovered a large number of pulsars. With 200 new pulsars were identified, including many in binary systems and millisecond pulsars. For the fast radio burst, CRAFTS has discovered 9 new FRBs. 5 of these FRBs have been published. All of the FRBs have shows low luminosity and high DMs, reflecting the new FRBs come from the early stage of the universe if we using the DM budget to calculate the redshift. CRAFTS also reviews a high FRB outscale event rate, higher than 10 to 5 FRBs per day above the faster threshold. So GPPS is also a large program. It is a high sensitivity, large area radio survey conducted by FAST along the galactic plane. It using the snapshot mode to search for pulsars and radio sources. During the galactic plane survey, GPPS also discarded 8 FRBs and 1 FRB candidate. these sources exhibit high DM and low fluence. So the largest first contribution in the field of FRBs come from the FAST Key Science project, FAST FRB Key Science project, a dedicated large program specifically for FRB studies, led by Zhu Weiwei and Zhang Bing. Also, FAST has very high sensitivity. It's a small field of view takes a less advantage for discovering new FRBs for the brand search. Instead, it is good at the follow-up observations of FRBs. For example, after the CHAM detected FRB, a new source, a potential repeater, fast perform follow-up observations. So the list here are the active FRBs that are fast frequently monitored by the fast KSP, FRB KSP. The KSP holds regular weekly meetings to discuss the follow-up observation strategies and the data analysis to the active FRBs. Usually, an interesting source is started from multiple scientific goals, so the leading to a series of publications. That's a general work style of the fast FRB KSP. So there's a case for the KSP work style. So for the FRB 2020-11-24A, the very famous one, this source was initially discovered by Chan and subsequently followed up by multiple major telescopes. During the follow-up observations, FAST detect a high event rate and get a large FRB examples, and uncovered a highly dynamic and variable local magneto-ionic environment. So this was proposed by Xu Heng, who is also a member of the KSP. And so the key findings was published in Nature in 2022. And however, the analysis of these large samples extended beyond the initial science discovery, so such as energy distribution, the morphology, the periodicity, the polarization. Each of these studies was carried out by different researchers. So these complementary works were published simultaneously, providing a comprehensive understanding of FRB 2020-11-24A. The other case is for FRB 2024-0114A, the hyperactive FRB. So this source is another fast FRB KSP collaboration case. So the hyperactive FRB has extremely event rate, and the total 10,000 bursts were collected. Junshuo Zhang led the discovery, and the paper is to be submitted. Alongside, there are several other papers focused on the different scientific goals like the RM, the morphology, were also carried out simultaneously. FAST also conduct long-term monitoring of some famous active repeater like the 1211-2, the first localized FRB. Using the FAST and GPT data and combined with the other major telescopes, FAST has revealed clearly evidence of a decade-long evolution in the local DM, and extremely the FRB and the complexity of the FRB's magneto-ionized ionic environment. So FRB 190520B is a source we discovered using FAST and have been continuously monitoring with FAST since its detection. It was first identified in 90 beam in drift scan survey of the crafts. So there are the 19 circles.
If that's okay.
Sorry. Notably, it has a second non-FRB associated with a competitive PRS. So the related discovery has been published in 2022. So over the 5 years of follow-up observations by FAST, we found that this source has never stopped. So it remained persistently active. Although its burst rate is not that high, but every time FAST pointing to this source, it can has a burst detection. Additionally, we have found the 12 DM unit per year decreasing for the total DM. Oh. So a quick advertisement I will take later. So finally, I'd like to introduce China's efforts on FRB detection are not limited to FAST. Many other existing and upcoming facilities will bring new opportunities for detecting and understanding FRB in the future. And thank you. I hope you can see you in China next year. I'll stop here. Thank you. Thank you.
Thank you so much. Have we got any questions? Are there any online? No. In which case, I have a very naive one. You said on one of your slides that you have 120,000 daily events. And then you also said in the same slide that you have detected 9 new FRBs. So that 120,000, are they from known FRBs? What are they coming from? I wasn't sure I understood that.
Yeah, maybe make a confuse. So for the OSCI rate, FAST has a low threshold, the very high sensitivity. So above the FAST sensitivity, the around 10 million Yansky 10 million Yansky millisecond. So above that threshold, we have the 10 to 5 FRB event rate per day, but it's for whole sky. So you know, FAST has a small field of view, so it doesn't have an advantage on the blind search, the FRB source.
Okay.
That depends
Thank
on
you so much.
how many. Yeah.
Oh no, Karen. Sorry.
It depends on how many sources FAST detected and using how many hours. But when you divide the field of view of FAST, very small one, so the event rate getting high, all sky event rate getting high.
Oh, thank you. I think we'll move on to our next speaker now. So if you'd like to stop sharing your slides. So our next speaker is Visweshwar Marthi, who is talking on behalf of the GMRT group. If you would
Thank
like
you.
to share.
Trying to share my slides.
Yeah, so you have 11 minutes.
Okay.
And I will come and talk into the microphone when you're running out of time.
Sure, thanks. Well, good afternoon, and I thank the organizers for inviting me. I couldn't be there physically because of some family commitments, but I'm happy to be representing the entire GMRT community and trying to give a brief overview of the telescope and its usefulness in pursuing FRBs. So unable to advance to the next slide. Okay, there we go. So the GMRT is primarily an imaging instrument. As you all know, it's an array of 30 antennas, 30 dish antennas, each of 45-meter diameter. And these antennas are placed roughly along the arms of Y, with roughly half of them along the 3 arms, and the other half in central condensation called the central square. So, and what this gives you is baselines up to about 25 kilometer, which give you very high angular resolution. Whereas the short baselines, which are all packed in the central 1 square kilometer, gives you sensitivity to diffuse low surface brightness features. And so this was designed in this way to optimize both sensitivity and angular resolution. And so, you know, this also means that it's primarily an imaging instrument. And like all synthesis interferometers, we use Earth rotation to synthesize a large aperture to fill the UV plane. And it has a very modern digital backend, which is an FPGA plus CPU, GPU-based hybrid digital backend. And being an interferometer, it allows you to harness its power both as an interferometer as well as a beamformer. And it's also primarily a low frequency instrument, but it also gives you seamless, nearly seamless coverage from 150 megahertz to about 1.5 gigahertz with very few gaps in between, as you can see on the top right picture there. So the observing bands are, for ease, we just call them bands 2, 3, 4, and 5, but they're typically about, the lower bands are about an octave wide from 120 to 250 megahertz, which is band 2, and band 3, which is the more popular band, which is 250 to 500 megahertz. The most popular one is, of course, especially in the context of FRBs, is band 4, which is 550 to 850 megahertz. And band 5 is our L band, which is from gigahertz to 1.46 gigahertz. Band 2 is mostly written with RFI, and so it's not very frequently used. But bands 3 and 4 are typically very popular with those who study FRBs. And on the right-hand bottom, you have a plot which shows the sensitivity with respect to the other telescopes, which are commonly in use now. Although this picture is somewhat dated, the GMRT is still quite competitive in terms of sensitivity, and it's especially useful if you want to follow up FRBs which have already been localized. So the heart of the GMRT is, of course, the wideband backend, which is a digital backend. It's an FPGA-based sampler plus packetizer, but the rest of the operation actually happens on a CPU GPU cluster, and that's used for real-time FX correlation. So it processes 100, 200, or 400 megahertz of instantaneous bandwidth. There's also a narrowband mode for spectral line observing, which is achieved by a digital down converter, which is running on the GPU. The interferometer provides instantaneously about 450 baselines, and the plus 30 comes there because of the autocorrelations from the 30 antennas. So you have about 465 instantaneous baselines at any time. And typically you get about 2,000 to 16,000, well, 2K to 16K spectral channels with about a 5-second time resolution. That's for the interferometric visibilities. But there's a concurrent beamformer, which can give up to 4 instantaneous tide array beams. And the way these tide array beams are actually achieved is by phasing up the array using the phases, the antenna phases, which have been solved for from the visibilities themselves. So the visibilities actually provide the solution. So the interferometer has to be running in parallel for the beamformer to be functioning. So the main 3 modes for the beamformer are the phased array beam, which is the other name for a tide array beam, where the voltages are added and then squared to get the intensities. There's also a coherently dedispersed beam where the voltages are added in phase, and then it goes through the coherent dedispersion kernel. And then there's also an incoherent array beam where the antenna powers are added to get the final beam. And of course, as expected, the phased array beam is actually the synthesized beam of the instrument, which is much, much smaller. The incoherent array beam is as large as the single dish beam itself. And the coherently dedispersed beam is, of course, the same as the phased array beam in terms of angular size. And we've actually been consistently working on upgrades to the GWB almost every time allocation cycle, and some of the new modes which have been unlocked are the in-field phasing, where point sources within the field are actually used to phase up the instrument, so you don't waste time going on to another phase calibrator, so it actually reduces your overheads. There's now also a gated correlator, which is useful for pulsar studies. A new high time resolution visibility mode is now available, which can give you visibilities at 83 milliseconds. There's a multi-beam recorder with 4 synthesized beams, and this is the mode where you can actually look at 4 different sources within the primary beam, which is very useful if you want to do follow-up on FRBs, as well as also VLBI. There's a post-correlation beamformer, which I have not listed at the top, but there we actually sum the visibilities instead of the antenna voltages. And then we also provide full Stokes beams available for the phased array, And then there's a new coherent dedispersion mode, which was quite challenging to implement for the full 400 megahertz at band 5. There's also a baseband beamformer up to 400 megahertz, which is now being used for VLBI. But the baseband itself can also be used for niche science. And what's coming up is a parallel backend, which will give you the per antenna baseband. So for every antenna, one's going to get the full 400 megahertz baseband. Good luck dealing with the data, but that's definitely in the works. So what do we use the beam for? So in the context of FRBs, the phased array beam is best used if you want to follow up already localized FRBs. For example, this is a proof of concept localization of FRB 180916B, where the GMRT was used both as an interferometer and the beamformer mode to study the bursts, as well as to prove that the concept of localizing FRBs simultaneously is actually quite effective. So, here is another example of using the GMRT in the incoherent array mode, where once Chime locked on to this 2020-11-24A with a lot of these ATELs coming out. Many telescopes around the world were looking at this interesting FRB. The GMRT at the time did not have the precisely localized position of this FRB. So we just used the fact that it is only localized to within about 40 arc minutes, which is exactly the primary beam of the GMRT. And so we had to use the telescope in the incoherent array mode, where the entire primary beam is accessible through the beamformer. And so
you have 2 minutes left.
Thank you very much. And so we were also able to localize the bursts here and also detect persistent radio emission, which is also out as an ATEL. And of course, the full Stokes mode, which has been very useful, and Surya Rao has actually done some very nice polarization work, and that's the figure on the right, where you can actually see the GMRT points following the polarization of this particular FRB after the secular evolution, which was reported by Ryan McKinnon et al. So this paper just got published recently. And on the right, of course, you have more results from using the tide array in both the multi-band and multi-subarray mode. So this was, again, baseband data was recorded, and this paper gives you the results as from that particular analysis. And many of you might have heard in previous editions of FRB. I think it was the last one in Thailand, where my colleagues have actually put together this wonderful system. It's called Spotlight, which is a real-time comment search program for FRBs and transients. In its full glory, it will give 2,000 beams with 4K spectral channels and about a few millisecond time resolution visibilities. At the moment, you can actually apply for competitive time using the Spotlight system, and about 100 hours of time is available per cycle. This will also dump baseband based on triggers, and which can be actually used for VLBI localization. And there's already some understanding between Spotlight and Burst, which hopefully will help localize many FRBs. And the first light has already been achieved. So we already have a system with 160 beams. And what you have here is just showing how the Spotlight system is organized. And so yeah, so this is just a brief overview of how the GMRT can actually be used as an instrument, primarily for following up FRBs. It's quite sensitive with the wide bandwidths, and it's also a versatile telescope. You can use it as an interferometer, as a beamformer with multiple modes, useful for deep observations. And several publications have actually come out of such observations. So at all frequencies below 1460 megahertz, it's quite effective, sensitive, and multi-band, multi-subarray observations, multiple beam modes have actually enabled some very, very interesting science. Of course, one now can also record baseband data up to the full 400 megahertz at band 5, for which the best application is VLBI for localization. And of course, Spotlight is coming up, and we're all quite excited here to be able to, we hope that in the next few years, we'll have quite a few FRBs through this commensal program. And so, we're looking forward to that. Thank you very much.
Thank you so much. Do we have any questions in the audience? Kyle. Okay, Catchbox. Or
from behind.
Or someone.
Somebody in the
Thomas,
middle,
or...
maybe. Heads up. Pavan.
Yeah.
Yeah.
Okay.
Hello. Kyle McGregor. I'm a master's student here at McGill.
Can you maybe turn around so everyone else can
Sure.
hear your lovely question too?
So I was curious if this Spotlight search is going to be using all 5 frequency bands of GMRT, or if it's just using the 2 specifically that you said like to be used for FRBs within. So it was like 250 to 500 and then 550 to 850.
Yeah, so it'll primarily use bands 3, 4, and 5 for the simple reason that band 2 is just full of RFI. But remember, this is a commensal program. So any observation that's looking at any part of the sky, Spotlight is going to be observing in parallel. So it's a commensal program. But there are also some policy issues which have been addressed. And you can actually find some information about that on the Spotlight webpage.
Thank you.
So it's primarily going to be bands 3, 4, and 5.
Awesome. Any other questions? Cool. In which case, we would all like to thank you again.
Thank you very much.
So our penultimate speaker of today is Kaustubh Rajwade, who is going to give us an overview of the Meerkat radio telescope and what it's been doing for FRBs. Kaustubh, I'll give you, you have 11 plus a bit minutes, and I'll come and speak into the microphone when you have 2 minutes left.
All right, thanks. Can you hear me?
Yes, we can hear you.
All right, perfect. Yeah, thank you so much for giving me this opportunity to talk about the Meerkat project. Yeah, I'm sorry I can't be there in person, but I'm more than thrilled to give you an overview for this project. So yeah, I mean, I don't think I need to really motivate too much about why we need to study FRBs, but I think one of the points I would like to make here very quickly is that I think it's quite important to find FRBs, that are much further away at much higher redshifts, not only to, break the degeneracies between different emission models, but also kind of really realizing their true potential as probes of cosmology. And so it absolutely makes sense to build a real-time FRB detection instrument at the Meerkat radio telescope, which is one of the most sensitive radio telescopes currently operating. So Meerkat, for those of you who don't know, is a 64 dish radio interferometer in the middle of the Karoo Desert in South Africa. And Meertrap actually works commensally, which means that any data that are being taken with the telescope are being continuously looked at and searched for FRBs and other fast transients using a pipeline that I'll go through in the next few slides. But before I begin, I would just like to talk about the collaboration. So Meertrap is mostly led a University of Manchester-led project. Ben Stappers is the PI, and the collaboration includes a lot of teams from Max Planck in Bonn and University of Oxford, And we got a tremendous amount of support from Cereo during the commissioning and testing phase of the system. So just want to give them a massive shout out. And of course, we collaborate pretty closely with the F to the 4 collaboration for following up our discovered and localized FRBs. So in the previous slide, I mentioned commensal observing. What it means is that the telescope is being used by many different projects. So when Meerkat started science operations, it was mostly focusing on these large survey projects that have been given an incredible amount of time on the telescope. And so these projects have been running now for a few years now. And what it means is that we're basically getting a huge chunk of observing time on sky with the Meerkat to look for fast radio bursts. And so just a lot more opportunities, a lot more, more discoveries to look forward to. So by the time the LSPs end, we'll roughly would have had 20,000 hours of observing time and even more, which I'll talk about later. So Meerkat predominantly works in 3 observing modes. So there's the incoherent mode, where you're taking the detected parts from all your antennas and summing them up so to sample the entire primary field of view of the telescope. But it does mean that it's not the most sensitive search. And so the sensitivity we get from that kind of a search for FRBs is comparable to what you would get from a 64-meter single dish like the Murray-Yang radio telescope in Australia. In the coherent mode, simultaneously, while we do the search over the full field of view, we tile some part of this field of view with smaller but more sensitive coherent beams or phased up beams. And so because of compute limitations, like I said, we're not able to tile the full primary field of view, but we roughly can do a more sensitive search for FRBs in that 0.4 square degrees of the sky. And it uses the 40 core dishes of the Meerkat array to make these beams. So you can compare this search to something that you would do with a 100-meter dish like the Green Bank telescope in the US. And then lastly, we also have this mode where, if we find a discover, or if the real-time system detects an FRB, it triggers storage of these channelized complex voltages from every single antenna that's observing, which then can be processed offline, not just to actually localize the FRB in order to identify the host galaxy, but then also do some high time resolution and polarization studies. So just to quickly give you a brief overview of the pipeline. So the beamformer, the actual beamformer, has been developed by our colleagues at the Max Planck Institute in Bonn, which generates these 768 beams, and these coherent beams along with the incoherent beam, and those are then received by the Meerkat compute cluster, which is made up of 65 nodes. Each node then basically processes to about 12 coherent beams in real time. And the single pulse search is done by a GPU-based algorithm called AstroAccelerate, which was built as part of the SKO single pulse search pipeline prototype. And then we also have a machine learning classifier, which then tries to identify the candidates as whether they're astrophysical or not in real time. Then, as I mentioned before, we have the transient buffer. So in the case that the real-time system finds or identifies a candidate as being astrophysical, we send out a trigger internally to the beamformer, which then saves the raw channelized voltage data from all these antennas, which is constantly being received on a ring buffer. So one thing we actually do is that when we save the channelized voltages, we actually take into account the dispersive sweep of the FRB. Which means that this is a huge help in terms of then actually it kind of overcomes the storage limitation that we have, because saving channelized voltages, as you would know, requires a lot of storage space. And so while we are able to save, about 30 to 50 seconds of data, we typically only end up saving about 300 milliseconds of data right around the time of the FRB after taking into account the dispersion sweep. Some of these, the key functionalities that we also have, I mean, the beamformer is really flexible. So what it means is that if we have multiple sources in the sky, we can actually create smaller tiles of coherent beams around these sources, just to follow up. So for example, if we have found something new, next time, the telescope is observing the same field, we can actually put a separate tile of coherent beams there to follow up that source to just, see if we can look for repeat bursts, or like, in case of a galactic source, just look for more bursts from the same source to maybe find the period. And also, we also have the capability of changing the overlap between, successive or just adjacent coherent beams. And this is quite useful if you want to also kind of quickly localize a source. So if you get detections in multiple beams, you can use that to get a very good localization, even before you actually localize it using the transient buffer. Now, we know that finding a multi-wavelength counterpart to an FRB is quite important in order to figure out what, to really discern the nature of FRBs. And so there's a lot of opportunity to do that actually with MIRTRAP, because there is an optical telescope called MIR-LICT based in Sutherland in South Africa, which is a fully robotic optical telescope, and that actually can co-point or tries to co-point with MeerKAT for simultaneous optical coverage whenever possible. And actually, very recently, we managed to achieve an almost contemporaneous optical coverage of one of the FRBs we discovered that I show here, which was localized to this nice potentially interacting galaxies. And this figure in the middle is just showing you kind of the limits, the optical limits that we got at the time of the burst. So yeah, so there's still, so we have shown that this can work, and we're still doing this and trying to see if we can actually get a fully contemporaneous optical coverage for some of our sources. So just to kind of quickly show you, so MIRTRAP has been operational now for almost 5 years, more than 5 years. And so far we have found more than 110 new galactic discoveries, and keep finding more. Most of these, tend to be pulsars or highly intermittent rotating radio transients. But we've also found some interesting sources like this middle panel, which is a 17-second pulsar, which we're following up. And also, as you would know, we also discovered this 76-second pulsar about 3 years ago. And then we're also finding some single pulses that are showing a lot of interesting structure in their emission. And Jun Tian will be talking about this, in the coming few days. So please stay tuned for the results.
You have 2 minutes, Kels.
Yep, thanks. We have found more than 80 FRBs over the last 5 years of our operation. More interestingly, I would say we have found about 25 high DM. So when I say high DM, DM of more than 1,000 kind of FRBs. And again, we're working closely with F⁴ collaboration to for following them up at optical wavelengths as soon as possible to try to localize them, find their redshifts, because I think that's kind of one of the strengths of a MeerKAT, in the sense that it is able to find these fainter and farther out FRBs. And so just to kind of end on the recent highlights, like I said, we're generating this sample of really high DM FRBs, and a lot of which we have localized to subarc second precision, which means that we'll be actually able to figure out what their hopefully what their host galaxies are, and then actually estimate a redshift for them. We have also recently discovered a repeating FRB. And so Kavya Saji, who's a PhD student in Australia, she'll be talking about it, I believe, in the next few days. And also, we have recently discovered this coherent radio burst from a galactic source from a known radio quiet neutron star, so which was really interesting, completely serendipitous. And so, so we can see that, there's a whole array of science that we can do with MIRTRAP. And so Manisha will be actually will be giving a late breaking news talk on one of these recent results on one of the high DM FRBs. And also Ben will be talking more about some of these results. So please stay tuned for that as well. So I think I'm just going to end there with my summary. I think all I'm showing is that, yeah, I think in conclusion, I think MIRTRAP has allowed for some detection of some, an array of fast radio transients over the last 5 years, and has utilized all the capabilities of Meerkat. We have about 30% of our FRBs that we have localized to arc second to sub-arc second precision, and at the moment trying to follow them up and identify the redshifts for their host galaxies. And lastly, MIRTRAP also runs commensally on open time projects on Meerkat, and so people can technically actually use MIRTRAP or can ask for MIRTRAP to run commensally with their projects that they have running on the Meerkat telescope, and this will continue to happen in the future. So thank you for listening, and I'm happy to take questions.
Thank you, Kaustubh. Do we have any questions in person? Amanda Cook. Sounded weird saying your full name.
Hey, Kaustubh. I was just curious,
Can you
what
please
sets
project to the
right?
rest of the
What
audience?
sets the limit for like how often you guys are able to do the simultaneous or near simultaneous optical follow-up with your FRBs?
Yeah, it really depends. Because I mean, firstly, yeah, it can only happen at nighttime, and so it's very, very weather dependent. And a lot of times there are also some I think we have just been a bit unlucky in the sense that we've had a few FRBs which were discovered during nighttime, but for some reason either Mirlicht was observing somewhere else or there were some technical issues with Mirlicht, and so it has just not happened. So this was the first time it happened. It got us super excited. So hopefully it happens a lot more frequently.
Yeah, thanks. Fingers crossed.
I have a quick question about your galactic discoveries,
Mm-hmm.
part of your talk. Were they all found in the Thundercat fields, or are they found kind of regardless? For
Yeah,
context,
so
Thundercat is an X-ray binary / galactic transients program running on Meerkat.
yeah, so we mostly tend to find most of the galactic transients in the plane. So, and Thundercat mostly observed in the galactic plane as well. But we also end up finding a lot of these transients in some of the pulsar timing projects as well, because a lot of the pulsars are also in the galactic plane. So yeah, so any project that's mostly looking in the galactic plane, we tend to find a lot of the galactic sources there.
Thank you again, and also thank you for staying up so late to give your talk. Let's give a
no worries,
final round of
thanks.
applause. So our final speaker of this evening or this afternoon is Benito Marcote, who's going to be talking about the precise EVM program. Benito, you have like 11-ish minutes, and when you get to 9 minutes, I'll come and talk into the microphone and give you a warning. Is that all right?
Okay, thank you. Perfect.
Nice background.
Okay, thanks. Okay, so thank you. I hope everyone is still awake and not too tired after the whole day. I'm sorry for not being there. I would have really loved that, but yeah, for different reasons, I had to do it online. So in any case, in this talk, I will do a summary of what we've been doing and what are we doing with the European VLB network observations on FRBs, and more precisely on the PRECISE project that uses these observations. And of course, I'm talking on behalf of the AstroFlash group that I'm part of and the PRECISE project. So the motivation of observing FRBs with the ABN started quite early when we really realized that having a lot of FRBs discovered was not enough if we really want to understand where they are originated and actually what's the environment or which formation channels may lead into the formation of FRBs. So to understand that clearly, we really need high resolution localizations of FRBs, and that's why we started conducted searches on FRBs using the European VLBI network, which is an array of telescopes that are mainly in Europe, but also in Asia and Africa. And with them, we can reach a millisecond resolution, and at least in the continuum, micro-Jansky sensitivity. So with that, we can be sure that we can pinpoint any FRB that we detect in our observations to the parsec scales on the host galaxy. So with that, we can really narrow down what's the local environments there. This is part of the Astroflash group that is led by Jason Hessels. We are based in the Netherlands and in Canada. You can look at the website to see all the people that we have in our group nowadays. And we follow up FRBs with different approaches. I will talk and will focus only on the PRECISE project, which is led by Franz Kirsten, which basically lies on this, observing with the EVN disease. So this started with regular observations within the EVN, but of course, at some point we realized that we needed more observing time than the one that we were allowed in the EVN or that it has for the whole year if we really wanted to follow up a lot of the FRBs that are active. So with that, we started this project where we kind of use the free time that all the small dishes in the array has along the year. So we can actually spend roughly nowadays hundreds of hours per year, which basically is one observation every 2 weeks. And we follow up all the FRBs that are currently active, either because of a trigger following up the chime detections or any other observatory. So of course, when you are using such number of small dishes within the network, you can use them in 2 different modes. One is using them as just regular single dish telescopes. So we can observe the same FRBs from different locations, either at the same frequency or different frequencies. And the other one is the truly interferometric mode, where if we detect an FRB, we correlate with the regular correlator at Jive from the EVN, and then we can perform the millisecond localization. So in the first mode, this is what we call the HyperFlash project, which in the last years we've been observing with these radio telescopes at different bands. And to put it in context, just last year with only Westerbork, we achieved almost 7,000 hours only in 1 year. So this allows us to do a big monitoring of active FRBs. In any case, I'm not going to go into details on these ones because tomorrow you will have a fantastic talk by Omar on this campaign and this project. And then he will actually show you why this is really important and everything that you can do with these small dishes that you cannot do even with larger ones, and what you can learn from FRBs from these observations. So just attend the talk tomorrow. In any case, this talk will focus more on the interferometric, the VLBI part. Until basically last year, there was a huge jump between almost all other telescopes that could localize FRBs, which in the best case scenario, they could perform localizations on their second level. So for the nearby FRBs, you could already pinpoint clearly the host galaxies, but this was not possible on the farther ones or fainter ones. So at least with our observations, we could perform millisecond level, which was like 3 orders of magnitude deeper in resolution than the other facilities. However, this has changed this year, and it has been really nice to see last week the first tens of millisecond localization given by Chime. So now we have other tools that can actually localize these FRBs at this precision. Of course, this will be a new era because with time we will be able to get hundreds, thousands of FRBs on that regime. The difference with respect to PRECISE is that we could still go a bit down to the millisecond level. And of course, we have much more sensitivity, especially in the continuum regime. So to put it in context, during these years, we've localized and published 8 FRBs. And then from these ones, it was clear why we really need such a precision, at least in a number of FRBs. So our numbers are way far from what you can do with CHIME, of course. We are not talking about 1,000 FRBs, but we know that for a significant fraction of them, having millisecond relocalizations will be really relevant if we want to actually understand these sources. So this is quite clear in those ones that are related with PRS, a persistent radio source. We have a few sources that resembles really like twins because they are in the same host galaxy. Both of them are colocalized with a persistent and really compact radio source. And here, things to precise, we can actually put two really constrained measurements sorry, in these FRBs. One is on the compactness on these persistent radio sources. So to date, our most stringent limit is less than 0.7 parsecs for 121102. And this is really constraining upper limit that actually allows us, if we put also in context with the light curve on the 10-year time scales, what's the nature of these sources? Because it still is completely not clear. And then by constraining the size and the variability that these sources may have, is the only way that we can actually solve if this is superluminous supernovae, a magnetar-with nebula, or just a massive black hole within the dwarf galaxies. So we see this trend in these sources that are quite extreme with high RMs, and by adding on new ones in the coming years, actually we will be able to trace if all the repeaters with PRSs are in the same host galaxies and how compact are these sources. However, identifying PRSs is not that easy, especially when you think that many FRBs are located in star-forming galaxies. So that means that in many cases we have radio emission just because of the star formation that either probably is in the vicinity of the FRB, either if it's inside or outside. And this is something that we really see that VLBA observations, like the ones that we've been conducted, it's really easy to disentangle this emission because on the millisecond level, you are already on the edge where you will resolve out the star formation just because of brightness temperature limits. And that means that if there is a star formation, purely star formation emission, then all the emission will be extended. So you cannot see a compact emission that comes from that mechanisms. So in that case, we can confirm the existence of
You have
PRs.
2 minutes, Benito.
Yeah. Oh, okay. Yeah. And of course, the other way is if you have a FRB that is either far, quite distant in a crowd field, or you have a very weak host galaxies. And this was a perfect case. So far is the faintest host galaxy, and it makes a perfect clear where you really need deep optical and radio observations to identify what's the actual true host galaxy. Because in this case, the FRB is associated to the 4 galaxy. It was not detected in normal, even from the Keck observatory. And then without the millisecond localization, any path analysis was actually linking it to a different galaxy. And the same happens in cases where we really see structures nearby, but then making the FRB placed outside or really in the vicinity of some formation of some regions actually makes a difference in the scenario that can explain it. So this is what we've been doing in the last years. What is upcoming in this year, basically, you may have seen a paper that you just submitted a few weeks, some months ago. This was the hyperactive 240114A, and then Mark did localization on this source, and this is the first time that we find an FRB in a dwarf galaxy, but then this is a satellite galaxy, actually. So it's a satellite of a more regular host galaxy that we see there. And another new localization, I will not go into the details here because tomorrow you will also have a talk from Alex that will actually reveal one of our new precise localizations. And stay tuned with this one because it's a really interesting case that we've been seeing again. So with that, I will finish here. With Precise, nowadays, we are serving hundreds of hours, basically targeting active FRBs. And when we use the single disease, actually, we are on the regime of thousands of hours. So we're the instrument that can achieve both micro-Jansky sensitivity on the continuum and millisecond accuracy. So if we can place where the FRBs are associated with persistent radio sources, this is a key instrument. Nowadays, we are running through a regular EVN project, the so-called EVN Lite. And as this was actually mentioned in the previous talk, nowadays the GMRT is participating also in EVN observations, and MERCAT will do it at the end of the year. So actually we expect that we will be able to even boost more the sensitivity of these observations. And from the scientific point of view, we really think that this is key if we really need to understand the local environments on FRBs, given the diversity of environments that we are seeing, and especially if the most extreme cases, the ones with very high RM and dwarf galaxies are associated with PRSs. And I will finish here. Thanks.
Thank you, Benito. Do we have any questions? No. Matthias? Someone do the honors. That's going to have to stop somewhere in the middle. Oh, that was a good try. I reckon by the end of the week, we'll have this down like flawlessly. Yeah, would you like to introduce yourself and ask your question?
Yeah. Hey, Benito, it's Matthias. I was just wondering, what's the gain in sensitivity that you expect having Meerkat join the EVN roughly?
Only with, there are two things actually. On sensitivity, we will be going down by 40% probably. Don't have the number in my mind, but I think on the 8 hours time scales, I think we will be able to go down to the 3 micro-Jansky RMS at L band. And the other part is that we win resolution, even if the baselines are not increasing, because we already have antennas on South Africa. Actually will allow us, especially on faint sources, to increase the actual resolution on the images. So in that case, we will be able to drop the levels, so the constraints on the sizes of these PRSs, hopefully to the 0.5 or even less parsecs if they are closer.
Awesome. Thank you.
And if we have no more questions, let's thank Benito again.
Thank you.
And before we wrap up for the day, Alice has a couple of announcements to make.
Yeah, so thanks everyone for being here. I know it's been a long day, but I hope when we go outside, it's going to be sunny and you can go and get some poutine and maybe go enjoy some of the beautiful murals, walk on the mountain. For those who are speaking tomorrow, please come check your slides and make sure you understand how everything works. Ideally, first thing in the morning around 8:30. If not, you could do it during lunch or the coffee breaks. And also those who will be chairing tomorrow, if you could come find me either now or in the morning, that would be great. Thank you.